respected dignitaries, honored guests, esteemed faculty members, industry professionals, and dear students. It is my privilege to warmly welcome you all to this national workshop on materials for transportation. This workshop aims to explore recent advancement in materials and technologies used across transportation sector like rail, road, marine, and aviation. It seeks to foster knowledge sharing and collaboration on developing lightweight, durable, and sustainable materials for safer and more efficient mobility systems. We are delighted to have among us today like academicians, industry professionals, and students who are deeply interested in material design and emerging technologies shaping modern transportation systems. Your presence truly enriches this platform of knowledge exchange. We sincerely thank our sponsor, Jindal Stainless Limited, for their generous support and shared commitment to advancing materials in transportation. To mark the auspicious beginning of this workshop, we now proceed with the lamp lighting ceremony. May I request our Honorable Vice Chancellor Sir and dignitaries to kindly come forward to ceremonial lamp lighting.
या कुन्देन्दु तुषारहारधवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्कर प्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा शुक्लां ब्रह्मविचारसारपरमा आद्यां जगद्व्यापिनीं वीणापुस्तकधारिणीमभयदां जाड्यान्धकारापहा
Thank you, everyone. I now humbly request our Vice Chancellor Sir to felicitate our esteemed guests and convey our profound thanks for their presence on this special occasion. I would like to welcome our guest of honor, Professor Paras Prasad, who is the distinguished professor at University of Buffalo, USA. I would like to welcome Mr. Arup Kumar Malik, Executive Director of HAL Management Academy. I would like to welcome Mr. Ranit Rana, Associate Vice President of Sales and Distribution, JSL. I would like to welcome Dr. S. Parivalal, Chief Scientist of CSIR, Structural Engineering Research Center. I would like to welcome Mr. Naveen Chandra, Development Director of Alstom. I would like to welcome Dr. Shankar Venugopal, Vice President of Mahindra Research Valley. I would like to welcome Professor Amol Anant Gokhale, Professor of IIT Bombay. I would like to welcome Dr. Senthil Kumar S., Senior Principal Scientist of CSIR National Aerospace Laboratories. I would like to welcome Professor P.S. Robi, Professor of IIT Guwahati. I would like to welcome Professor P. Chakrabarti, Professor of IIT BHU. I would like to welcome Mr. Biswaroop Bose, DL Transverse Discipline of Alstom. Now, I would like to welcome our Honorable Vice Chancellor, Professor Manoj Chaudhary sir, for his welcome address.
Good morning. First of all, I would like to welcome all our distinguished guests and speakers to this very, very important event that we are doing in our history of Gati Shakti Vishwavidyalaya today. For the next 5 or 7 minutes, I would like to briefly explain why we are doing, because it's always the purpose that must drive our actions. As we all know, today there is a tremendous progress happening in our country all around, particularly in the infrastructure sector, whether it be railways, aviation, highways, maritime, all these aspects. On one side, we are building Indian Railways every day at a rate of 14 km a day, adding new track lengths. Another side, we are building national highways maybe at 35 km a day, and we aspire to go to 100 km a day. On the other side, we are building new railway stations, we are introducing new trains, we have doubled our number of airports in the country in last 11 years from 74 now to 162, and we aspire to be 350 in some years. Same is the case in the port sector. We are building new ports, we are modernizing our ports. Same is the thing happening in the inland waterway sector. Therefore, to summarize, across land, water, and air, all forms of transportation, there is a great progress happening in the country. In order to facilitate manpower development for this sector, for which this year in the budget also there is a provision of 12.2 lakh crore rupees. Last year it was 11.2. Every year we have a significant amount of capex, capital expenditure provision for the infrastructure sector. In order that this sector grows momentum, we need superior human resources for the sector. And therefore, this university was established in 2022 through an act of parliament to cover the entire transportation and logistics sector. Therefore, it is our national mandate to not only look at education, research, executive training, but look at the entire ecosystem in the sector for the development of railways, maritime, aviation, and all forms of transportation. Sustainability being a very, very important part of it, because as India always says, one earth, one family, one future, and therefore each of our action is for the net zero targets that the government has already declared. When we do that, currently we have several programs related to rail engineering, both at bachelor's level and doctoral level. We have programs in aviation engineering. We have programs introducing in maritime engineering. We have programs in port and shipping logistics. And compared to any other university or institute or in India, we have an official mandate to train officers of the government of India. We have an official mandate to train all officers of Indian Railways who join Indian Railways, whether through civil service or through engineering services. Their entire probation period of 104 weeks that is 2 years, is designed and conceived by GSV. Similarly, we train a large number of defense services officers across Indian Army, Indian Air Force, and Indian Navy in the logistics and supply chain management. Similarly, we train a large number of civil services officers on efficient infrastructure planning and development across the country. Last year, we launched a 15 hours training program, online training program that was launched by the Union Commerce Minister, Sri Piyush Goyal ji. Very happy to say that close to 200,000 officers across the country had registered for the program, with approximately, I think, 60,000 officers already completed the program. So that means across civil services, across defense services, across railways, across the entire industry, we have a very big mandate and role to play. So far, we do not have a dedicated program on the material science. Though the material science is absolutely important, whether it is for the railway track that we make, or whether we look at the wagon design to carry, for example, important commodities like salt, we need lightweight wagons, for example, materials that are non-corrosive in nature, and therefore material science becomes a crucial foundation for us. Same is the case whether we look at new composite materials in the aviation sector that is currently being taken very rapidly. Same is the case in the highway sector, that last year when the Dwarka Express was inaugurated, it took a large number of solid waste and the plastic waste from Delhi and used them into construction of the highways. That means newer ways of how to utilize sustainable practices is also important as we look at the new material paradigm. Across all forms of transportation and logistics, therefore, material science becomes very important, whether for warehousing sector, the kind of materials we need, or whether for Gati Shakti cargo terminals that we are making. Every aspect needs new materials. And therefore, we are currently conceptualizing to introduce a bachelor's program and a master's program at some point of time, maybe in next year itself. Dedicated programs on material science, maybe also in metallurgy, to expand our horizon for the entire transportation logistics sector. Important players which are present today, for example, Jindal Stainless Steel, have a very important collaboration project already with us for encouraging stainless steel as one of the very important aspects of the transportation sector. Same is the case with one of the biggest railway companies, Alstom. Today, when President Macron is in India, and only yesterday I had to give some updates about what collaborations we are doing with France. And I was very, very happy that we have big collaborations from GSV with Airbus. We already have a center of excellence set up for sustainable aviation fuel. It is inaugurated already. We have a big tie-up with Alstom. And many students are working. Currently, we are in a phase to introduce a focused MTech program for Alstom employees to train them. We have a big collaboration with world's one of the largest aero engine makers, Safran, which has recently set up their engine MRO facility in the country, the first one to set up engine MRO in whole of India. Therefore, with many of the French companies, we already have a good collaboration. And I know the current visit at high level will also expedite our collaboration. I'm very thankful to Mahindra Research also being present here today. I'm very thankful to all the institutes and the leaders of the institutes who are here today, and in particular to Professor Prasad ji, who has traveled all the way from sunny Buffalo, from US to be with us as guest of honor. And therefore, what are we looking from today's summit? It is not purely a research symposium, wherein we only talk about advances in the sector, but we are looking at the relevant aspects of material science for the transportation and logistics sector. If I can visualize, maybe the set of invited speakers today will form a kind of an advisory committee for us, who will advise us, guide us when we launch our academic programs in the bachelor's and the master level. All the programs in the university are industry driven, and therefore industry is involved from day one in terms of what to teach, who will teach, how do we do practical immersion to improve employability for our students. And it is that result only that last year we had 91% placement, one of the highest in whole of the country. All 91% of students got job before they could graduate from the university. This year we are expecting 100%. And with industry support, we are moving forward. Therefore, from today's deliberation, we are looking at the key themes that will drive and propel the transportation sector going ahead. When we have a chance to introduce a new program in material science, we do not want to just do a run-of-the-mill program that just looking at different IITs, what they are doing and introduce similar kind of program. We really want to look from the leaders, both in academia and industry, on what is the cutting edge topics that are needed for India to drive its mission in the transportation and logistics sector. And that is why we want to look at a curriculum in future which is futuristic, need of the hour, as well as relevant to the industry's needs. So that is one of the expectations that I have. Many of the students today are not exposed to material science per se. They might have one course or two courses at best in their entire 4-year program. But going forward, materials become a very, very important part, as I highlighted. And therefore, today's discussions will also give them an idea of how new materials can transform the entire transportation and logistics sector. We will build the new programs going ahead, but today, the seed that we are going to sow, hopefully in next years will become and blossom into a very big tree, a tree that will be very, very important for the India's entire transportation and logistics sector. 2 days back, I had a chance to update our railway minister, who is also the chancellor of the university, that we are doing this event, and he strongly encouraged us to do more and look at what problems of the railways can we solve. Today, India, for example, has become biggest hub for coach manufacturing. Today, India, wagon manufacturing India. Last year, India made number of locomotives in the country, 1,681 to be precise, which was more than the combined total of what was made by Europe plus North America plus South America together. And therefore, in locomotive production, Make in India initiative has a good role. In new train sets, great role. Automatic train protection system, great role. Tomorrow, for example, when we introduce new materials for improving wheel-rail interactions, if we have to design new elastoperic plastic kind of pads, EM pads, it becomes very, very important. And therefore, materials plays a very, very important role. We are trying to make our trains and introduce newer lightweight materials into them that can last longer, that can make the trains lighter, that can be strong enough, that can have resilient, and also support sustainable practices. And with that goal, I would like to once again welcome all of you. I am particularly thankful to Jindal Stainless for sponsoring the event today and coming forward wholeheartedly. I look forward to interacting with all of you. And I just also highlighted that our interaction does not stop merely after the talk is over, but actually it begins when the talk is done, so that how can we build tomorrow's new material science program for the country. Thank you so much. Once again, welcome you all. Thank you.
Thank you, sir, for those inspiring words. Now, it gives me immense pleasure to invite our first speaker, who is our guest of honor, Professor Parasan Prasad, who is a distinguished professor and the Samuel P. Capon Chair of Chemistry at the University of Buffalo, USA, and serves as Executive Director of the Institute for Lasers, Photonics, and Biophotonics. He earned his PhD from the University of Pennsylvania and BSc MSc from Bihar University, India. His research focuses on nanophotonics, nonlinear optics, biophotonics, nanomedicine, sensor technology, and energy materials, with application in imaging, photonic devices, and nanofabrication. He has received numerous honors, including the SPIE Gold Medal, ACS Peter Debye Award, IEEE Fellow, and multiple honorary doctorates, including one from the IIT Jodhpur. Professor Paras Prasad is also a Fellow of the Optical Society, American Physical Society, and National Academy of Inventors, and hundreds of scientific publications that have had broad impact in photonic science and engineering. Today, he will be delivering his talk on materials and photonics for transportation and aviation. Welcome, sir. We eagerly look forward to your insights.
This is okay. Namaskar. Good morning. I'm really truly honored to be here at this very important and timely workshop. And for that, I thank Professor Manoj Chaudhary for this invitation, with whom I have a special relation. I call him my younger brother, truly younger, much younger. And so I cannot help bragging about himself. You know, he has been a visionary leader who has brought new strategies and vision to advance the transportation and aviation sector over here. He has put GSV on world map. So again, congratulations for all the successes that he has already shown, and we can expect a lot more from him in coming days. So with that, I would like to say that I can hardly wait for a day when we will have a statue honoring him in the university, right? As the legendary VC. So again, many more things to come, and this is, as he said, this is much needed input for this country to develop, continue to develop its infrastructure and logistics in transportation and aviation. You can hear me in the back? Is it okay? Hello, can you hear me in the back? All right, nobody's answering. So let me move on. So I'd like to introduce our Institute for Lasers, Photonics and Biophotonics, abbreviated as ILPB, which is a part of University at Buffalo, and University of Buffalo is a part of the State University of New York system. So for a long time it was called at State University of New York at Buffalo, or SUNY at Buffalo, which Manoj called SUNY. I like the word sunny better because we can use that, lots of sun in winter. So that's the same thing, but now we call University of Buffalo, abbreviated as UB. And it's a multidisciplinary research center, one of a kind, which integrates engineering, sciences, and medical school to work in the areas of global priority. And a very important strategy is to bring together many departments, as I have listed over here. So we have light wave technology is an important tool for us, and we integrate with materials of many different kinds, which are organic, soft material, hard materials, and their composites at nano scale. As Professor Chaudhary said, an important aspect is that can we make them lightweight, can we make them reusable, can we make them multifunctional so that they can do many things at the same time. So those are the materials base. An important aspect of our program, again, is international collaboration. And we have network of collaboration all across. Some person said, you know, you actually look at it that your collaboration extend on all 7 continents, including Antarctica. And you may wonder why Antarctica? Because we are using extremophiles from there and their bacterial machinery to make new kinds of nanomaterials in a very green way. Okay, and so that here you have it, and I'm here to offer collaboration with GSV, whether it is in the areas of, thank you, materials development, or in area of developing your curriculum, educational part, to create a skilled workforce. So, and then we work with industries, We are very heavily engaged in entrepreneurship around the world, even trying to create companies in India. Okay, so our vision is to use convergent science and technology for transportation and aviation. So some of the materials ways can be common for both. When we are talking about lightweight, we are talking about strong materials, we are talking about multifunctionality. They can be a common denominator for both of them. So here we are looking at part is energy harvesting, where we can use green energy. We are involved in not only harvesting, but storage, transport, and management of energy so that we can more efficiently use it. We are also interested in tracking, communication, sensing, and this is where we are using quantum science now to advance that. Materials for structure, protection, energy sensing, hypersonic propulsion, these are more important for aviation, so that's another part. Safety, security, and logistics are important aspect. And then we are also using artificial intelligence. We have a very big program, hundreds of millions of dollars going at our university in AI, where we are using it for automation, intelligence, and robotics. Okay, so and applications again, railway, aviation, and naval seaways. So in a broader sense, transportation. And so over here again, in a space aviation, we are talking about satellites, energy efficiency. Space is a very crowded place, so we want to also have a space awareness. We want to know who are our friends, satellites, who are foes, and then IoT is important. So anyway, some of these aspects we are addressing by development of materials. And so in terms of energy, again, Professor Chaudhary emphasized sustainability. We are fully aware of it and we are totally engaged in that. So for that point of view, we are looking at new ways of harvesting energy for natural resources. And there we are looking at solar cells, thermoelectric. There are other avenues, wind turbines, hydroelectricity, nuclear, but the yellow code is the ones that we are engaged in. The other one is energy storage and conversion, where we are looking at batteries, supercapacitor, and fuel cells, and so on. Energy transmission, we are looking at power electronics, and the other avenue is superconducting cables, but we are engaged in power electronics. All these technologies require new materials, so that's the justification rationale for doing that. And so our approach again is to use our strength in multi-scale modeling combined with machine learning and AI tools to develop new generation materials on a more rational basis rather than ad hoc basis of development. So this shows to you in a schematic of how we are designing, training the machine to understand the structure property relationship, and then, depending on what kind of functionality we want, we design the materials firstly on a computer, then we go and synthesize. An important aspect also is that in harvesting, for example, solar energy, light matter interaction. So there we also are looking at how we can model interaction with light to make it work in certain ways. So that's where we use a response theory in there. Okay, let's move on. So let me give you some scattered example of it, which may appear very scattered, but at least a snapshot of what we are doing. So one of the area is how, again, emphasizing lightweight and processability. Cost is important. So there is a big push for, simple processes of making solar cells. So one of them is solution-based thin film technology. And this is where one of the champions have been perovskite. So perovskite cells, which are made of inorganic lattices. Here we note over here that there are lead, tin, germanium, there are halides, and then it can incorporate in ionic lattice some organic material. So it's again example of inorganic organic hybrid, and that they have shown fairly large efficiency, but important, and we have been engaged in that. But important issues have been reproducibility, and then their environmental stability, hysteresis, you go in one way, come back again, go, it changes. So there we introduce a concept, again, a very simple design of so what are the instability due to? Instability is due to grain boundaries and cracks and others. And very simple example is that if we make organic diamine of certain length, we call organic linkers, and we sap it, those ones into these cracks and grain boundary, they seal it. And when they seal it, then they can form a very stable performance over here, as you can see in red color, with our organic linker, that it is stable, it doesn't degrade, and it has a stability against environment, it has a stability, a reproducibility, there is no hysteresis. Okay, so very simple example of materials modification, bringing again the hybrid nature of material that can do better than individual component. Okay. Now we can use again light matter interaction in another way to enhance the efficiency of solar cell that already we are using, say for example silicon or dye-sensitized solar cell or plastic solar cells, where if you look at any of these, even including silicon, what happens is the silicon absorbs only visible portion over here of a spectrum. The IR photons, which are abundant in night, abundant in space, are not utilized. Okay. The other thing is that by current solar cells. The other thing is that in UV region, if silicon absorbs, a lot of its energy is wasted as heat because it doesn't need that much energy to generate electron-hole pair. So you have wasted heat and have you to worry about heat management. Okay. So what we said, what if we actually use light matter interaction by manipulating it, what we call photon management. So IR light by multi-photon absorption in a medium transforms that into the we call upconversion into the visible region. Now silicon can absorb it. Okay, so that's one process. The other one is what we call quantum cutting. We took very high energy radiation now, UV, and you take one photon and we cut them into two photons. Now each photon can be absorbed by silicon to create electron-hole pair. So you have now twice as many, okay? So that we call it quantum cutting. So we use the physics of optical physics, and then we couple that into materials design, which make it workable. That one is these, where we have world-leading capability. We call these optical nanotransformers. So these are rare earth ions doped into a crystalline lattice. In this case, it is a sodium yttrium fluoride, and these are nanoparticles. So we make nanocrystals of sodium yttrium fluoride doped with rare earth ions, which could be thulium, erbium, or other ions, and they are so small, you can disperse them into a medium like over here, water or organic solvent, very transparent. When you pass IR light, they can absorb these ions, depending on what ion they are. They can absorb 2 of these IR ion, let's say at 980 nanometer, which is invisible, and transform that depending on whether it is what kind of rare earth ion, it can convert that into green or blue or red. Okay, so now we can harvest over a broad range of IR, shifting them to visible, and that can be absorbed so that we can use it for many applications that we have explored, night vision, but solar energy conversion. The other one is quantum cutting. Again, we take the rare earth ion again in nanocrystals dispersed in a transparent matrix, and we can cut that into two. Near IR over here now generates 2 photons in the visible that can be absorbed. So this was physics. We made the materials, we optimized the materials characteristic again using modeling and AI to enhance its efficiency, and then the question may be, well, then we can use another strategy, a nanoscale, nanostructuring. You can make core, shell, and shell all nano sizes, and core converts IR light in one spectral region to one color, one shell converts to another color, third one another, and you can broadly harvest and shift them into visible for solar energy to be affected. So that's what we showed over here, that in the core is erbium, one shell is holmium, third one is thulium. They are all into sodium yttrium fluoride lattice, and then they all absorb in a different part of the spectrum and over here and transform into blue, green, or red. All of them can be absorbed by cell. And here we showed example that actually in sunlight can be converted. So you take sunlight, filter, get IR going, and you can convert that. So it's not into lab simulation. In actual solar cell, you can do that. And then we showed over here that solar cell efficiency is increased by adding this extra add-on layer that can transform and feed into silicon cell or dye-sensitized solar cell. So that's where photonics come in. My title was Materials and Photonics. So that's one example. Okay. Another example of this upconversion that we showed was again in the space awareness, where you're looking at these upconversion nanoparticles which are in IR, right, absorbing, transforming into visible. You can code them. So you code them with certain pattern. You can write QR code, you can write three-dimensional code, and like I'm showing over here, that you can code them, and then when you shine light, you can generate the pattern that can tell you whether it's a pattern of a friendly object or non-friendly object. So security coding can be done by using invisible IR light that generates a visible pattern that you can recognize and read. Okay. Now for a space, you also have a lot of X-rays, right? Or you have high energy ions. And, so one issue is, can we protect against those high energy radiation, X-rays, our object or satellite and others? But on the other hand, wouldn't it be nice if we can take those high energy and shift it to lower energy, not harmful light, and we can use that to again, solar energy conversion, electricity, so on. So the same kind of nano formulation with lattice, but using a different composition. Oh, no. Oh, here, okay. So same nano lattice, if you use a different combination, heavy elements like gadolinium or bismuth, they can harbor X-ray. and then X-ray energy can be funneled down, migrate through the lattice, and then can again create electron-hole pair that can combine to give you visible light. That process is called scintillation. X-ray converting that into visible light. So we are developing nano-sized particles that can be dispersed, and they can harvest X-ray now easily, and we have demonstrated very efficient conversion into visible light by a lot of physics were going on, which I don't have time to go. So nanoscintillators is another kind of materials we are developing that can be useful for lighting, can be useful for converting X-ray into visible, that can be absorbed by silicon to give you solar energy conversion. So that's another area. Now another area we are working on is thermoelectric. You can have a big heat gradient in this space, or even when you are in transportation system, you have heat generation. Can we use that heat to funnel back and generate electricity through thermoelectric? So we are working on materials that are new generation thermoelectric. So what you have to do is thermoelectric, you're looking at heat differential, convert and transform that into voltage. So one part over there is that requirement, without going into physics, is to keep the electrical conduction at the best. But thermal, we need to minimize so that heat doesn't dissipate, the temperature gradient stays. So you want to have those two. Generally, when you take any system where electrical conduction is high, like in metal, thermal conduction is high too, but you want them to go in opposite direction for thermoelectric. So we design systems where, again, a hybrid system that allows you to dissipate thermal conduction minimize, and then electrical conduction maximize. So we design these kinds of systems where you have two-dimensional materials which are atomically thin, so lightweight, and then we in between intercalated organics which actually minimize thermal conduction. Okay, so these kind of hybrid systems, without going to physics, are new generation thermoelectric that we are trying to advance to actually make them work. Okay, let's move on then. So coming back to that, we have advanced our areas of nanomaterials. Why nanomaterials? Because nanoscale architecture allows you to introduce many kind of functionalities. As I already showed you example of core shell structure, core doing one thing, one shell doing another thing, another shell doing another thing. So you can do that. You can also make them, so that's zero-dimensional. You can also make them thin, atomically thin sheets. That's two-dimensional materials. And in two-dimensional materials, we can actually make them very thin, have one, and then you can stack different kinds of 2Ds. So you can make heterostructures, and again, one thin sheet can do one thing, another one can do another one can do, or you can do interlayer interaction to induce new kind of functionality, electrical, optical, and others. So that's the beauty of 2D materials. And again, they're atomically thin, so they're lightweight, so we can use them. So we are working on both nanoparticles, and we are working on 2D materials. There are different kind of 2D materials. One important one is using boron. Boron is a light atom, but it has a very interesting properties. It has very interesting chemistry, and one of them is that their bond can be very, very strong. So For example, if you take a borofene, which is an analog of graphene, as you know, graphene is a very strong material in the layer, mechanically very strong. They have been used for structural materials in composites. But borofene, which is analog of graphene, only boron, is projected to be stronger and lighter than graphene. So we are working on these 2D materials which really show a lot of promises. The other one is hexagonal boron nitride. Third one is metal boron complex called ambenes. And then the other one is mexenes. What is this one? X is here, the carbon. So these are the 2D materials that we are working on. There are other kinds of 2D materials, transition metal, dicarbonized, perovskite I already talked about. So we have a big program in this area. And I want to just give you some example. So one example is our hydrogen energy, where boron nanoparticles, nano size. Another advantage of nano size is that you have large surface to volume. Okay, surface is really big, and in 2D is even bigger. So when you go to nano size, the boron nanoparticle surfaces are very active, and we demonstrated that indeed you can very efficiently generate hydrogen that you can couple with fuel cells to utilize. So this is one example. And one example of making this very simple way, this nanoparticle, is by using laser-assisted processing. So again, we're using tool photonics over there. So in this case, we had a sheet of boron, and we simply use very short pulse lasers to ablate small particles in the solvent. And they come out, depending on the conditions you make it, they can come out 20, 30 nanometer fragments, nanoparticle, very simple way. The other way we have made is whether you use hydroboron and pyrolyze with laser, so boron comes out and they cluster together and make boron nanoparticles. So those are the ways we make it. So we are using sometime dry chemistry, sometime wet chemistry, sometime hybrid. So there are a number of synthetic tools that you can use to make materials as well. All right, so this is one program, multi-million-dollar program that we have running, which specifically addresses application to space. Okay, this is funded by the Air Force Office of Scientific Research, which I lead, and we have partners with other universities. And so here we are looking at, again, 2D materials for space technology, particularly in this case is mexenes, which are doped with lanthanide, rare earth elements. Rare earth element, I already showed to you the photon conversion, up conversion, down conversion. One was one for space. The other one is this doping. We want to use it to see whether we can enhance properties useful in space. One of them is EM shielding. EM shielding is one concern over there. The other one is a protection against ionizing radiation. It's called radiation hardening properties. And so we are trying to use this, again, to manipulate the properties, and we already have shown that these 2D materials mixing doped with rare earth provides better EM shielding and also provides radiation hardening, protection against highly ionizing radiation. So I don't have time to go, but there are other properties, terahertz and other properties, which I'm not going to go. Okay, so again, we are using these different methods where we can, a simple method is to make 3D arrangements of these, max phase they're called, and then you can actually exfoliate layer by layer and make them in two-dimensional mexene. So this is the kind of approach we use. Okay. Now, another kind of material which we are investigating, and that is materials, polymeric systems, soft materials, which have dynamic hydrogen bond. So they can self-heal. So if you scratch them, cut them, or damage them, and you just heat, and they kind of again rearrange and fix it. So that self-healing material make it more reusable platform as a coating. So we are looking at one system that called Vitrimer. Vitrimer that has dynamic bond, and we are mixing it with other kind of components without going to detail. Chiral polymer is an area where we can use chirality control of photonic function, and we can, as I say, automatic self-healing. So we can provide self-healing, like you can see over here. Pointer sometimes doesn't work. All right. So you can scratch over here and you can heal, and we already said that. All right, let's leave it. So anyway, so that's a very useful kind of medium, and again, you can opens up a new possibilities where you can actually make composites, where one component in there gives you one functionality, and then it also has a healing property. Okay, so that's another area we are working on. We are exploring this vaccine for energy storage application, where we demonstrated useful properties and energy storage as a supercapacitor. MBean, which is a boron analog, we are exploring it for energy storage devices. And here again, we have already shown the merits of high electrical conductivity, chemical stability, high surface area, mechanical strength, versatile surface chemistry, where we can have efficient charge-discharge cycles, enhancing capacity to store a long-term performance. So this is a very exciting direction for us. Then we are working on this high entropy. So these are non-equilibrium type materials which are stabilized because of the large entropy gain. And these are the materials, or like carbides and borides. They are materials that are exceptionally hard, high temperature strength. You're talking about thousands of degrees stability, and then have low thermal conductivity. They are radiation tolerant, and we are actually making many of these transition metal carbides and borides using two different processes. One of them is thermal plasma driven aerosol route. In aerosol chemistry, we have developed. The other one is just thermal route that Professor Ganguly, good friend of ours, developed earlier. So we are using these metal borides that are a very useful class of materials. Another direction that we are going now is into quantum. So where we are using in quantum materials, we prepare quantum states of light that can work as a sensor for different kinds of field in space. Magnetic field, for example, is an important aspect. You're looking at thermal, electrical. You can make sensors by preparing especially certain kind of quantum states in a material. So quantum material is a big direction. And the other one is quantum photons. Photon we prepare in a special state so that they can interact in a unique way to give us more advantage in sensitivity and resolution that we are probing. So that's another area we are investing big at UB, at our university. All right, so I want to again emphasize that we are not just making these materials and publishing papers. We are also very much keenly interested in, from invention innovation to inventions, and invention to actually technology transfer, and then making a global alliance partnership to spin off companies and businesses. So one successful example is where we use the concept that originally was an imagination. That one was this fantastic voyage in 1966 of making so there was a diplomat who was kind of injured, and then the scientists, they made this submarine and put there the medical personnel and tools and shrunk it to nano size, so it was a nano submarine, and launched into the body of the diplomat to go to the disease site and fix it and come out. So we in 2002, we made this concept we call nano clinic, a small silica bubble packaged with therapeutic and diagnostic tools, having a targeting group on the surface to recognize disease site and fix it. And then we started a company in Paris. It's called Nanobiotics, and Nanobiotics now is almost a $500 million publicly trading company. So again, as I'm saying, we are very interested in seeing it. And as a matter of fact, we are having a workshop with 7 ICERs, our university, on March 16 and 17 in Trivandrum. And one big forum over there is entrepreneurship and technology transfer. In that meeting, which will be actually inaugurated by Professor Karan Dicker. And then we have a panelist who are industrialists, venture capitalists, and some of the agencies like this, what is the private founded technology, US India Technology Forum agency that support that, and ANRF, their representatives are going to be there. So I think that is a new direction where academic community over here should think of not just develop and publish papers and write thesis, but what could be a broader impact of that. Okay, so anyway, I want to say over here that I would like all of us to be a big dreamer. As Professor Manoj Chaudhary every night is dreaming what he can do and which direction he can expand the bandwidth of transportation. Over here, we need to aim high. We need to make a difference in what we are doing. Okay, and so for that, thinking outside of the box is important. And so advancing the frontier for high societal impact. So we are looking at multidisciplinary integration. Different disciplines have to come together and work. We need to take advantage of rational design provided by AI, ML, and modeling. We need to make a transformative, disruptive advancement, not incremental, small incremental. And we need to have a global vision to work together as one international community. So I think that's what I have to say today. So dhanyavad, thank you.
We can ask some questions, sir. So before our student ask question, I just want to mention some things. I know he was introduced well in the beginning, but I want all of us to just reflect. He talked about dreams. 60 years back, he went to UPenn, one of the top university in the world, and did his PhD. That was a dream, that is aspiring. He's 80 years young, only 80, but you can see not only excellence, but the passion with which he has been working day in, day out all these years. Not only that, while working in US for last 60 years, he always thinks about what can be done for India in India. Therefore, he set up a path-breaking initiative between Buffalo University, that is one of the top 20 or 30 university in computer science, and IITs in 2002, which was highlighted when the President of India, President of US and Prime Minister Modi ji met, and this was highlighted as a joint statement between US and India for a very big partnership between top university in US and IITs in India. And I'm very happy and thrilled. That is why that not only I had a chance to visit him in 2022 in his laboratory, and that is when we set up this IIT and partnership, but I have been following him and requesting him that can we do a similar partnership with GSV and Buffalo University, and for which he has been kind enough to set up many meetings between their School of Management, their School of Engineering, and hopefully we will do. So I want to firstly thank you for such an energy and such top quality work that is happening all over the world by people like you. And then any questions. Thank you, sir.
So now it was his turn to brag about his elder brother. Thank you. Is there any question, any comments? I wanted to, yeah, especially I like from a student. So let me add to that. I grew up in a very small town in the state of Bihar called Sitamarhi, birthplace of Goddess Sita. And when I was born and was still 13 years old, I had no electricity, no running water, but just a dream to do something and be somebody in that kind of environment. So all of you can really think of it that if you set your mind to something, some goals, and you can achieve it. The other thing is that I am also a professor in the School of Medicine, okay? And somebody who never took a course in biology, daring to do research in biodomain, writing 2 books. One book is called Monograph Biophotonics. The other one is called Nanomedicine and Nanobioengineering. Somebody who never took a course, self-taught. So you can train yourself to do anything. Thank you. Very good question.
Namaste, sir. First of all, I am also from Bihar, Bhagalpur, and I wanted to say you and ask you a question that you told about Nanobiotics, a company in France.
Paris, yeah.
Okay, sir. Then in which area the company is working, and if they are selling product or not? I wanted to know.
Very good question. So Nanobiotics is working on nano formulation for targeted treatment of head and neck cancer. Okay, head and neck cancer. So, you know, when you, by the time you file for a patent and go through series of, you know, testing, you know, different levels, you know, and you have, you know, the trials of human trials, there is a lag time of at least 20 years. So right now that company is in the phase 3 clinical trial at a number of hospitals, and so very close to actually being in patient care. So it's not selling any product right now. It's just into clinical trial final stage where it will be submitted to approve. But you can do publicly trading, people invest in that based on its potential already. So that's why the company has grown to become almost $1 billion company.
Okay, sir. Thank you very much.
By the way, I spent 1 year in Bhagalpur, actually 6 or 8 months period where I was a lecturer at TNB College before I jumped to Philadelphia to do PhD. have time?
Any question?
Good morning, sir. Sir, it found great to hear you that you are also from Bihar. I am from Muzaffarpur. So it's make great sense to...
Where are you from?
Sir, Muzaffarpur.
Oh,
Muzaffarpur, Bihar.
Muzaffarpur.
Yes, sir.
So I was at LS College. Go
Yes,
ahead.
sir.
Tell me, yeah.
Sir, so my question is, sir, as you pointed out in your presentation that self-healing properties of nanoparticle. Sir, is it that much fast like what we have seen in movies like Spider-Man?
No, I didn't get your question.
Sir,
Manoj.
like you have pointed out self-healing properties of nanoparticle. Sir, is it that much fast like what we have seen in movies? Means the particle gets distorted and then they fast, matlab, self-healed fastly. Matlab, what is the timing of self-healing property?
The timing of
Self-healing of nanoparticle.
self-healing. Oh, yeah,
Healing,
okay.
healing.
So that one self-healing, it takes, depending on how you heat and on what method, you're talking about 30 minutes to an hour
Okay.
kind of thing. Yeah.
Okay, let's thank him big time. Thank you. Please have a seat. No, it's okay. Please.
Thank you, sir, for your insightful thoughts. Your expertise and global experience have given us much to reflect on. May I request our Honorable Vice Chancellor, sir, to felicitate Shri Raju Prabhakar, DRM of Vadodara. Welcome, sir. We now move forward to our next distinguished speaker, Shri Arup Kumar Malik, who is the Executive Director and Head of HAL Management Academy, the Apex Learning and Development Center of Hindustan Aeronautics Limited. He previously served as a General Manager, Customer Support and Quality Assurance, and brings over 35 years of professional experience across private, public, and technical sectors, including more than 20 years in aerospace and defense with domestic and international marketing exposure. Before joining HAL, he worked in engineering, project management, and international marketing across multiple industries. At HAL, he has handled diverse high-impact roles in research and design, helicopter division, marketing, corporate center, customer service, quality, and flight operational safety. Shri Malik holds a BE in metallurgy, a postgraduate diploma in marketing management, and is a certified project management professional of IPMA Level C. His expertise spans marketing management, project management, and international marketing, underpinned by a strong customer-centric and value-driven philosophy. As HMA head, he leads initiatives to build future-ready leadership, enhance project capabilities, and foster continuous learning aligned with HAL's strategic objectives. Today, he will be delivering his talk on aerospace materials and its indigenization initiatives taken by HAL. Welcome, sir. We are honored to have you with us today.
Uh, Distinguished guest, and thank you for inspirational speech. I am spellbound by your journey and that much dedication, dream, and how to make it fulfill and still think about India. So I think you are truly Atmanirbhar, sir. Hats off to you. Now, it becomes that much challenging for a multi-domain specialist like me to justify this kind of inspirational talk. But anyway, I will try to do justice with respect to our effort of indigenization of material, the drivers, and challenges what we are going through in aerospace and defense sector for the material development aspect. When I talk about material development aspect, it is not just the composition what we develop. It is the sub-processing to get the proper property and the final processing to get shape and its application to fulfill its performance requirement. Next. Sorry. Okay. So if we just go to the requirement of the material required for A&D sector, it is immediately flashing in our mind that variety of spec, shape, size, type, everything is involved in this development process. Now that permission combination becomes very difficult. It is not that particular composition which matters. The matters is the ultimately what you are looking at to fulfill the performance requirement. If we look at the next, if you look at the aircraft and engine, yes, most of us know that the aluminum plays a very important role. The duralumin series of aluminum, nowadays aluminum, silicon, aluminum, copper, and all are newer materials which is carbon. Then composite, Ti6Al4V, the Inconel series of material. So all this having its specific requirement because of the temperature profile it works, that strength of material what is required, the fatigue property, the creep property. So it is a combination of all those requirements to bring and culminate to a product. If you look at civil industry, there are a lot of uses of composite material, and that it is the specifically it is because of the strength to weight ratio, and which every gram of weight saving is that much fuel efficient and that much payload it can carry. So it is whether you talk about civil or military, the drivers are strength to weight ratio and efficient lightweight materials. Now, when we look at the scenario of material development, perennially we have seen that wherever the blocks which is having civil and military industry self-sufficient and an ecosystem exists, there the material is very easily developed. Look at Europe, look at Russian belt, look at China. We not all the informations are readily available. Look at US-Canada belt. So there the civil industry, means civil aviation industry and military aviation industry runs equally. So the scale of economy is very easy for the industrialist to develop proper material and go to the targeted market. But when it comes down to us, it is difficult because in civil aviation industry we still are a consumer. Ecosystem of civil platform is yet to mature in India. Be it transportation sector, be it troop transport or cargo, or we still, HAL being one of the leader in this industry, we are not yet made a big aircraft, say 100-seater. So that's why we are looking for partner like SSJ, a Russian partner, to bring to India. Now, as the civil sector grows, I think days will come down the line, maybe 5 to 10 years, the ecosystem will develop with respect to military and civil, and the material development for the specific sectors will have a huge boost. Now, see, generally the driver for the, just 1 minute. Can I go back? Down? No. पीछे जा रहा है क्या? और पीछे हाँ हाँ ठीक है ये हाँ ठीक है. So, if you look at the drivers for indigenization in India, yes, we always getting choked by the so-called 5 to 8 big material players in any sector. Now, we have to get immune to with respect to that. Otherwise, we'll always depend, and in the crunch moment, we'll not able to deliver to the expectation of our nation. Embargo sanction, we have seen post-Pokhran, what happened. Toray, Japan has choked us with carbon fiber, and necessity is mother of invention. And T300 was developed by NAL, our team. But a very unfortunate scenario, still we are trying. They have developed the material, but it has not yet come to aerospace grade. So, see, application of composite can be in various fields, but it has to finally boils down to come to the aerospace. Then only we will propagate. Otherwise, we have to depend on Hexcel, Cytec, all those French and US companies for our material. So, the essence of this is, as industry, as scientist, as academia, we all together need to focus what best can be done as a one nation towards to achieve our Atmanirbharta goal. Because government is promoting, but it is our responsibility how we have to use this promotion to ultimately go to the end result. In depth, I don't know how many people are about the process, but the promotion of defense acquisition process, they have now made it mandatory. The IC content, indigenization content, should be 60%. It started with 30, today it has reached 60. Now, we may be making 90% of the system as Indian system, but the value addition as per IC calculation in the defense DAP, chapter 2, I think Annex 11 or 14, there is a calculation which may lead to just a opposite scenario where we may land up at 40 to 50%. The major chunk of it is, say, engine, say, IP related materials, which still we are not able to develop in India. So unless we develop that, our IC percentage will get saturated at 50 to 60%. So that's why the focus on semiconductor, that's why the focus on material. It has become so much important that down the line, we need to go to the basic to have that IC, indigenization content, to become self-reliant. That is the essence, really, to become self-reliant. We have a civil sector which may reach pinnacle, I told. Yes, we are into ALHNG, the helicopter what we have developed, and it will be given soon to ONGC. Pawan Hans will be operating it. All the state government is looking at it. There is competition coming from H125 Airbus. Kolar, they have found industry. So yes, ecosystem is developing very fast. So if HAL is having a requirement of 40,000 ton of material, and from the vibrant ecosystem which is prevailing today, another 40 to 50,000 comes, I think this scale of equivalence is viable for the industrialist to look into it. I request maybe here JSW is there to look into these aspects, whether we can really contribute in at least the steel sector. Now, what are the challenges? Yes, any opportunity come with challenges. The challenges is this, that the materials are, yes, exotic, stringent, large number of variety with the less number of quantity, because civil market yet to grow. Infrastructure requirement for a specific metallurgical product is very, very high cost incentive. The process are really, it is not that we, the fraternity of material science and metallurgy, there is a dearth of knowledge in India. No, we have better knowledge. It is the scalability. It is the scalability which matters. And I am surely hopeful with the industry, how it is looking up. And as the ecosystem of A&D sector is going leaps and bounds, the days will not be very far where Kaveri engine will come up, and HAL's HTFE and HTAC engine down the line may be successful, and we will become self-reliant in even producing our own engines, with all, of course, towards which we have taken lot of initiative from the HAL side. I will show few slides. The too much of technicality I will not go, because our great professors are always there to help us out. I will skip through those slides, but the essence of it I will tell, because there is hardly 30 minutes of time for me. So as I told, the infrastructure requirement is very high. If you look at aluminum alloy, melting furnace, DC cast, macro etching, testing, these are normal thing. So aluminum, yes, we are having an ecosystem which is developing. Hopefully down the line, most of the aluminum, other than newer generation material, it will be able to get developed in India. I think our professor from Mumbai, IIT Mumbai, will be dealing in that area. So as I told, there is not only the primary process, the secondary process is also important. Primary production is the casting, then we need to do extrusion to get the particular shape, size, and the metallurgical property. Then the most important thing, when we'll down go to the forging sector, which is the maximum utilization what HAL is doing, the ratio plays a very important role. It starts from 4 and reaches up to 8. So these are the challenges which we have to face in our material development, so satisfy these requirements. When you look at the titanium Ti6Al4V or Ti422, the amount of infrastructure required to produce this material is really high. Same will go by mnemonic alloy when it is coming to the engine related parts. So the manufacturing process itself is very, very infrastructural cost oriented. So again, it boils down to economy of scale. Same, just now I talked about, it is similar to titanium scenario, but further more complicated. Now I come to another area, certification challenges. Please understand, A&D sectors, there is no margin of error. A material failure can cause catastrophic failure, loss of life. In helicopter platforms, you don't have any ejection system. So if it fails, we lose not only pilots, and they are the cream of the society, being trained for years of experience. So when we lose one or two pilots, it is not a loss for that particular family, it is loss for the nation. So that's why the certification agency become that much stringent about each and every aspect of metallurgical testing, certifying, and everything. So robust system is in place. People may feel that too much, but this is order of the day. Nothing can be compromised in this area. Now I come back to a little bit of effort what as a application engineers we did and contribute to the ecosystem of A&D sector. When I talk about A&D sector, it is aerospace and defense. We started our journey in 1990, and the first aluminum alloy get developed through OFAG Nagpur. Currently, the Foundry and Forge, it is F&F, means Foundry and Forge division of HAL, is leading the material development, indigenized material development effort for the structural and equipment area, whereas the Koraput, our Sonabada, Odisha factory, is focusing on engine development materials. We have mastered technology from Russia for the Sukhoi engines and Sukhoi technology, single crystal blade, shape memorialized. So those we have totally indigenized. I will show you few slides, and I will quickly run through our effort in making at least some contribution in development in metallurgical field, in metals and material and composite. So till date, we have 100 different material forms are type certified, Semilac in association with HAL, ADA, Midhani, GTRE, and Yantra India Limited. See, this is not alone HAL effort. It is the together effort of industry, academia, and private players, our partners in development. Today, we don't talk about vendors. It is all our partner, all our risk-sharing partner in any development process. Last 2 to 3 years, we have sizable infusion of our fund in indigenization effort to make material and composite and ecosystem. And a lot of our profit we are pumping in this area, because otherwise it is we are affecting in our deliveries. So it is which is to be done first. So first we have to achieve IC content, and we have to be self-reliant in our metallurgy and material science area, where we can produce raw material for A&D sector. A little bit of contribution of our Foundry and Forge division. We cater to all of our HAL platform. with regard to forging, casting, rubber, brake pads, and SMA means shape memory alloy ferrules. This process is totally indigenized, and we are holding hand for our even the primary risk partners of private players. In critical strategic project also, we have a sizable contribution. You people know that the entire structure of GSLV, PSLV and everything, it is ISRO designed and we produced. And recently HL has diversified for making GSLV, and it will be launching from their own effort. They will search for the market, and maybe one day down the line, maybe by 10 years, we'll be able to, with ISRO's guidance, we'll be able to launch our produced GSLVs, for which already we have aerospace division totally catering for this. We have selected, created a R&D center for that this year. We already deliver the forging, casting and brake pads for those areas of other fields other than our own platform. We have also, Foundry at Forge is contributing forging and casting towards BrahMos missile, Akash. Incidentally, BrahMos missile is get integrated to Sukhoi by HL and DMRL. If you look at when we can give for this civil engines and global civil engines, ring forging and investment casting, and today our Foundry Forge 200 crore sales comes out of export. It is a doable thing. Only thing the ecosystem has to develop. If Foundry and Forge can do, any other fellows also can do. So yes, we have also done this shape memory alloy with the combination designers by ADA and HL. Product development was BARC and HL. Then again production was HL, Foundry and Forge, testing BARC, NAL, GTRE. You look at this entire chain, it is not alone. So here the main crux is together. Together we have to develop the material so that we sustain. It's nobody can do alone. Here, okay, we are currently the industry leader. So yes, it is our responsibility to handhold and produce. But with the vibrant ecosystem in space, who knows, already Tata is into there, Mahindra is there, Tata is there, Adani is coming into picture. So there may be HL like 3-4 ecosystem available, and today in future down the line 10 years, maybe 80 to 90% of the material will come out of India. Shape memory alloys, this ferrule, most of the LCA ferrules, we use this shape memory alloys totally developed by us. Material was developed by Midhani. For GTRE, we have steel, titanium, nickel. It is we have developed through Midhani and delivered 107 parts and 25 parts under development through GTRE. It is our ecosystem responsibility to make that Kaveri engine succeed. Hopefully it will get uploaded to LCA soon, and we will at least fly our Kaveri engine and make it airworthy. And then rest of the thing always evolution can take place. I think yesterday there was a saffron collaboration also is happening with GTRE. Macron was there. This is our small contribution. So 6 of the titanium alloys mills we have developed along with the industry partner, 10 nickel alloys and 20 steel alloys, but long way to go. It is just an initiation. HL along with NAL, we have a dream that someday I think we will able to make aerospace grade composite. T300 technology is available with NAL, but the requirement is not only T300, it is for T600, T700 and high temperature composite also. All the combat aircraft in a regime will go to the intermediate fiber zone, carbon fiber zone, where the high temperature property, composite property is required. So when Russian university can do that, when China claims China can do that, and why only Hexel and CPET will be doing it? Toray Japan can do it, why not India? See, if you look at the consumption, these slides we will see at that already we are consuming 4,000 ton, and next 5 years the projection is sorry, it is around 4,000 ton. It is going to another 5,000 ton. So already we have consumed 10,000 ton. So, and with the ecosystem, vibrating ecosystem, it will become maybe another 50,000 will get added. So that's what I am telling, that maybe scale of economy we will achieve down the line, so to produce our own material. These are the things already we have developed through Midhani, Tempen, and all other industry partners. And there are, our current plan exists for so many lines to be produced and indigenized raw material. So conscious focus is there. This is for the engine areas. Forging and stock, ingot indigenization already happened. Hindalco, Century Extrusion, Sunflag Steel, Starware. So Sunflag is a good competitor for Midhani and they are doing well. So the full support is there for HAL to all, Midhani, Sunflag, or whoever. It is for the nation we need to work. So if you look at this slide, that we are under indigenization is around 14%, titanium is 11%, steel is 13%, and nickel is around 18%. So slowly we are moving forward. These are the things. Mainly we are dependent. So this is the scope which is available for the industry. These are still getting imported. If you look at this slide, see steel, already Midhani, Sunflag, Starware, Sarolaha, Aluminium, Yantra, Hindalco, Century, Nickel, Midhani, Titanium, Midhani, and PTC is moving forward to do it. If you look at this, you see before it was, import was that blue and indigenization is red, and now you see after 5 years of effort, so maybe we will make it the blue zero. That is the goal. Sorry. These are the major contributor in material development ecosystem in last 5 years. So yes, as Government of India is consciously promoting this Atmanirbharta in material, and I am seeing a positive attitude from even GSB to focus on material science. Yes, as together, as I am always tell, this is the ecosystem which need to deliver, not a single company or single industry. It is impossible. So there are certain exemptions available, so which we need to, there is a positive indigenization list which is promoted to restrict import. So we are forced to indigenize. So that kind of environment is there, and whatever is available for any people to make it indigenized, that is there in the Srijan portal. Make one, make two process is in place. So where our industry is willing to partner with the long-term commitment to some kind of development activity. Time-bound monitoring of this positive indigenization list is also one of the drivers. So this is what I told, that another 50,000 metric ton will be required. So these slides I will just go through. The report says still we are in aluminum itself, still 50% is we are importing. Titanium, it's huge, almost 80% is getting imported. Steel alloys, here there is lot of chance. We should able to focus and indigenize. Nickel base challenges is there, but Midhani is doing some good job. So to Sunflag. These are the HL platform which is available currently, which will drive the requirement. Similarly, the vibrant ecosystem, Mahindra, Tata, Adani, and others players who are coming into the market will also boost the requirement. So now lot of our Indian mill started exporting. So in that case, when we have sufficient capacity to export, why can't we just improve the range? Focus little bit on improving the range so that more and more material get indigenized. So if you look at the last line, so many OEMs, even Foundry and Forge, we are selling 200 crores of material every year. This is the toughest area, and all stringent and composition wise, metallurgical property wise, all are there. But here also efforts, conscious efforts are there from our Koraput division to get, these are the design drivers. I will not talk much of about it. I will skip through. So yes, efforts are there. Already we have done 27 lines of casting, 19 lines have completed. So these, we have a specific timeline to improve upon our indigenization effort, and it has been monitored in the highest level in the company as also in the Ministry of Defense. So basically, see, this is driven by the specific strength, temperature and material property, where we should use what material. That is purely the designer prerogative of a metallurgist. So if you look at the hot metallurgical zone, this is the zone where we are not able to penetrate yet. The hot metallurgical zone, till date, whatever engine is coming, whatever TOT is happening, they will not provide the IP of this. So this needs development, the red zone. There only the Inconel, wasp alloy and those things. The process we have mastered, means the secondary process, but the manufacturing is still a question. Magnesium alloy, yes, in certain cases, the AGB's auxiliary gearbox and gearbox, this magnesium alloy, we are able to do it. Foundry and Forge, we do casting, and this the pattern and the gate making is a big challenge. The magnesium alloys are very much inflammable, so it likes like a flower pot. That kind of impression it gives when it is poured, or if we are not, and it cannot be, if you sprinkle water, it will increase the propagation of lot of fire hazard is there. There are 1 or 2 incidents in our Foundry and Forge division also. So it has to be handled with care. Titanium alloy, yes, whatever specification is coming, we are able to do the processing aspect of it. Material wise, only Midhani is able to do it. There is a metal matrix composite which is coming into picture in some of the high temperature zone of our engine development area, which is still imported. Hot section, as I told, hot metallurgical zone, it is still a gray area for us. Now, let us talk about the indigenization area where we have done some kind of success. Depending on the Koraput success of Sukhoi based engine which we produce, there the metallurgy we have now ventured with, with the help of DMRL, we are able to do LPT for Adur 871 engine single crystal. If you look at the single crystal technology wise, I will not go in detail. It is basically a directional solidification and preferred area. We able to make the seed. Currently we are able to make the seed through which with the we are able to even single crystal, that process we have mastered. The nickel we are able to make. Only the tungsten is a gray area here. That is the seed which we make, and then we create the single crystal structure. The blade is created out of this single crystal structure. So the process of manufacturing a seed, we have blade casting done at HAL Koraput, pure nickel indigenized, pure tungsten still being imported. The alloy is also imported, but we have taken initiative with Midhani to realize it. So this will be realizable. So we will be only depending on the tungsten. These are the few new generation alloy which is coming into the area of engine application. Still we are not able to master it. DMRL is working on it. This we have mastered. Midhani has already done it. We are able to make this alloy. This is again a new generation alloy we are not able to produce yet. So these are the area where industry and academia can work together to make indigenized material. Ceramic matrix composite, yes, as I told that we are able to master the technology of processing, but not the material. The new generation engine LEAP, if we look at, again that I told, the thrust to weight ratio, thermal capability, durability and architectural shift, more lighter, fuel efficient engine is coming up, throwing more and more challenge to material engineers. Shape memory alloy, as I told, yes, we have done, and there are sizable rings we have made to use as a ferrule technology in our LCA. Magnesium casting, as I told, it is used in our helicopters. AMAGB auxiliary, this one, the main thing is those intricate shapes, pattern design and this. So these are, we have mastered in this, and we are able to produce the process, but again the alloy is still coming from abroad. These are the few effort HL Foundry and Forge has done and developed through the ecosystem. This is the development done through ecosystem. So previous slide was about Foundry and Forge, and this is through the ecosystem. We have also developed the brake pads, which is a powder metallurgical product. If you look at the non-metallic, I think NAL will be a better position. As I told clearly, that T300, they have the technology. They tried once along with the industry partner, very unfortunate, got a wind up. Then HL is willing to even invest. So talks are on. Hopefully, I think we will be able to produce at least T300, maybe in future T600 and 700 series will come into picture. So these are the initiatives, CSIR and NAL. Yes, T300 we have done, but in the lab level, not yet productionized. So presently Hexcel, USA, as I told, Huntsman and this, the entire integral thing of composite is coming from abroad. But please understand, sources are possible. These are the sources, ecosystem which are available and we have tried, they are willing to do. So we may have to tie up as a ecosystem to handhold them and then come out with the aerospace grade composite. Oh, sorry, I'm going. And finally, to the industry, this is the way we, being a government organization but listed, we follow the structure, a typical case. We release a RFQ, then these are the process. We do technical evaluation, sometime QCBC, then documents are followed, ORDA. This is the way typical material test COC, the certificate, test certificate, what we get, and then mechanical property, NDT, all those things is tested. Then based on that, we produce the material. So whatever we have done together is the last line. Together we can and together we will. So with that, I think I am able to do little justice to my subject, though I am a metallurgist, but I am very, very thankful to Gati Shakti to bring me back to and study again in metallurgical field, and I put a lot of effort to make this because bits and pieces here and there. If with great professors are in front of me, so if I have gone somewhere wrong, please excuse me. Now I am open to any question. I think I have overshoot my time, but if you anybody anything, I will try to answer. So metal, again, the material, sir,
Hello.
I think the best
Hello.
person who can tell is NAL. See, we are application engineers in HL. If we have mastered in the process like layup, vacuum assisted resin transfer molding, or the layup process. But the material, the resin, India can develop. Carbon fiber, India can develop. They have developed. It is not yet fully certified for mass production for aerospace grade. Whereas metal composite, we are using in aircraft division, we are using the metal composite. We are users. But the material is coming from abroad. Still, I am telling now we are at 50 to 60% of indigenization level. The goal is 75, and 60 to 75% is not easy. As you reach higher and higher, any 0.1 incremental improvement is hell lot of effort.
Namaste, sir. What do you think of nanotechnology integration in
Correct.
the field of
Correct.
aviation?
It is of huge, huge importance. I was watching sir's presentation and he was talking about 2D nanotechnology. So there are areas where coating, boron hexaferrite, stealth coating is possible with nanomaterials. I remember in one of my project, I was with IIT Roorkee. They have developed at that point of time some boron hexaferrite coating nanoparticles, which is radar absorbing RAM, radar absorbing paint application. It was tested in lab level. They able to produce, and our Jaisalmer, I think there is a lab which can test the RC, the radar cross section area, which was done in it was found satisfactory. But the very unfortunate thing is somebody should be there. We are again, I am telling, HL is a application engineer, there is industry, academia. There is somebody who should take the responsibility to match, to make it produce. This happens in Russia. I was involved in a lot of Russian project. Russia, the university makes the basic research and government takes over. It is their responsibility to put this technology by whom. If you look at their system, it is United Aircraft. All the aircraft, United Aircraft. All United, conglomeration. United Engine Corporation, they have conglomeration, but their supplier base is basically 4-5 mills or 4-5 specific vendors. 1 or 2 composite manufacturer supplying to everything. So scale of economy is achieved. And the entire design and material development happens in university, academia.
Okay, sir. Thank you very much.
Yeah, very important point you made. I think what I have noticed, my interaction over here coming, which I'm trying to promote, is really a stronger coupling between academia and industry. You know, as you said, they develop the materials, do fundamental studies, but there has to be a pathway somehow to translate that. So I think that's one area that needs to be strengthened here.
Yes. So before thanking Dr. Arup Malik ji, I must definitely.
I am not doctorate yet.
Yeah, I must definitely say that he was gracious enough to host us at HAL Management Academy. We have already defined the contours of our partnership between GSV and HAL, and
It's
which
a
is
matter
like
of time.
yeah,
Just a matter of time.
just a matter of time, and it will be formally announced. So many things we will do together in aviation sector, in material sector, and so on. I really want to thank you for coming, and a strong partnership. As you wrote, together we can, together we will. So GSV will be a trusted partner to
Thank you,
HAL.
sir. Thank you.
Thank you, sir, for sharing your valuable industry perspectives. We now move forward to our next distinguished speaker, Mr. Ranit Rana, who is graduated in Metallurgical Engineering from IIEST Shibpur and holds a PGDM from SP Jain Institute of Management and Research, Mumbai. He began his career with Tata Steel from 1997 to 2007, working across operations, technology, and sales and marketing, and later headed marketing at Martin Limited, implementing a corporate branding globally. For the past 14 years, he has been with Jindal Stainless Limited, popularly known as JSL, as Associate Vice President, Head Mobility and Managing Business Development for Automotive, Railways and Transportation. He serves as a co-chairman of the Railways Committee like PhD CCI and ASSOCHAM, and is a committee member of Urban Development and Real Estate FICCI. Mr. Rana is also visiting faculty at premier institutes like IIT BHU, IIT Kharagpur, IIT Roorkee, NIT Trichy, Surathkal, and Rourkela. An avid traveler, trekker, reader, and sports enthusiast, he has represented Bengal in the Vijay Merchant Trophy National Cricket Tournament. Today, he will be delivering his talk on lightweight and corrosion resistance mobility solution. Welcome, sir. We are honored to have you with us today.
Good morning, students. Good morning, faculties, and good morning to all the distinguished speakers. It's always, energizing to be amongst the student community. And today, it's also very inspirational to be amongst this august gathering of eminent personalities. It was fascinating to hear Professor Prasad and Professor Malik. And, I was very much taken by what Professor Chaudhary's vision and perspective on material science and his vision of, institutionalizing a material science department at GSV and also having a very relevant course on the optimum materials for transportation. I would just like to inform you, sir, that 6 years back, it's from 2017, we've instituted such program on stainless steel because I happen to be from Jindal Stainless at various IITs and NITs, and it has been appreciated by all the students and the faculty. So we would definitely like to work with GSP to have a program along similar lines.
We already have.
You already have this? It's a 3-credit course?
Yeah, Jindal is already teaching.
Oh, that's wonderful. That's wonderful. So coming back to my presentation, what I'm going to do in my in the time that I've been provided is to look at the various challenges that the transportation segment faces, and then what's the optimum material which could mitigate and address those issues. So if you look at the transportation segment, and as Professor Chaudhary had rightly mentioned, there are 3 key challenges. One, having a material which would enable, a protracted life of the vehicles, which will enable longevity. Second is, how do we make the vehicles, lightweight, because it has a direct bearing on fuel emissions, on carbon dioxide emissions. And thirdly, how do we make it a sustainable solution? If you look at the first issue, corrosion. Corrosion is not only a challenge in India, but it's a global, a global disease. And if you look at this slide, almost the annual cost of corrosion globally, it comes to about $2.5 million US. And it comprises about 3 to 4% of the global GDP. If we look at India, India loses about 5 to 7% of its GDP annually because of corrosion. And particularly in the automotive segment, it loses about 2 lakh crores of rupees annually. And this is not surprising because if you look at this corrosion hut, almost we have a huge, coastline. It's amongst the largest in the world, and around 90 to 95% of the country falls within the corrosive zones. This is a picture, which I had personally taken from Bangalore. So this is at the Kengadi workshop of Karnataka State Road Transport, and this is what happens to GI tubes, galvanized tubes, after 4 to 5 years of operation. You would know, of course, that Bangalore is a landlocked country. So what I want to emphasize on is that it's not only the geographical location in terms of how close or how near it is to the coast, but even the groundwater quality makes a substantial difference, to the corrosion problem that is faced in particular regions. The second most important problem is today the world is facing an existential threat because of global warming. And you would have read that even a 1.5 degrees increase in the temperature, can have a catastrophic effect. And just to give you this, update you, the last year, the global warming has been 1.6 degrees centigrade. And if you look at the graph below, it basically establishes the correlation between increase in temperature along with carbon dioxide emissions. So this is a point which needs to be noted. And as you are all aware, India has taken a very bold step of announcing that it would become a net zero carbon emitter by 2070. But there are countries like US, Japan, and China who have taken a pledge to become net zero by 2050. And of course, if you look at the contribution of various segments to the carbon dioxide emissions, transportation forms, it contributes about 30% of the global emissions. And even amongst the transportation segment, 80% of the carbon dioxide emissions is brought by, the commercial vehicles and the freight. Rail constitutes about 2% of the carbon dioxide emissions. And I always share this slide because railways is a segment which is very close to my heart. And I believe, when I look at the various governmental organizations, it is the railways, which have taken a very a steep target of becoming a net zero carbon emitter by 2030. So this is indeed a very, a laudable step by Indian Railways. Now, this slide basically focuses on what would be the material of transportation, the optimum material of transportation today and in the future. And this is a slide which was developed by Grant Thornton, and they did a study which says that the material must focus on three aspects. One, safety, savings, and sustainability. So when we look at a safe material, it should be crash resistant, it should be fire resistant, and it should have a combination of strength, ductility, toughness, and fatigue properties. When we look at the savings, it's primarily the material must be a high strength material such that it would enable lightweighting of the vehicles, and it should also be corrosion resistant. Therefore, the repair and the maintenance cost should become nil. And finally, sustainable. It should be a green and a sustainable material. So what are some of the materials? And of course, you know that today a lot of carbon steel are being used, a lot of aluminum is used. But let me tell you, we've done a detailed analysis, and stainless steel, we feel, is the optimum material going forward, which could be used for the transportation segment. And I would also like to inform you that if you look at the growth of various metals in the last 20 years, stainless steel has been growing at a CAGR of 5.3%, 5.5%, whereas if you look at copper, aluminium, zinc, they have been growing at a rate of 2 to 3%. So stainless steel is finding a lot of demand amongst this segment. And therefore, now one of the critical elements of stainless steel, or the uniqueness of stainless steel vis-a-vis other materials, is self-passivating characteristics. This I would like to highlight upon because you would know that the base stainless steel grade, it costs 3 to 4 times as compared to a carbon steel. But yet, why stainless steel is being, is finding so much of traction among automotive manufacturers? The only reason is that, it has this self-passivating characteristic which provides the longevity. But so by self-passivating, the chromium in stainless steel, it reacts with the oxygen in the environment to form chromium oxide layer. And it's the chromium oxide that imparts the major corrosion resistance properties to stainless steel. Of course, there are other elements like nitrogen, like molybdenum, but it's primarily the chromium which determines the corrosion resistance. And that is what distinguishes it from a galvanized material which has a layer of zinc on carbon steel or a painted carbon steel. In fact, there is a property called flaking. There's a characteristic called flaking, which is basically when you form this galvanized material, when you weld it, when you bend it, there are certain micropores from which the zinc coating, gets peeled off. And it is from these pores that corrosion starts. And once the corrosion starts, it becomes extremely difficult, to contain that. And therefore, we also did a salt spray test result. Very recently we did it. We tried to understand what's the salt spray characteristic of a 80 GSM GI or a 120 GSM GI vis-a-vis, a bare stainless steel. So just to tell you, we did an ASTM B117 studies, and 80 GSM galvanized material, it gave a salt spray test of 96 hours, and 120 GSM GI gave a salt spray test of 192 hours. Compared that with, a stainless steel grade having 0.5% of molybdenum and about 13% chromium, it's a SS415 grade. 440 hours have passed and it's still running. So this just basically, I'm giving this data just to highlight the difference in the corrosion resistance characteristics of a galvanized and a stainless steel. Now, what contributes to this stainless property is, and this is very important, we need to have a minimum level of 10.5% of chromium. Because if you look at the graph, so at 10.5% chromium, there is a substantial rise in the corrosion resistance property. So any alloy which has at least 10.5% of chromium, only those could be termed as stainless steel. Now, what are the various possibilities? And here what I'm going to do is I'm going to share with you the developments that have happened in India and, and how it has mitigated the issues of lightweighting, how it has mitigated the carbon dioxide savings. So this I'm going to focus on. So if you look at the application of stainless steel or the usage of stainless steel in the transportation segment, both in India as well as what's happening in the Western countries or the developed economies. So on the left, you would see that almost 15% of stainless steel goes into the ART segment. So by ART, we mean the automotive, railways, and transportation. So this is what's happening globally. In India, it's about 4 to 5%. So there is a huge possibility of implementing stainless steel in the transportation segment today. And this is one of the key focus areas of Jindal Stainless as well. Coming to railways, you must have all heard about the Vande Bharat trains. And let me tell you, today the Vande Bharat trains are completely made out of austenity grade of stainless steel. It's a high strength stainless steel, a much more corrosion resistant material as compared to ferritics, which are currently being used in LHB coaches. And therefore, there is a potential of a weight reduction of close to 5 metric ton. But let me tell you, actually, there are certain components which the private manufacturers like Titagar or TMH Russia, they are still retained in carbon steel. But other than that, when they have converted the other components in stainless steel, they have got a weight reduction of 2 to 3 metric ton. And this basically gives us an analysis, a breakup of how we can achieve this 5 metric ton savings. So apart from the underframes and bogie frames, now underframes is another component which railways, very recently, they have come out with a tender of converting the underframes as well into stainless steel. But other than that, if you look at the various other components, I've basically given you what is the existing material and what's the proposed stainless steel grade. I will not go into the details, but the potential of weight reduction is close to 4 to 5 metric ton per coach. Now, apart from Vande Bharat, Indian Railways today is the largest adopter of stainless steel. Today, all trains, whether it is the long distance or the short distance, whether it's the EMU, the passenger trains, the LHB coaches, Rajdhanis, Durontos, they are all made out of stainless steel. Even the wagons, all freight wagons. So by freight, I mean the wagons which are carrying coal and iron ore, they are all made out of stainless steel. The components, whether it's the modular toilets, it's the floor, or the battery boxes, the water tanks, they are all in stainless steel. And this is a very recent development which we have had. In fact, we did a lot of analysis. We visited a lot of workshops, carriage repair workshops across the country. And we highlighted that, the cotton steel underframes, today they experience severe corrosion within 2 to 3 years of installation. And if we convert that from cotton steel into a stainless steel, corrosion-resistant stainless steel, an austenitic stainless steel called SS201LN, it would provide an almost corrosion-free life of 35 years. And let me tell you, Indian Railways had taken heed to this suggestion. They had developed 100 coaches with SS201LN underframes, and they had put them on track in 2020. Till now, 6 years have passed, and there is a confidential report which states that till now, these stainless steel underframes haven't yet experienced any kind of corrosion. And it's because of that, MRVC, Mumbai Rail Vikas Corporation, very recently they have come out with a tender for almost 3,000, local trains. This is how the local trains in Mumbai is going to look like. And if you look at the tender specification, they have specified austenitic stainless steel for the underframes as well. This is another area, there's another initiative which we are working with railways, the bogie frames. Now, if you look at the bogie frames for coaches, these are all fabricated, and this is the condition, this is the corrosion which happens after 4 to 5 years. Now, what the carriage repair workshops have told us is 4 to 5 years, almost 50% of bogie frames get replaced because of corrosion. And after 9 to 10 years, 100% of them get replaced. So we are working with railways to convert these bogie frames into stainless steel as well. And just to give you an brief idea about the grades that we have proposed is this SS201LN, which we had already seen success in the underframes, and a lean duplex grade. We will discuss that later on. But it's a lean duplex. This is a study which we had utilized. It's a study which was done by International Aluminium Institute, and it was supported by the European Aluminium and the Energy of and the Institute of Energy Heidelberg also, where they have looked at various forms of transportation modes, and they have determined empirically determined what could be the carbon dioxide savings with the distance traversed, with the years of operation, and the weight reduction that could be achieved. So if you look at the passenger trains, the rolling stock, I would say, for India, what they have mentioned, what they have found out is the lifetime carbon dioxide savings for long distance trains, it comes to about 180 tons for every 1 metric ton of weight reduction. Now, we have utilized a very simple calculation. So if we are able to get 5 metric ton of weight reduction, we have already achieved 2 metric ton of weight reduction. If you are able to convert these underframes, which are now happening, and the bogie frames will be able to achieve another an additional 2 metric ton weight reduction. So per coach, the lifetime cost, the carbon dioxide savings would be about 900 tons. And if you look at the production plan of Indian Railways, on an average, they produce 9,000 numbers of coaches. This year, in the coming year, they have increased it to 10,000 coaches. But even if you consider the average of 9,000 coaches per annum, the total carbon dioxide savings over the caudal life of 35 years comes to about 8.1 million tons. And if you convert that on an annual basis, it comes to about 2.3 lakh tons. Second, Indian Railways, they are also going to come out with a new scheme, a new policy of new generation of wagons. And if you look at the specs, if you look at the unique parameters of this policy is, they have asked for lightweighting of the wagons. And again, here also we've proposed high strength and corrosion resistant stainless steel. For example, currently, if you look at the wagons, they're using a ferritic stainless steel called IRSM 44. Now that has an yield strength of 350 megapascal minimum. The grades that we have proposed or that we are working with various wagon manufacturers as well as with RDSO is a grade called SS415. It's a martensitic stainless steel with a substantially higher yield strength of 620 megapascal. And we've also looked at a lean duplex, that is 2101, which has also got a higher strength and a very high corrosion resistance. Now, why lean duplex? Because very recently, China, they have developed these coal wagons in this particular grade, and they have been operating since December 2024. So this is a grade which we would also like to introduce in the Indian Railway segment as well. So when this is the chemical composition, which basically states that these two grades have substantially higher corrosion resistance as compared to the currently used, the ferritic stainless steel. However, when we did the weight reduction calculations, we can see that there is a weight reduction possibility of about 2 to 2.5 tons, per wagon across all the various types of wagons. And when we look at again the current production volume of wagons multiplied by the carbon dioxide savings because of weight reduction, it comes to about 5 lakh tons for the wagons on an annual basis. This is a study which was done by Ernst and Young, and they had looked at a wagon made out of stainless steel vis-a-vis a wagon made out of aluminium. They have analyzed the various types of life cycle cost savings that could be obtained over a period of 35 years, and also what is the carbon dioxide emissions or the carbon dioxide savings. And as you could see, the carbon dioxide savings with a stainless steel wagon is almost about 4,500 tons more as compared to a wagon made out of aluminium. Now, it's not only in railways that have made headways, that stainless steel is being utilized on a large scale. Today, if you look at the transportation segment, and there's a new segment which we are developing, Jindal Stainless, containers is another area where we are seeing significant demand coming up for stainless steel. Not only containers, today we have developed tipper trailers also with stainless steel, and the primary motives why people are going ahead with stainless steel is because of lightweighting and corrosion resistance, so that the repair and maintenance cost could be nullified. So CJ Darsal, it is one of the largest logistics providers in northern India, maybe across the country. It's a joint venture between Darsal, Delhi Assam Roadways of India, and a Korean company, CJ. Now, they were the first to develop 50 numbers of containers in stainless steel, and they had put them on tracks in August 2024. They had got a weight reduction of close to about 500 kgs, and even today, they are extremely happy, extremely satisfied with the performance. And that's the reason why today they have also developed the sidewall trailers in stainless steel. So 90 numbers of sidewall trailers have been developed in stainless steel, and the grades that they have used is a combination of austenitic and SS415. There's a martensitic grade, and till now it's been 3 to 4 months. These are running absolutely fine. And if you look at the weight reduction that we could achieve, over the various categories of these sidewall trailers, it varies from 950 kg to 1300 kg per sidewall trailer. Secondly, the tip trailer. So this is, again in stainless steel, and this is how it looks, after painting. So again, here we had utilized a JT grade of stainless steel. We call it JT. It is also included in BIS 6911 as N7. So it's a high strength austenitic stainless steel. So we are seeing a lot of traction of this particular grade of stainless steel, not only in in tip trailers or in sidewall trailers, but in buses as well. So this is how it looks. This was before the painting operation, and the weight reduction obtained was, they had initially converted the shell where they obtained a weight reduction of 400 kg, and now they are looking at the underframe components and the structural components as well. So in containers, Agarwal Packers and Movers, they were the second to come in line. To adopt stainless steel. And in fact, today 60 to 70 containers, and these are all photographs of actual vehicles in stainless steel. 60 to 70 vehicles of Agarwal Packers and Movers, they are already on road made out of stainless steel, and they have plans to convert their entire fleet in stainless steel over the next 2 to 3 years. And if you look at the weight reduction which has been possible, it's again about 1 metric ton per container. So it's not only Agarwal Packers and Movers. Next to come on board was TCI, as the Transport Corporation of India. Initially, they developed one prototype, which we had fabricated for them. And now they have given us orders for 72 to 3 years, complete corrosion. And thereafter, there's a comparison. So after, 5 to 6 years, if you look at the photographs on the right, there is absolutely no corrosion. And today, the entire region is converting from carbon steel to stainless steel. And so this is how a stainless steel, a salt trailer looks like. And even if you look at the weight reduction, so here we have used a combination of austenitics, 304 and JT. And the weight reduction which we have attained is about 1.2 tons per trailer. So this is, okay, I'll just skip it. Now, this is, I am sure this is a very, very recent development. It happened about 2 or 3 weeks back, and I'm sure all of you would have come across the tweet of Sri Ashwini Vaishnavji. So we have worked with Indian Railways to convert the salt container, or to develop. I think this is the first time in the country we have developed the salt containers in stainless steel for Indian Railways. And this was fabricated by Kalyani Castek in Haryana. So again, this is a combination of SS304 and a 200 series grade. And this is how it looks like. It has been, it is operating in the Gandhidham region. And so the reasons why Indian Railways are now looking at containerization of salt movement is because, one, it's a low cost, it's a substantially low cost option. Then it's a hygienic transportation of salt. And finally, it would require lower maintenance, and it's a higher there's a shorter turnaround time. So this is the reason why they have now containerized the salt movement. It's not only salt now. If you look at the rail containers, the 20 feet, the 40 feet. So this is a company called Western Carriers who have developed these rail containers in stainless steel as well. And as we speak, there are fabrication going on, where the entire container will be converted into stainless steel, and which will give them a weight reduction of almost 1.2 to 2 tons per container. So these are, a foldable container developed in stainless steel. I'll just skip this. So fly ash containers, and this could be utilized for carrying cement as well. So these are now also being developed in SS415 grade. Just to show you some of the images. And again, when we looked at the carbon dioxide savings, and again, we had utilized the particular study, which mentions that the carbon dioxide savings for heavy and medium duty trucks is about 28 tons for every 1 metric ton of weight reduction. Again, multiplying the weight, if you are able to, since we are able to achieve a weight reduction of 1 ton per truck, and if you look at the production volume of M&H, medium and heavy commercial vehicles is about 3.88 lakhs per annum. So there is a potential carbon dioxide savings of almost 11 lakh tons per annum. Buses, and this is the last segment that I'm talking about. So this is a new segment which we have opened up, and we are now working with all the major OEMs in commercialization. They have already developed prototypes, and they are now in the stages of commercialization. So the weight reduction which they have been able to achieve is about 25%. And of course, the corrosion, because of the higher corrosion resistance, the repair and maintenance cost will be almost nil, over the life of 12 to 15 years. So while it's a new concept in India, but globally, it has started much earlier. And if you look at all the global bus manufacturers in US and UK, they are already utilizing stainless steel for fabrication of the buses. So this is, Optare is a company which was taken over by Ashok Leyland. And again, they have gone in for a ferritic stainless steel, and therefore they had to paint it. Similarly, Scania, Volvo, Solaris, they are all utilizing stainless steel. Even in India, JBM, Eka Mobility, Tata Motors, Ashok Leyland, Volvo, Eicher, they have completed the, the prototype stages. I wanted to show you the photographs as well, but since we are bound by confidentiality agreements, I am not able to, share the photographs, but they have all achieved, a weight reduction of about 900 kg, which comes to about 21%. Some photographs, I'm just showing of how a stainless steel bus looks like. So this is how, it looks like during the fabrication stages. So again, the grade of stainless steel which we have utilized is a JT, which is again N7 as per BIS 6911. And if you look at the tubular structures, the yield strength is 700 megapascal minimum, which when you compare with galvanized tube, GI tubes, or other grades of stainless steel, it's far superior in strength. And it is because of this characteristic that they have been able to reduce the weight of the structures by 25%. And let me also tell you, very recently, we have now received inquiries from Canada. There's a bus manufacturer in Canada which has now come to us, approached us for supply of this particular grade of stainless steel for fabrication of buses there. So the word is spreading, and if you look at the carbon dioxide savings, so we had categorized, there are two types of buses. One is, the buses which run within the city, and the buses which connects, two cities, intercities. So if you look at the intra-city movement, the weight reduction is about, sorry. Yeah, the weight reduction is about 40 tons. The carbon dioxide savings is about 40 tons for every 1 metric ton of weight reduction. And again, and since we have got about 500 kg reduction for the intra-city buses and multiplied by the production volume per annum, it gives us a savings of about 0.8 lakhs of carbon dioxide, 0.8 lakh tons of carbon dioxide per annum. When we look at the intercity coaches, the carbon dioxide savings are higher. It's about 70 tons for every 1 metric ton of weight reduction. And again, multiplied by the production volume and the weight reduction which we have obtained, it comes to about 1.5 lakhs tons per annum. So in the bus segment, we are able to save about 2.3 to 2.4 lakh tons of carbon dioxide per annum. Now, when we look at the carbon dioxide savings in the transportation segment, I would say the ART segment, so about 2.4 million tons is the carbon dioxide savings if we convert the diesel buses in stainless steel. 10 million tons is the carbon dioxide savings if you are able to convert the commercial vehicles like the containers, the sidewall trailers in stainless steel. And when we look at the rolling stock for Indian Railways, the potential is it's about 18 million tons over the total life of 35 years. And there was an internal study which was also done by Indian Railways along with a UK-based agency, which mentioned that if railways could achieve a net zero target and they're able to cut about 15 million tons of carbon dioxide emission, then the savings would be about a humongous, 17,000 crore. So the potential of the criticality of utilizing the optimum grade of material for the transportation segment is immense. And so stainless steel, it has endless or limitless possibilities of getting utilized in the transportation segment, in the ART segment. And we from Jindal Stainless would be extremely delighted to have meaningful conversations with all representatives from Mahindra, from HAL, and others as well, and devise a customized solution for each of these organizations. Thank you.
So while thanking Mr. Ravit Ranaji, I would like to highlight that we already have an active collaboration with JSL, Jindal Stainless, particularly their Stainless Academy. And in last semester alone, there were course that was taken by the experts of the Jindal Stainless here. Apart from that, our students were taken on the industry tour by Jindal Stainless to their factory. And we are looking forward to more deeper engagement. GSV students who graduated last year, some of them are already working with you and helping you. This year also, I know you have hired some students, and I want you to explore
Surely
more, and we can collaborate more strongly in this area. As you know, Indian Railways has a big mission, and we have been set up by Indian Railways, particularly for the transportation sector, so we are a natural partner. Thank you so much.
Thank you, sir, for sharing your valuable insights with us today. We would now like to present each of our esteemed guests with a token of our appreciation. I now request our esteemed Vice Chancellor, sir, to present the honors to them. to Professor Paras and Prasad, we present the memento of our gratitude. Shri Arup Kumar Malik, please accept the token of our appreciation. Shri Ranit Rana, please accept the memento of our gratitude. Ladies and gentlemen, we will now take a short tea break. Kindly reassemble in the hall by 12:30 p.m. for the next technical session.
Jindal Stainless is one of the world's leading manufacturers of stainless steel products. Founded in 1970 by the visionary Shri O.P. Jindal, Jindal Stainless today has a capacity to produce 1.9 million metric tons of stainless steel. The company stands committed to its guiding vision and mission of providing trustworthy and innovative stainless steel solutions. Stronger and lighter at the same time, stainless steel is inherently corrosion resistant, durable, recyclable and aesthetic. For this reason, stainless steel is the preferred metal in industries like nuclear energy, construction and architecture, automotives and transport, oil and gas, desalination processes, fertilizer, storage, chemical processes, dairy industry, food processing, sugar, white goods, and of course, kitchenware. recyclable and aesthetic. For this reason, stainless steel is the preferred metal in industries like nuclear energy, construction and architecture, automotives and transport, oil and gas, desalination processes, fertilizer, storage, chemical processes, dairy industry, food processing, sugar, white goods, and of course, kitchenware. Our cutting-edge technology in the Special Products Division and state-of-the-art R&D wing is complemented by a superior knowledge of supply chain systems to produce world-class stainless steel products. Our wide range of stainless steel coils, plates, and sheets are acclaimed for their superior quality. The company is also one of the largest producers of coin blanks and razor blade grade of steel in the world. Our specialized subsidiaries offer innovative architectural and lifestyle solutions. Our service centers cater to tailor-made customer requirements through a distribution network spread across the country. Jindal Stainless serves the domestic and global stainless steel demand with its robust network of sales offices and service centers throughout the globe. Our customers include some of the world's most renowned market leaders. Rooted in the Indian philosophy of Vasudhaiva Kutumbakam, we strive to empower local communities by providing comprehensive healthcare, education facilities, and vocational training for promoting self-reliance and also augmenting their employability among communities. Backed by a wide network of 13 global offices, 10 domestic offices and 6 service centers, Jindal Stainless is continuously developing the stainless steel landscape of the country. Jindal Stainless, because it's not just steel, it's stainless steel. Jindal Stainless, India's largest stainless steel manufacturer, is a part of the $25 billion OP Jindal Group. With a turnover of $3.2 billion, Jindal Stainless is one of the world's leading manufacturers of stainless steel products. Founded in 1970 by the visionary Sri O.P. Jindal, Jindal Stainless today has a capacity to produce 1.9 million metric tons of stainless steel. The company stands committed to its guiding vision and mission of providing trustworthy and innovative stainless steel solutions. Stronger and lighter at the same time, stainless steel is inherently corrosion resistant, durable, recyclable, and aesthetic. For this reason, stainless steel is the preferred metal in industries like nuclear energy, construction and architecture, automotives and transport, oil and gas, desalination processes, fertilizer, storage, chemical processes, dairy industry, food processing, sugar, white goods, and of course, kitchenware. Our cutting-edge technology in the Special Products Division and state-of-the-art R&D wing is complemented by a superior knowledge of supply chain systems to produce world-class stainless steel products. Our wide range of stainless steel coils, plates, and sheets are acclaimed for their superior quality. The company is also one of the largest producers of coin blanks and razor blade grade of steel in the world. Our specialized subsidiaries offer innovative architectural and lifestyle solutions. Our service centers cater to tailor-made customer requirements through a distribution network spread across the country. Jindal Stainless serves the domestic and global stainless steel demand with its robust network of sales offices and service centers throughout the globe. Our customers include some of the world's most renowned market leaders. Rooted in the Indian philosophy of Vasudhaiva Kutumbakam, we strive to empower local communities by providing comprehensive healthcare, education facilities, and vocational training for promoting self-reliance and also augmenting their employability among communities. Backed by a wide network of 13 global offices, 10 domestic offices, and 6 service centers, Jindal Stainless is continuously developing the stainless steel landscape of the country. Jindal Stainless, because it's not just steel, it's stainless steel. Jindal Stainless, India's largest stainless steel manufacturer, is a part of the $25 billion OP Jindal Group. With a turnover of $3.2 billion, Jindal Stainless is one of the world's leading manufacturers of stainless steel products. Founded in 1970 by the visionary Shri O.P. Jindal, Jindal Stainless today has a capacity to produce 1.9 million metric tons of stainless steel. The company stands committed to its guiding vision and mission of providing trustworthy and innovative stainless steel solutions. Stronger and lighter at the same time, stainless steel is inherently corrosion resistant, durable, recyclable, and aesthetic. For this reason, stainless steel is the preferred metal in industries like nuclear energy, construction and architecture, automotives and transport, oil and gas, desalination processes, fertilizer, storage, chemical processes, dairy industry, food processing, sugar, white goods, and of course, kitchenware. Our cutting-edge technology in the
Good afternoon, everyone. Yeah. Bhaiya? Okay. Good afternoon, everyone. Welcome back, everyone. I hope you all had a refreshing tea break. We are now ready to resume our session. It gives me great pleasure to introduce Dr. Shankar Venugopal, who is a Vice President at Mahindra & Mahindra, leading technology innovation and the intellectual property portfolio for automotive and farm businesses, and serves as Dean of the Mahindra Technical Academy. He previously led technology innovation at GE, Dow, Honeywell, and Cummins. He holds a PhD in material science from IISc and a management degree from IIM Bangalore, and is a prolific inventor with 30 international and Indian patents, receiving awards including IISc's Best Thesis Award, GE's Edison Inventor Medal, and the Prolific Inventor Award. He also served on the B20 Task Force for Technology, Innovation, and R&D for Business Growth. Today, he will be delivering his talk on Materials, Innovations for Sustainable Electric Mobility. Ladies and gentlemen, please join me in welcoming Dr. Shankar Venugopal.
हेलो हेलो
थोड़ा आवाज हो जाएगा
Perfect. Hello, friends. I'm Shankar from Mahindra. If you're looking at that sheet and looking for my name, the speaking slot has been swapped. So that's why I'm coming in a little early. And I'm going to talk to you about some very exciting stuff that's happening in the automotive industry. And for all that excitement, materials are very key enablers. Without these new materials, we won't be able to achieve our dreams. That's the reason I thought I should talk about it here today. So my background, I studied physics and my PhD is in materials. I worked for a few other companies before I joined Mahindra, been about 10 years with Mahindra now, based at the Mahindra Research Valley. That's where we build all the new products that you see from Mahindra. The 6E, the 9E, the 9S, all the new electric vehicles that's hit the market in the last couple of years. They're all been designed by engineers like you sitting at the Research Valley. About 70-80% of the crowd is very young engineers like you all. So I would be very happy to host you all if you happen to be in Chennai to the Research Valley to show you what we do and how we go about it. When you talk about mobility, especially in the cities, three things comes to your mind. One is the tailpipe emission from the vehicle, which leads to a pretty bad scenario. So depending on which city you are in, you'll be able to relate to one of the three challenges that I'm going to show you. So this is the first one. And the second one is, in spite of all the technology advancements, you do see a lot of accidents that happen on the highways, and which I feel are completely avoidable. So we'll briefly touch upon technologies that can take care of that. And the third and the most important, I have lived a good part of my life in Bangalore. So everybody who has been to Bangalore can relate to this picture out here. Whatever be the day, whatever be the time, this is the kind of traffic you have to navigate through. So even if you are in an electric car, if you are stuck in a traffic jam like this, you are still stuck. Okay? So you have to start thinking about a very holistic solution, not just at a vehicle level, but at a complete ecosystem level to solve problems that are as complex as this. So can we come up with a zero emission mobility technology where absolutely there is no emission, absolutely zero emission, zero accidents? Have technology in place in your car so that accidents can be totally avoided. And the last but not the least, zero traffic jams. All the vehicles on the road should be such that they can smartly interact with each other and navigate through without leading to any traffic congestion anywhere. Is this something possible? Three zeros: zero emission, zero accidents, and zero traffic jams. In the next few minutes, I will lay out the plan to you to say that this is completely possible and this is not going to take a very long time. We are looking at a time frame of 3 to 5 years by when all this will be possible. What gives me the confidence to say that is basically a combination of 3 technologies: the electric vehicle, the autonomous vehicle, and the connected vehicle. It's a combination of these 3 that's going to do the magic. So you're all familiar with the engine-based vehicle and all the engine and all the other components. This is what you will see from that perspective in the new electric vehicle. The engine won't be there, and all the other mechanical components associated with the engine will also not be there. So this is what you will see in the electric vehicle. If you happen to open the front bonnet of a Tesla Model S, you literally see nothing. It's all empty space out there. So it's a fairly big mind shift for automotive engineers and product designers to visualize the capabilities, the possibilities of this new technology. What is really exciting about electric is 3 things. Absolutely no tailpipe emission, not even a speck. Nothing is ever going to come out of the tailpipe of your car. Second is very high fuel economy. We are talking about an engine with 20-25% efficiency to an electric motor which has 85-90% efficiency when it comes to energy conversion. So it's really something very attractive. And also not only the initial cost, the total cost of operation in terms of the fuel cost, repair, maintenance, everything makes it very, very attractive to switch over from engine-based vehicle to electric vehicle. And if at all you have some concerns about switching over to electric at this stage, it could be threefold. One is, I want to drive very long distances, but this vehicle has very limited range, so I may get stuck somewhere halfway through. Second is, the initial cost is definitely going to be higher because the technology is new. And the third is, oh, I drive into a petrol station, fill the tank and drive out in 5 minutes, whereas that's not going to happen with the electric car. It's going to take at least a couple of hours to charge my car, and I cannot wait that long. So, but if you look at all these 3 concerns that you may have, all of them can be traced to one hero in the electric car, that's a battery. So whatever breakthroughs that you can do in terms of the battery design, the materials, the manufacturing processes that goes into it, has an impact to really enhance all these 3 aspects and make it very easy for us to all adapt electric mobility in a very big way. Primarily, there are 3 bottlenecks around electric. One is the material that goes for the battery, which is a lithium-based material. The second is magnets. We need very small compact motors, which means we need very strong magnets, and those magnets are invariably rare earth magnets. And we have Professor Amol here, who is an expert in that area. He has done extensive work on possibilities of indigenization of this critical technology in India. You will hear more from him during the course of the talks today. And the third is the charging infrastructure. You need not just EV chargers, but you need fast chargers, which you can charge your car in 30 minutes and 45 minutes, which we don't have sufficient number today, but we have to build that. So the rest of the talk today, I'm going to touch upon few of the materials that goes into this. But actually my talk is more on the right side. You may wonder what is there on the left side, which is the sustainable energy part. I very proudly said there is 0 tailpipe emission. But imagine, you are not polluting, but at the end of the day, when you connect the car for charging, if the electricity that you use is coming from burning fossil fuel somewhere, then you are still polluting. So we are looking at clean sources of energy like solar, wind, where you can be doubly sure that you are not polluting neither on the road while using, nor at the source when you are generating the electricity. That means we need batteries for storing renewable energy. We need batteries for storing the energy on the car. So there will be double the demand for these lithium batteries. That's going to be a very intense activity in the battery space. Then we'll touch upon the rare earths for the motors, and also the more interesting, the sensors and the semiconductors, which goes into the automotive electronics part. I don't know, you heard a lot about steel and materials that you are familiar with so far in the day, but I'm going to talk about a few materials which you might not have heard at all. Can you try pronouncing some of these names? Dysprosium, neodymium, praseodymium. Okay, Amol has practiced it extensively because that's the world he lives in. So these are the rare earth materials that we are talking about. Then of course you have lithium, lanthanum, cobalt, manganese, nickel, all these going into the battery. So the rare earths goes into the motor and the rest of the things goes into the battery. This shows that the rare earths, they are critical materials because they are not available easily, and going forward they'll become even more difficult to get. That's why they are shown with a red dot. That's our critical materials. The yellow, the lithium, is near critical. As we make more electric cars and as we need more lithium, that will also become critical. So how are we going to mitigate this risk? Because our aspiration is to make a lot of electric cars and make our cities absolutely clean. But if these materials are so difficult to access, how do you mitigate the risk around the supply of these materials? That's something every researcher should start thinking about. This is basically the battery pack. If you look at Mahindra's vehicle or any vehicle which is electric, the entire floor of the vehicle is a battery pack. So it's not some small battery that you can take and put it back. The entire battery, we call it a structural battery because it's so heavy, we use it as part of the structure of the vehicle itself. So it's a fairly big battery system that you see out there. And of course, these are the materials, these are the properties. You want this battery to be safe, very high performance, thermally stable, a whole bunch of things that you want this battery to be. Of all the chemistries that you see here, look at the one on the bottom right, LFP, the lithium iron phosphate, is a current bestseller. That's what is being used by the industry today. It's really good in terms of performance and cost and very ideal for Indian conditions. So a lot of your work can focus on LFP because that's what is being used by the industry today. So there is a steady increase in the demand for the batteries today. So it becomes very important. Very large-scale plants have been set up in many parts of the world to make these lithium-ion batteries in very large numbers. The good news is the battery is almost 35% of the cost of the electric car. So if you want to make the electric car more affordable, we have to make the battery more affordable. And what this chart shows is there is a 73% drop in the price of the battery pack since 2010, okay, which is very good news. Can you imagine how much breakthrough, how many innovations would have happened to bring about a 73% drop in the price? This is amazing. So we can study what led to this kind of a significant cost reduction before you start your own research in this space. This is a very familiar picture to most of you who have seen how salt is made. Lithium is made the same way. There are these water containing lithium salt. So you evaporate away the water, you are left with the lithium salt. That is one way. The other way is also mining. But primarily, the world's supply of lithium comes primarily from Argentina, Bolivia, and Chile. 3 countries, A, B, C. It's very easy to remember. But that's where most of the lithium really comes from. It can also be mined. This shows the geography, the dependence of the materials from different countries. So when we are looking at building something indigenously, it's important for us to recognize where these materials are available and how we can come up with the right innovations to mitigate all the risk around supply of these materials. Some country, if it says that we won't give you this material, our activity should not come to a standstill. We should still be able to proceed with our vision. How do we do that? I said 3 countries for lithium, but if it is cobalt, which is another important material for the battery, that's only 1 country called Congo. Okay, so imagine with this kind of very stringent dependencies, how do you build this technology? How do you make it feasible and viable? So we did some work. This is a pure research work using a very powerful model called system dynamic modeling. This was originally developed by MIT in the US, but over the years this has been adapted by the industry and academia and also the government think tanks, where you can model however complex the system is, you can actually model. For example, if I make more electric cars, I would buy more batteries. When I buy more batteries, the price of the raw material will go up. When that goes up, naturally the car will become expensive. Car become expensive, the sales will fall. When the sales fall, naturally the battery material cost again will come down. So there is some kind of a balance that happens all the time. And it's once you understand the balance and how these interactions are, it's possible for you to predict various scenarios in the future. And then very easily you can have a control. You know what the knobs are, what the levers are. Then it's easy for you to build a viable business around even these critical materials where you have a lot of dependencies. This we built about 7-8 years back, and over the years we have fine-tuned the model by our predictions, comparing our predictions with the reality. What is the lithium price? What is the cobalt price? Every year we do this to fine-tune and make our model better and better. So this has gone through 6 years of iteration, and today it's in very good shape. And today you have AI and Gen AI, and that can do even a better job of handling these kind of complex dynamics and giving you very precise estimates. So it's not that difficult. Even the material is scarce till you will be able to manage it. That's the reason I projected this here. There are about 10-15 papers that we have published around this. I'll make them available to you if you want to use this in your own research. So we kind of did some predictions of pricing and availability for all the key materials. This is a work that we did with the IIT Madras. But you would have heard the good news that we do have lithium in India. Kashmir, the Vaishno Devi region, that's where we found not just small amount, but almost 5.9 million tons of lithium. Now the focus should be on how to process this material and how to purify this material so that we can have indigenous technology built around lithium-based products. I think this is a very good news. And today, there are very interesting startups looking at urban mining, which is collecting the used batteries and extracting the material, the cathode, anode materials from that and building whole new batteries out of a old battery. So there are companies which claim more than 90% efficiency in terms of extracting the used materials. So this is a big business opportunity. The second is what we call as deep sea mining. These materials are rare only on the Earth's surface, but some parts of the sea are very rich in these minerals. So today we have technology to do deep sea mining. So when you go for that, you'll be able to mitigate some of the risk around availability of these materials. So if we thought deep sea mining is crazy, I have something crazier than that, which is asteroid mining. There are startups which are getting funded for this, and people are seriously looking at catching hold of a few asteroids and mining on them. But these rare materials are available in plenty. Entire asteroid is made out of these critical materials. So if you have a way to handle it, you'll be able to mine it. Sure? So that is the crux of this whole thing, that it is, you will hear that some of the materials that goes into the battery for the EVs are very scarce and very difficult to manage, but there are ways in which it can easily be handled. Through your innovation and through your creativity, you'll be very easily able to manage these challenges and realize the dream of electric mobility. So it's very important not to get distracted by these negative things, that, oh, this material is very rare, how will you do it, we don't have enough lithium. That is fine. But we have, in the past, we have come up with many innovative solutions that has helped us to overcome these limitations, and sure, we can do it in plenty now also. This is the motor. So we are switching gears from the battery to the motor. Here, a whole bunch of materials are coming in for different performance parameters of these motors, like the cost, operating temperature. You heard about corrosion, the corrosion resistance, and also the strength of the magnet. So that's how all these dysprosium, neodymium, praseodymium, they are coming in different combinations to boost some of these properties that you are looking at here for a very small, compact, but very powerful motor in your electric vehicle. Today we are even talking about hub motors, so small that it can sit right on the wheel of the vehicle. And people are also exploring motors which don't need a permanent magnet, so that you need not worry about the rare earth magnet at all. That's another way to look at this. And of course, we do have rare earths in India, a good amount of variety of rare earths deposits in different parts of India. So that is also not really a problem. But whenever you think of rare earth processing, this used to be the picture that comes to the mind of people. Processes which are not very environment friendly, which exposes the people involved to great danger and risk. But that was past, long, long back. Today we don't need to do that. We have autonomous vehicles, we have completely automated mining systems, and all these things can be done in a very safe way, in a completely automated way, with many, very, very minimal human involvement in that. So we have the rare earth reserves, and by moving to these automated modes, we are also able to make sure that we are mining and processing in a very healthy and environment-friendly way. So that story is changed a lot. So we need not really worry so much about the rare earths. Finally, when you talk about autonomous car, how does the car see? It sees by something called a LiDAR. And this LiDAR used to be about 13.5 kg, a huge thing. Today it is so small that you can carry it in the palm of your hand. So compact it has become that it becomes very easy. When it becomes so compact, naturally the cost of the LiDAR also comes down. So what was around $70,000 is less than $1,000 today. You can do the math, it will be like 98% drop in the price of the LiDAR. Can you imagine? It's just 2% of what it used to cost just about 15 years back. Can you imagine how much of innovation would have happened to bring down the cost so significantly? So that is the eye of the autonomous vehicle. Today, any vehicle you buy in the market there are 5 levels of autonomy. So today's vehicles are between level 2 and level 3 autonomy. So the LiDAR price has come down so significantly today. And it's not just the LiDAR, a whole bunch of sensors. For those of you who have entrepreneurial dreams, who want to have your own startups after your study here, you can choose any of these sensors, because many of these sensors we are still importing, but it's not very easy, it's not very difficult to make them here in India. And I'm visiting one such startup, which is near Anand today in the second half of the day. This person has come back from the US and set up the shop here, and he's making some of these EV charging systems and sensors right here in Gujarat. So there is a lot of entrepreneurial deep tech activity around a lot of the EV components that's happening, especially in Gujarat. So for those of you who have a startup dream, you can look at all these as opportunities to indigenize and make EV a lot more affordable. So this is the snapshot of all the materials that you can pick up to work on if you want to really make an impact in the EV space. Just to wrap it up, we talked about EV battery materials. We initially said that they are little rare, they are near critical, but I also showed you ways in which it can still be managed, and you'll be able to bring back the lithium from the batteries and make new batteries and continue to make more and more EVs. So that is not a challenge. The second is the motor materials, the rare earths. We talked, the concern is more about the way we mine and process. Today with automation, that can be made in a much, much better way. So that is also not a concern. But it's very important for us to have as a nation a critical material strategy. That's where the industry and academia need to come together along with the government labs to have a roadmap. Today we are in 2026, where we want to be by 2030, where we want to be by 2035, that kind of a very clear roadmap in terms of materials, manufacturing, and design. This is very much needed. A couple of years back, I led the effort for a roadmap for lightweighting. So it came out really well. Now the government has started funding the labs for all those research. So I'm confident that we can do this for the critical materials also. So I brought all the industry, including the competitors together, and all the key universities together, and the government labs to make this happen. It took us more than a year to converge on a roadmap which is threefold: materials, manufacturing, and design. Because all three have to be in sync for us to realize this technology. The last corresponding materials technology roadmap is required, and with that I have shared what I wanted to share with you today. I am available for any questions or any other views you may want to share today. Thank you. I'll make myself available for another 10-15 minutes, then I would leave. Okay. Yeah. Sure, sir.
Whether it is happening in India as of now, because we are at nickel consumer battery.
Right.
Tried, but not yet. And now recently the Boeing debunked it.
That's true. Very true.
So there is a setback. So is there any knowledge available so that we can
Sure,
think of a safer?
Absolutely. So our experience with the LFP, the lithium iron phosphate, is a very safe technology. All the concerns that we have around lithium systems, we don't see any of them with LFP. And it's also cost-wise also it's very affordable. But the fact of the matter is all the battery packs are heavy. Okay. As long as we are on the surface, it's fine, it's not a problem. But when you want to fly, that can pull you down. So, but I have seen startups based out of IIT Madras who are making small aircrafts completely electric. These are like 4-seaters and 6-seaters, but completely E-plane is name of one such company. So they are making small planes because we have many small airports across India which are not being utilized fully. So they want to use the small aircrafts. These are completely electric. One another interesting thing was there is a solar-powered electric 2-seater plane that went around the world. So you can imagine, you have to fly in such a way that you get enough energy from solar, you land, and that way they are able to go around the world. So electric planes are possible, but today it's very small-sized aircrafts because of the weight of the battery pack, nothing else. It's only constraint. Okay. Yeah, sure.
You have one.
Yeah.
Very great question.
Sure.
Can you comment on the energy density and how is it going to go up in the future?
Sure.
That will impact the transport of the future?
Definitely, definitely. You asked a helpful question because energy density is way high for any lithium-based system. If you have the plot, it's somewhere right at the right extreme. But what can make it even better is a solid-state battery. Okay. If you ask me how long it will take for the solid-state battery to come in, I may not have an answer. But when that happens, the battery pack that I showed you is so big across the floor of the vehicle, it won't be so big. Maybe it will be as compact as this, so that you need not wait for charging the vehicle. You can swap the battery and move on. That's one aspect. So second aspect is maybe you need not pay for the battery. You can basically, you can pay for the battery as you use, so that your initial cost may get moved by about 35%, which is also a very attractive business model. So there are a lot of good things will happen when the battery becomes compact. That's what they are expecting when the solid-state battery comes in. So my guess is it could be 5 to 10 years, but most of the expert guesses have gone wrong with EVs. It has always happened earlier than the expert prediction. So we will hope that same thing happens with batteries also. Sure.
Just an interesting, maybe future. Can we think of a wireless battery? Like we need not a battery like a wireless charger.
Yeah.
We can have a vehicle, we don't need a battery in that.
Sure, sir. There have been efforts on wireless charging of the batteries. This is done in a fairly large scale in Tel Aviv in Israel, Seoul in Korea, and Sweden also had built a highway, maybe about 10-20 kilometers stretch where you can have a wireless charging. This is charging on the go. It's moving and then it gets charged. See, the concern around range anxiety will get knocked out if you're going to gain more and more charge as you are driving. But the transfer efficiencies are low, and there is also heating up of the system that happens. But For a small confined region with the extra cooling arrangement, one can definitely look at wireless charging. It becomes easy to align the car and charge in the parking lots especially. If you're away parking for 2 hours, if it can get charged during that time, it will be something good. So we have to start in a small way and then make it dynamic and wireless, not yet. But there have been 3 experiments that I'm aware of. I will share the references with you. Sure.
Thank you, sir.
Thanks.
Thank you so much.
Yeah. I think.
Yeah, thank you very much. So I fully agree with you. Solid state batteries really are in the horizon because there is a lot of development going on in processes involved in that, primarily in the mobility of the carriers there. So the other aspect where also there are important development going on is electrodes, nanostructured electrodes that provide more gain in kinetics happening at the interface. So I think that we can be very optimistic that both these coupled together can have a major advancement in making it compact. As you said, the issues of charging, discharging, how fast you can charge, speed, and durability, as well as cost.
Absolutely.
Thank you.
And also the weather conditions across India are quite so we have to optimize it for a variety of weather conditions, also terrain. So we have coastal, then the hilly regions and plains. You have to optimize it for all these regions. But the direction in which it's moving is the software is doing as much as the hardware. So even if you have a little not so great battery pack, if you have a very good battery management system and a bunch of software and apps to be intelligent enough to optimize it, still you'll be able to get a better performance. So more and more software is coming into the vehicles. So we call this as software-defined vehicles. And next they are talking about the AI-defined vehicle. That's where the software will eventually lead to a AI-based system. But surprisingly, all these things are happening in the cars right now. Because people are used to the smartphones. They feel if a phone can do that, why my car is not doing it? So they are now expecting all these things from the car also. Like when you get in, it should know that it's your birthday and say happy birthday and things like that. All the Tesla cars do that now. The lights will blink and say happy birthday, Prasad, and things like that. So all these things people seems to like. Actually, beyond fuel efficiency and safety, these things also have become as important, surprisingly. Sure. One question seems to have. Yeah.
Some more questions?
Is it okay? Yeah, one question.
Yeah, please take.
Yeah.
Good.
Yeah. I can hear you.
Hello. Hello. Sir, so China controls about 90% of the raw earth market.
Yeah.
So can India do cutting edge research when this is the case?
So that is what I try to convey here today. The materials are not uniformly distributed across the globe. But with whatever available materials, if you intelligently use in terms of designing the battery in such a way that you can recycle and reuse, you can build a new battery out of an old battery. All these things are very effective ways in which you can mitigate. That systems dynamic modeling diagram I showed you, if you have such a picture, you'll know what is the demand going to be and what is the supply you have to match. All those things are very well within your control. It's not that difficult. So materials, any risk around supply of materials can be very effectively managed, not an issue at all. Sure.
Okay, while thanking Dr. Shankar Venugopalji for an excellent talk. Firstly, one thing you might have all noticed that as the slides progressed, the battery got fully charged. Right? So are all of us with your knowledge.
Yeah.
Right? One. The second is with Mahindra Research, GSV can do many collaborative things together.
Sure.
I will just talk one or two possibilities.
Sure.
Firstly, GSV is now made a member of the Government of India's new task force on CCB. So we have a new thing to collaborate on the future of vehicles.
Sure.
Right? And possibly that is one area. The second, as you strongly highlighted, that for batteries, particularly, not only the material, but also it is very important to accurately estimate the state of charge and state of health.
True.
Right? And therefore, several models, which are so far maybe based on electrochemical models, there are newer models that we can make, which are more based on physics-based models.
Sure.
and we have good faculty members in battery space.
Absolutely.
Because if you have a accurate state of charge, state of health model, then you know how far the car will accurately go before you need charging.
Absolutely.
And without that, EV world is uncertain world.
Absolutely.
So that
Very
is
true.
another area that with Mahindra Research we can collaborate.
100%.
Our mechanical engineering students are and electronic students are very strong in that area. So maybe I offer a good collaboration.
Absolutely. I have 2 points to make in response to what you said. So I'm also the dean for the Mahindra Technical Academy, which is the organization which has reskilled all our engineers from the IC engine technology to the EV technology in a very short time. So that while we are hiring new engineers, we also made sure that all our existing engineers were skilled in the new technologies, and we brought all of them safely forward. So whatever we developed and used to train our engineers, I'd be very happy to share with your faculty and students. That is point one. Point two is we have launched an initiative called Future Leaders in Automotive and Manufacturing Engineering, FLAME, which is where we work with students in the colleges and have monthly interactions. We bring experts from different domains to talk to them, have mini projects, competitions, a whole bunch of things, so that in 1 year they become industry ready. So that happens when they are still with you here at GSV. That is something I would love to open it for GSV students today. With your blessing, we should be able to take it forward.
Thank you. Thank you. And GSV is an open green field for you. Our goal is on day one, after they graduate, they are productive in the industry, and that is what we aim at, and that is what we welcome you, your initiative.
Thank you.
Thank you.
Thanks. You have a question?
Yes, sir. Hello.
One second. Yeah.
Sir, I am asking that is there any big initiative from government of India? Why government of India is not focusing on these sustainable things as nanotechnology, deep sea rare earth materials, as you talked, will increase human development and India better?
Sure. Very good question, but I'm the wrong person to answer this. But whatever I know, ANRF and other schemes, there is a lot of funding made available for research in these areas. I'll share them with you, sure? I'll give you all those links so that you can use those resources and possibly come up with the research proposals also. It's all very big scheme with a lot of funding, with very clear focus. A lot of good things are happening, sure?
To add to what he said, right? Firstly, out of our ignorance, we should not say that government of India is not launching. We should know what is already launched. Let me tell you, right? I can tell you, even as a common, I'm not from the area, government of India recently launched a National Critical Minerals Mission, under which the focus is on ensuring the supply chain consistent manner for critical minerals that will be required in these areas, number one. Number two, right? Our current policies on the automotive, the FLAME policy that was recently launched, on how do we promote electric vehicles, and more of that is launched. As you know, the third thing, even in railways, if the 99.6% electrification is today done, it is done with an approach to move towards more of electrification and sustainable targets. Fourth, in our renewable energy mode, today India has a total energy capacity production of around 503 gigawatt total, out of which 258 gigawatt is coming from renewable energy. Okay, one of the largest. India has already set up a goal that by 2030 we shall have 500 gigawatt of renewable energy. Out of this 258 that is already ready, roughly around 58 is from wind energy, roughly around 106 from solar. And for wind energy, because as he mentioned, magnets are very important for that. That is why you must have noticed when our Honorable Prime Minister Modi ji went to Japan or to China or to Australia recently, there is so much discussion happening on securing the consistent supply of these rare earth materials so that our wind energy targets can be met, right? Last point, right? So these are the series of steps that are happening, right? The last point is that our own internal focus on renewable energy generation is taking a very, very big leap. So across EV adoption, right here in Gujarat, you have the biggest factory set up for EV batteries for Maruti Suzuki e-Vitara plant. Biggest factory, EV battery factory in whole India is set up in Gujarat. So there are many initiatives taken up by the government of India. Thank
Sir.
you.
But
before I leave, I'll take you offline. Before I leave, there is one more point which could be useful for all of you students here. So if you ask what kind of engineers the automotive industry needs, it's not just a mechanical engineer or electrical engineer or any one of the domains you are familiar with, but it's a mobility engineer who knows mechanical, electrical, electronics, programming, product design, all these things rolled into one. That is what a mobility engineer is. It becomes very important for you to pick all these skills rather than limit yourself to just one branch. And how do you do it in just the 4 years that you get to spend here? Don't limit learning only to classroom. Have summer internship projects. Participate in a lot of the hackathons and competitions. Take somebody from the industry as a mentor. Once in a month, you talk to them and understand what is happening in the industry. A lot of online courses are available. NPTEL, Swayam, Coursera, Udacity has a full-fledged course on autonomous driving. You should do all these things in your free time so that these 4 years, you are totally ready for the industry. Because this is a once-in-a-lifetime opportunity for India. If we get this right, we won't be just leaders in India, we can be truly global leaders. The EVs that you guys build here in India can go to any market in the globe and sell. We are doing that from Mahindra, and each one of you can do that. So it's a very important opportunity that you cannot afford to miss. So make the best. This is a university dedicated only for mobility. You cannot be in a better place than this. So make the best out of this opportunity. Thank you. Sure.
Thank you so much, sir, for that valuable insight. I would like to request our Honorable Vice Chancellor, sir, to present the token of appreciation to Dr. Shankar Venugopal. It is my privilege to introduce our next distinguished speaker, Mr. Naveen Chandra, who is a Development Director at Alstom, Component Development Site, Interior, India. He holds a BE in Mechanical Engineering from Delhi University and an MBA in Supply Chain Management from SIMT, Germany. With 25 years of industrial experience in automotive and rolling stock global business, he currently leads component development for Interior in India. Today, he will be delivering his talk on emerging trends and sustainability in material science. Welcome, sir. We are truly honored to have you with us today.
Good afternoon. It's first of all, thank you very much for giving me an opportunity to be here. It's a great pleasure for me. I think in principle you took me around 20 years back in the history. I was just thinking about it because 28 back, I was also just like you as a student in the Delhi University. So it is a good experience to be back in that kind of environment, to see the young talent. I also was sitting like you around 20 years back in the university listening about all the seminars and anything which is coming up in the industry. So it's a pleasure for me to give you some kind of insight from my side also. So about me, my name is Naveen Chandra. I'm looking after the development of whole of the interiors. When I call interiors, everything which goes inside the train. So if you happen to visit in Delhi, Lucknow, Chennai, Mumbai, Kochi, or in Pune, and if you find something on the train which is related to the ceilings, sidewall, seats, lighting, door pillars. I would call this thing as a grab pole or handrails. So these are something which are being developed by myself or my team. So if you have any kind of a suggestions or any kind of a remark, feel free. You have a face in front of you now. So in the coming years, you have my coordinates. So I'll be happy to see any kind of a remarks or a suggestion which is coming out from you. Coming back to today's agenda, I would like to give you a bit of insight about what kind of emerging trends which we are facing into the mobility world, which is shaping our mobility solutions, and how we are steering it up for anything which is coming up in a future world also for the mobility solution. And we being a part of an Alstom world, which is one of the leading rolling stock manufacturer in the world. So as an Alstom employee, how we steer to these kind of upcoming trends, and to see that what kind of solutions we can provide to the industry, to the people, to steer properly to these trends, challenges into the opportunity. And then last but not the least, I would like to give you some kind of real life solutions also which we have implemented onto our Alstom trains. So this is what I said about the agenda. First, on the emerging trends, I believe that this is something which is known to most of you people, but just to reiterate myself again, in terms of emerging trends or a global risk is something related to population. So this is the core of what a kind of a challenge which everyone has to face in terms of a population growth. And if you know this thing that in the coming 20 or 30 years program, right now the world population is in the range of 8 billion people. We are strong 8 billion people on the planet Earth. But soon it has been given in all the writings that in the coming 30 years time, by 2050, we will be around a strong of 9.7 to 9.8 billion. So we are growing fast. And while we are growing, it looks like that we are eating up all the resources quite fast. The demand on the resources is getting more and more stringent, and the scarcity of all the resources is there. So this is also one of the trends which drives what kind of solutions we have to drive onto the mobility world. And there is one more aspect for the population growth. I would say that we are growing, but if I say this thing into the population cluster, we call this thing as a Gen Z, millennial, or we call this thing as a boomer or a Generation X. And the last one, which we call this thing as a silent population. It is something which we have to take into account that we are growing in the manner in such a way that we are having more boomer and more silent population is growing. So in this way, how the mobility solutions in the future will address to the requirement of that strata of a population. Because right now, most of the mobility solutions which we are having it here are what we call this thing as a basic infrastructure development. We want to cater to the high capacity metro applications. If you can see in Delhi or in Mumbai, how we are using the mobility solutions. And if I go in the range of people who are in the age group of, for that matter, 50 plus or 70 plus, we need to think how we can cater to the requirement of those people, because those peoples are growing fast. Then there is one more aspect for the population that we are migrating quite a lot. So the people are leaving their well-established, I would say, the living nest, and they are coming to the urban cities. And we are having a huge strain coming up in urban city. People are highly density population is growing up there in small pockets, and how to cater to the mobility requirement of those highly concentrated population strata, that also we have to define. So this is one aspect in terms of population. Environment, I believe that everyone knows that we are having a huge strain on all the environmental requirements in terms of whatever resources we are having it there. We are using it, consuming it quite fast. Before me, some speakers also mentioned about the CO2 emissions. So our, what we call this thing as a planet Earth temperature is increasing more rapidly than what we anticipated. The 2025 target, which was given to us, we have already overshooted it. We thought that we can maintain it within the level of 1.5 degrees Celsius, but we are a little bit more. So that's how emissions are increasing, pollution is increasing, how to cater to that thing so that our solutions in terms of mobility can help us out in reducing these kind of changes and make a positive impact. Then in terms of geopolitics and finance, inflation is also one factor. Everyone wants to have a right value of money. I want to have something which tomorrow should be cheaper. I saw an expert person from the EV industry. He mentioned something that within a span of 10 years, he has reduced the EV battery from 97% and all these things. So everyone wants to grow, but they want to have a value of money. So this also is creating a little bit of strain that we have to provide the same performance, same services at the better price, at the better conditions. Then I believe that you know that recently or maybe in the down the line in the last 3 to 4 years, we are having a huge increase, steep increase in terms of what we call as a geopolitical conflicts. I would say that if you can see what recently happened in Latin America, what is going up in Western Europe, what's going up in the Middle East, all these things is creating a lot of stress in whole of a global supply chain. We are putting more resources and effort in terms of a military and defense spend, and this creates a lot of scarcity for us also in the mobility business. What should we do? Then thanks to Mr. Trump, I would say maybe it's a political, I don't want to be political, but thanks to Mr. Trump, he always brag every second day that this is a war which he is stopping. So this also creates a little bit of a stress in the market for us globally in the financial world. How to cater to those kind of requirements, we have to develop some kind of solutions which are agile, resilient, robust. So these kind of a target which we anticipate to reach. And the last one, which I call this thing as a technology, I call this thing as an enabler, because technology is something which is going to help us out to create the solutions more user-friendly, appealing to the passenger comfort. So we are using this kind of a technology to ensure that how we can get to the passenger experience well established to the market at the right time. So you'll see that in the upcoming slides. So these are the trends which we feel that needs to be addressed to shape up our current mobility solutions and the future solution which we want to anticipate. And then what we do as Alstom, who is one of the leader of the rolling stock business. So what we have done is this thing that, okay, we know that environment is an issue for us. The geopolitical and macroeconomics and population, these are the external ecosystem for us. We don't influence them. We have to cater to those points so that we can get this thing delivered into our product in such a manner that the end user will not get any kind of impact. We can create some kind of a positive impact. So this is what we see that in case of a climate, we anticipate to go for a zero emission. That's our aim in the Alstom also, that how we can reach and focusing on a zero emission mobility solutions. Then in terms of a geopolitics and macroeconomics, we would like to see that our solutions in the market should be more robust, should be more resilient, adaptive to the situation so that they can carry that kind of a stress test which is going on in the market can be properly catered. And the last one is in case of a population, we would like to be more inclusive. Our solution should address to all the strata of a population, not only for the Gen Z or a millennial, but I would like to see that my product should be really catering to the requirement of a boomer section or a silent population also, that they should also feel appealing and respected inside my solution, which I'm going to provide. So then, just to summarize this thing, that what we have done in Alstom, we have looked into all these dynamics, and we have put 6 major work streams which we are working. So this is the first work streams to explain you that higher capacity at constant infrastructure. We feel that the infrastructure is something which is not going to have a multifold increase immediately. So how we can increase our capacity of our rolling stock by maintaining the same infrastructure availability which is available to us. Time to the market. Every time we are having a huge demand for the rolling stock, but how to cater to that demand at the right time so that we can reach to the market, to the real customer at the right time. So this is also one of the work stream which is quite stringently followed in the Alstom. Then the reduction of total cost of ownership, not only for the acquisition cost. People say a lot that, okay, I want to have a cheaper solution, but we should have a more perspective. I think this morning, Mr. Rana, if I pronounce it correctly, he mentioned about the 30 to 35 year of a life cycle vision. So we should develop some kind of a solutions which gives you that kind of a vision that what is going to happen for me in the next 30 to 35 years of my product, to see a kind of a concept which we call as a total cost of ownership, not only the acquisition cost for a hardware, but always integrate the service portion also of it. How well my product is going to work in the service area in the real field. So that also we should take into account to develop our solutions. Robust and resilient. In the past, we were having always a more emphasis in terms of a robust solution. That means we develop a solution which is sturdy, which is heavy, which is catering all the stress. But now we would like to go not only for robust, but the resilient. Resilient means that something which is adaptive, something which can sense the environment and adapt to the requirement and modify and get this thing properly delivered performance. So these kind of solutions also we are anticipating in future. Towards zero emission, so as I said that this also is one of the key pillar stone for us to go for a sustainability solutions. So we are anticipating and we are targeting for towards zero emission also. And the last but not the least is about the passenger experience, because at the core, our solutions are for our passenger. We want to enhance the experience of my passenger. So anything which happens onto my solution, the person who is using it should feel happy at the end of the day, that these are the trains and these are the solution which was given by Alstom, and they are okay, they are good. So having said this thing, so for me, these are the 6 major work streams which we are doing it in Alstom, with a targeted result which we want to anticipate is passenger experience, enhance the operation, and to maintain my assets, which is their rolling stock assets which we want to maintain. And then a little bit more into the sustainability priorities now, because we say that how we can go towards the sustainability. So these are the key 5 pillars which we are having into Alstom world. The first one is to see that how we can reach to the zero mobility emissions target. Then we are having a resource preservation. So this also is quite a good initiative which we are trying to work out, that not only looking for a linear economy, we would like to put more and more circular economic concept, that how we can put the product back into the life cycle again and again, so that we don't go for anything again and again in terms of a new production of the raw material, new production of the parts. So this is onto the kind of a material side. Then along with the material side, we at Alstom are keeping people also in the center point, that we would like to keep our solutions more inclusive. Inclusive means what? That people who are having, for example, restricted mobility, who are not able to reach to the train properly. So I would like to see that my trains should have that kind of a capability to adjust to the requirement of the people of restricted mobility, or a special needs can be provided to those kind of a people in my trains. Then to have a kind of a support in terms of not only for gender diversity, but to have a people acceptance and to develop a people quotient in our train business so that they can feel happy. So it's more of a social inclusiveness which we want to build up as a kind of a sustainability model. And the last but not the least is towards the social supply chain. When we call social supply chains, that means I is only a part of an ecosystem, because I need to take care of my tier 1, tier 2, tier 3 also, because all of these people are a part of my ecosystem, because I'm sitting at the end of the ecosystem and I'm delivering my product to the customer. But whatever is happening inside my train is being driven by the various custodians, tier 1, tier 2, tier 3, tier 4 people. And there we have to get that kind of a sense that how their product and their services can be sustainable, how these products can be made green, easily available. So there also a program of Alstom is there that we have to filter out these kind of ethics and the way of working to a major supply chain driven suppliers. When I say suppliers, because at the end of the day, I usually buy around 70% of my sourcing is done through the external people. So I'm dependent on 70% outside the ecosystem of Alstom also. I know that how I'm going to drive the 30% of the value additions, but I'm highly dependent on my business partner, my supplier, my consultant also. So this kind of a know-how and this kind of a drive, we should do it on whole of the ecosystem. So we Alstom always feel that kind of a initiative should be followed at the last mile operation also in the value chain. So these are the key 5 activities which we are having in terms of a sustainability activity. And just a bit of a deep dive, because it was told to me that to have a sustainability, how you attain the sustainability. So this is one of the initiatives in terms of how we target zero emission. As I said before, that since we are a part of an ecosystem, we are dependent on the various business partners, supplier also. So we have clustered this thing into main 3 areas. What we call this thing as the carbon emissions. So we have a program where we are encouraging all our service provider and the part provider that they should also have that kind of a sense that they should start measuring their carbon emissions. They should have a carbon footprint tool estimation so that we can get those products integrated into our train ecosystems which are sustainable, which is having a kind of a good acceptance from us. So if I see this thing that in case of purchase goods and services, this is our target from Alstom side, that by the end of 2030, we would like to see that whatever is there at the level of 2021, our organization has taken an initiative that we should have a reduction in the range of more than 30% of the carbon footprints. So that means that whatever is carbon emission, we were having it into our product in 2021. By the end of 2030, we should have at least 30% reduction. And what does it mean 30% reduction? So it just says that for me, I should have a reduction of approximately 670 gram of CO2 emission on every euro which I spend on my vehicle. So this is a target which we are pursuing into the procurement community, because this is highly driven by the sourcing community, that they have to tighten up and they have to encourage that kind of a supply chain which can help us out in achieving those targets. And then in terms of operation, which we call the thing as scope 1 and scope 2. Operation means that anything which is happening within the premises of Alstom, because we being a rolling stock manufacturers, we do that kind of installation. Close by to your place in Vadodara, I believe that we are having a huge facility in Savli, so that Savli also is assembling a lot of rolling stock business. So Savli also is having that kind of a target that they have to reduce absolute emission of 40% by the 2030. What does it mean? That whatever they are having in terms of fossil fuel or any kind of electricity or any kind of operational support which they are doing it to get the product out from their premises, they should have a reduction of 40% in their consumption of the carbon emission. That's what we are targeting. Then in case of a sold product, so because the product, once it moves out from the Alstom premises, we sell the product with a design life of 30 to 35 years. So I do a stringent regulation by putting these targets just at the verge of handing over to the customer. No, I want my product to meet these kind of a carbon emissions and the carbon reduction norms in the whole lifespan of my train life. So that is 35 years. So there also, these are the targets which we are anticipating to reach. That is in case of a passenger vehicles and in terms of a freight wagon also. So these are the targets which has been pursued by us. I would say that when you can ask me this thing, that where are we today? So I would say that today we are not up to the mark. We have a lot of work which needs to be done in the next coming 5 years. So as per our anticipation, we should have been done in a better manner in 2025, but work is ongoing. It's tough work, and there we need to have a support from all the people from the ecosystem that how we can meet those targets. As far as the operation is concerned, and for the sold products, there we do have huge influence from our side. So that's what we are doing it step by step, but it's require a kind of a collective effort, which we see in the whole of the industry. Then maybe in terms of resource preservation, as I said in the beginning, that this also is an initiative which help us out in limiting our carbon emissions, that how far we can go for a kind of a circular economy products, not only for the linear, that from input to output and then go to the waste. No, we would like to see that what happened to the waste also. So there's also an initiative in Alstom that whatever is coming up from the operation, any kind of a waste, we should have at least we should have a kind of a recycling concept on each of the Alstom site. We encourage that each of the Alstom site should have a capability of putting at least 85% of the waste should be properly recycled, and it should not be dumped in any kind of waterfronts or any kind of a riverfronts. We should have a proper recycling there. And in terms of recycled content or rolling stock and infrastructure business, that we see that more and more the recyclable product should be there on my train, so that the trains can be properly recycled after the design life of 30 to 35 years, for that matter. Then towards the end, just to give you an example of two of the sustainable solutions which we have implemented on our train. So what we call this thing as e-leather. This is one of the concepts which we have worked out with our supplier, which is more of a tier 2 supplier, which is e-leather. What they do is this thing that they conserve and they refurbish the leather which goes in the downstreams. So they process this waste, and from that waste they regenerate a kind of a leather solution which we are using it into our seed business. So if you happen to go in the Europe, so these are the various commuter trains in Germany and in Denmark. So these trains will be having a reprocessed e-leather, so that we can have a more kind of a carbon neutral products into my train. And then onto the right side, you can see that on the flooring cover business, we are having a supplier by name of a NORA interface. So there we are even going to the level of carbon negative. So they are locking more carbon emission into their product rather than emitting it into the open market or in open business. So these kind of a trends we are trying to work out into our product, so that we can have a more and more kind of a circular and carbon neutral products on Alstom train, and we should be having a socially more responsible supply chain. So that's our vision, so that we should make it more and more appreciative. So that's why we are in context, we are developing a kind of a carbon rating system for our supplier. So whoever who is going to have a more carbon rating, who can provide us a solution which can have a more kind of a carbon neutrality or carbon negative footprints. So those kind of a product and solutions we would like to emphasize more and more, appreciate into our train. I understand that there's a lot of issues in terms of certification because we are basic infrastructure mobility company, so the safety and security is always the core of us. So all these new solutions require some kind of a certification, testing. I would say that, like, let's take the example for fire and smoke results. All these things has to be stringently tested, but we always appreciate and welcome that whoever who's having any kind of a solution which can goes for that kind of performance, we appreciate and put that thing on our trains. So in that manner, this is what I wanted to present to you. If you have any kind of a questions or query, feel free to ask me now.
Carbon negative. Is those products and material is readily available in India or you need to import?
Just a minute. For India.
Yeah, interior. The
Yes.
interiors, there are, your target is set as a negative carbon and nil carbon. So whether whatever material you are using, is it available in India or you need to import?
Right now, we have to import, but we are developing in form of a technology transfer. As I said, that we are working into a tier 2 and tier 3 level of a supply development also, that yes, we are developing and working on the technology transfer kind of activities. And for us, just to add on this thing, India is like a very expanding market for us. Because in the beginning, I mentioned that our world population is going to increase drastically. But it was also one of the hindsight. You will be amazed that India is going to have a 30% content on that increase. It has been told to us that India, Pakistan, and Nigeria, these are the 3 countries who are the front runner for the next 30 years in the world population increase. So if we are the people who are going to be consumer of these technologies, I'm pretty sure that it is something which has to be driven from the bottom up. So we as a India market has to go and get it more robust in developing these kind of a technology because it's a need of a time for us.
Okay, thank you so much for your very wonderful talk. I think the lunch time is approaching, so not many people are asking questions.
Okay, good.
Right?
No problem. If anyone have a question, feel free to raise later on, offline also, no problem.
Maybe we have one more talk and then break for lunch.
Okay.
Quickly. Yeah.
Good, thank you. Thank you very much.
Thank you so much, sir, for that insightful session. It is my privilege to introduce our next speaker, Dr. S. Parivalal, who is the Chief Scientist and Advisor at CSIR Structural Engineering Research Center, Chennai, and a Fellow of the Institution of Engineers, India. He holds a BE in Civil from PSG College of Technology, MA in Structural Engineering from Government College of Technology, Coimbatore, and a PhD from Anna University, Chennai. Since 1994, he had led the structural, health monitoring, and fatigue and fracture laboratories working on experimental mechanics, stress evaluation, condition monitoring, and remote health monitoring of critical infrastructures across nuclear, aeronautics, pipeline, and defense sectors. He has published more than 150 papers and 250 technical reports, guided PhD and postgraduate students, and delivered lectures in colleges, workshops, and advanced courses. Dr. Parivalal serves on a Senate of Alagappa University and Planning Board of MS University, and received the Smart Technology Development 2007 Award for Smart Sensor-Based Remote Structural Health Monitoring. He is an active member of IEI, ISNT, ICI, and ACCE. Today, he will be delivering his talk on Materials, Monitoring, and Mobility, CSIR-SECR role. A warm welcome to you, sir.
Thank you.
Vanakkam and good afternoon to everyone. So today my presentation is on material monitoring and mobility, CSIR-SERC's role. As we all know, like our railway network, initially from steam engine to diesel engine to nowadays like electric locomotive with all high power engines and all, and again loading also from CC loading to now CC plus 8 plus 2 and nowadays 25 ton loading. So the loads are all increasing and the speed also, like nowadays it is like a high speed and bullet trains are coming, so with the speed also increasing. So we need to cater for these improvements, we need materials. And again, these materials has to be like evaluated, performance evaluation has to be done, and some kind of a health monitoring of this structure has to be done. So for that, monitoring is very much needed for this mobility related things. So CSIR-SERC has contributed like more for this material development in civil structural engineering and for monitoring also. So I'll be presenting what are all the CSIR's contribution to this railway network and in general for transportation network. So briefly about Structural Engineering Research Center. So this is comes under CSIR, Council of Scientific and Industrial Research. About 37 laboratories are there in all over India. So ours is placed in Chennai, and ours is a 60-year young institute. Recently only we completed our Diamond Jubilee celebrations. So we are basically doing this basic R&D, and based on the industrial needs, we taken up some R&D activity, and we are solving their industrial problems also. And some of the societal, based on our R&D, some societal activity also we are doing, and we are contributing to strategic sector also. And we are working on 6 thrust areas: structural health monitoring and life extension, disaster mitigation, advanced materials for sustainable structures, special and multifunctional structures, energy infrastructure recently like renewable energy and all, energy infrastructure, and offshore structural engineering. So these are all our thrust area, and we are working in 10 different laboratories. Okay, these are all the different laboratory to cater or working under these areas. And as I said, we are a 60-year old institute, and these are our contributions. Like India's first fly ash building, like 1973, at the time, the fly ash was not thought of as a waste. So at the time itself, we have introduced this fly ash in utilization of this concrete. And precious concrete sleepers for railways, like replacement of wooden sleeper to precious concrete sleepers. We are started this precious concrete sleepers, and some of these cold deformed parts. Nowadays we are telling all these reinforcements. So this is developed by CRC, and these are all some of the like activity we have done during 1965 to 1984. That's first 20 years. Later, like national capacity building. So LPG gas pipeline lowering. So the pipeline is running across the country, and this is they are find it difficult whenever any like canal or something is crossing. So we are also solving that pipeline industry, and these are all some of the activity we have done. And 2004 to 14 interdisciplinary research and activity. So here we are contributing to like nuclear power industry and remote structural health monitoring, and again this is for like seismic testing and evaluation. And currently we are doing for remote structural health monitoring, aerodynamic studies for wind engineering and all, and new material development, fly ash aggregates, geopolymer, UHPC, etc. So these are all the recent scientific contributions. 3D printing is currently going on, and emergency retrieval system for power sector, and floating renewable energy. So these are all the recent contributions. So with that, I am coming to this presentation. As I said, the loads are increasing, so we need advanced materials for sustainable infrastructure. So I am covering this also, and structural health monitoring. And based on the research and research activity, we have solved some industrial problems and also that also I am presenting. So as we all know, this mobility infrastructure, bridges, highways, railway, airport and all, this is the backbone of economic growth and connectivity. So these structures to be like durable, safe and sustainable. So no, we have to ensure the safety, serviceability and sustainability of this kind of structures, and for that this modern infrastructure depend on advanced materials and smart monitoring. So for advanced materials, like already we have seen steel and different materials. Being a civil engineering laboratory, we are more concentrated on this concrete or concrete-based materials. So these are all the latest materials available: high performance concrete, ultra high performance concrete, then corrosion resistance and high strength steels, fiber reinforced polymer, FRP composites, then nowadays smart materials and self-healing concrete, and now how to dispose old concrete and all. So based on that we have taken sustainable recycled material, how we can utilize it, and geopolymer concrete and all. So basically the benefits are strength, durability and sustainability. So CSIR-SERC, we are developing various kinds of concrete, so carry out both computational experimental studies, and we have state-of-the-art facilities, we are utilizing that. And what is the need to develop R&D expertise in areas of lightweight and high strength material, alternative material for green construction, recycling material and use of waste material in construction, and nowadays prefabricated and pre-engineered structures. So that are all emerging area, so that also we are contributing. So we are doing holistic design and maintenance approach for achieving sustainable infrastructural systems. So one of the thing is like engineered cementitious composites. So here in this concrete we are introducing, or the fiber reinforcement is introduced, and this give rise to like strain hardening property, and it is giving like when any damage is there, it will give multiple damage so that the performance will be enhanced. Here you can see like So for normal concrete, the ductility will be very less, and here in high performance concrete, the ductility is improved. Same way ultra high performance concrete also. Here also the performance we can see, and this is ultra high performance concrete. So here the minimum compressive strength 150 MPa. So for the latest like high speed train and all, we need that kind of higher strength material and all. So for that also we are contributing. It is typically 5 times stronger than our normal concrete and 50 times higher than the fracture energy. And these are all the elements also nowadays coming, the weight also coming less, and this is ideal for precast material. So this R&D, and we are utilizing and we are transferring technology to the construction industry. And these are all the places it is used. Okay, cooling towers, blast resistant, bridges, wind turbines, so all that places these are all utilized. And nowadays the 3D printing is coming to limelight. So that also nowadays we are using characterization of 3D printable concrete. So we need buildability, flowability, and the extrudability. So these are all the basic requirements. So we are doing R&D, and we have already developed 3D printable UHPC mixers. We have characterized rheological characterization already been done, and based on that we have constructed on demo building also using this. So this is the printer at laboratory level, printer available at our laboratory. So these are all some of the studies carried out. So basically, so these are all the materials, material side concrete, these developments is happening, and how to like perform, evaluate the performance of these structures. So for that, the structural health monitoring is very much needed. So this monitoring plays a crucial role in ensuring safety, reliability, and optimal maintenance of mobility infrastructure. So normally, these are all some of the like failures are happened all over the world. If you see all these structures, the damage, the failure started in some critical member failed. That leads to a catastrophe. So in order to identify this kind of failure at the initial stage itself, the damage could have been eliminated or reduced. So for that, this structural health monitoring is very much needed, so that uses sensors to continuously monitor and assess the behavior. So this this system help in detecting early signs of distress, fatigue, corrosion, and damage, enabling timely intervention and preventing catastrophic failure. So what are all the needs? As I said, due to traffic and increased loads, the design requirements are high, and weather and material are aging. So unsatisfactory inspection and monitoring of existing structure needs this kind of monitoring. If the monitoring is not there, these are all the consequences. Catastrophic sudden failure will happen. So loss of life and high social impact. So what are all the different methods for monitoring? This is visual inspection, non-destructive evaluation, condition monitoring, and structural health monitoring. So the importance is like it will enhance the structural reliability and also enables early detection of structural issues and to prevent catastrophic failure. So it is supporting real-time monitoring and rapid response after the disaster, and it is increasing the lifespan and sustainability. So like medical doctor, the analogy is like medical doctor monitoring the patient's health. So same way we can monitor the condition of the structure by using different sensors to check the overall structural health. And if excessive stress or deformation is there, we can do a corrective solutions. So what are all the structural health monitoring implementation strategy? There are baseline structural assessment is there. So at the time of like new structure itself, we can take what is the baseline of these stresses and all. Then later we can compare with that while monitoring. So that way we can detect any deviation from the original signature. Then real-time monitoring. So this also like we can deploy the sensor with the communication network and all for continuous monitoring. And periodic inspection also we can do, that is integrating structural health monitoring data into maintenance schedule. So based on the response, the maintenance schedule can be like formulated. And disaster response and recovery planning. So immediate assessment, once the structural health monitoring is in place, after any like major disaster, we can immediately assess and post retrofit can be done. So what are the technologies used in SHM? Nowadays, like IoT, Internet of Things and smart sensors are available, and artificial intelligence. Once the data, sensor data is collected, how to get the health of the structure using artificial intelligence and machine learning. So we can use pattern recognition and predictive maintenance. And nowadays the data, so much data is coming from the sensors. So we need some cloud computing and big data analysis. So these are all the technologies very much needed for structural health monitoring. And as I said already, these are all the advantage of structural health monitoring. So basically the structural health monitoring is non-destructive in situ structural evaluation method that uses several types of sensors embedded and attached to the structure. So finally, ultimately, structural safety, strength and integrity can be assessed. So the benefit is like reduction in downtime, prevents catastrophic failure and reduction in downtime, and it increases the operating life, reduction in lifetime cost also. So we can utilize for aging infrastructure such as containment vessel, bridges offshore, and like a new generation material. Like nowadays there are so many materials are developed. So that material initially without having a long-term performance, we are using it. But by using this health monitoring, we can get what are all we can develop a confidence for that material. If anything is there, we can corrective measures also, we can do it. So that way the new opportunities are available. So in structural health monitoring, we can classify into two categories, like first is diagnostics. Once diagnosis is done, then how to do prognostics. So that is like in diagnostics, identification, where the structural damage is, whether structural damage is there or not. So that is identification. Once if we identify some damage is there, then we have to identify where the location is, where it is, the damage is occurred at which location. Then location is known, then what is the quantification, whether it is a small damage or what is the bigger damage. How then once these are all available, then we can do how to prevent, or we can how to extend the life. So that way diagnosis and prognostics, we can do it for structures. And there are two methods. One is global structural health monitoring, and another is like local structural health monitoring. In global structural health monitoring, we need to measure acceleration, deflection, frequency, modes. So using these parameters, we can evaluate the structural health. In local structural health monitoring, we can measure strain, impedance, guided waves using, these are all the sensors, piezoelectric sensors, optical fiber sensor, laser interferometer. So these are all things. And basically from global structural health monitoring, we can find out where the damage is there. Once the damage is there, the detailed thing we can do it with local structural health monitoring. So any like health monitoring, it should be a combination of global and local structural health monitoring based on the structure and requirement. So these are all the diagnostic techniques available in structural health monitoring. There is a distributed strain sensing, crack detection, corrosion monitoring, thermal imaging, vibration-based technique, wave propagation techniques. So these are all the techniques available for civil infrastructure. And basic structural health monitoring system should contain sensor to monitor, then the data acquisitions to acquire the response from the sensors. Then based on the data acquired, the damage has to be identified and localized. Then after that, the health can be diagnosed. So these are all, each category, these are all the parameters we can monitor: environmental loading, global performance, local performance, then how the data acquisition system, data simultaneously we can acquire, and for remote structural health monitoring, what all things needed. So these are all the basic functional modules of a health monitoring system. And for any civil engineering structures, this is the typical instrumentation scheme. So here we can monitor deflection, strain, acceleration, temperature, precessing force, tilt, rotation, settlement, and where they can, the sensors can be aligned. So this figure gives how the instrumentation scheme could be in a bridge structure. And these are all different sensors. For deflection measurement, dial gauges, displacement sensors available. For acceleration, accelerometers can be utilized. And for strain, there are different sensors available. For short-term monitoring, we can go for electrical resistance strain gauges. And for long-term monitoring, vibrating wire sensors are available. And even fiber optic sensors, there are, these are all used for long-term monitoring. And for temperature measurements, there are different temperature sensors available, RTD to thermocouple to thermistor and the semiconductor. So these are all different temperature sensors available. Even we can measure tilt, rotation, settlement using this kind of tiltmeter, inclometer. And precessing force and crack also measured using this type of sensors. And data acquisition system. Nowadays, like so much data is there, we have to process the data and store the data. Modern data acquisition system comes with all these things: signal conditioning, analog to digital converter, computers for processing. So key benefit is like real-time data collection and accurate signal conversion and easy integration with the computers and software. So any like remote health monitoring scheme, we can say like from the structure, we can collect in a local site processor. So all the data is collected near the bridge or that structure. So this is a short range measurement. So it can be wired or wireless also. Even with a radio frequency signal, we can collect this data in a local site processor. From the local site processor, like we can monitor from thousands of kilometers away. Like Kashmir, bridges in Kashmir, we can monitor from Kanyakumari using these kind of arrangements. So the communication, we can use PSTN network, GSM, our mobile network, or fiber optic cables. So already we have developed a system some 10-15 years back, and we have we monitored Visakhapatnam Port Trust bridge from Chennai. So that way we have developed this kind of systems. And nowadays with the advent of IoT cloud-enabled integrated structural health monitoring framework, these are all things online, like online monitoring can be done. So here, as I said, these are all different sensors, and this is a local site processor. From that, like broadband or IoT-based protocol, we can send it to wherever the monitoring station is there. Then later, like data aggregation, analysis, all that thing we can done at laboratory level or monitoring station using IoT client framework. So with this latest technology available, all these things are nowadays possible. So like we have solved for railways and other infrastructure users. So that some few case studies I am now presenting. So as I said, for railways we have done so much work for Indian Railways. You can see in that map almost all over India we have catered to railways in different zonal railways. So these are all activity we have continuous. Like every month we are going to site for at least two bridges. So that way our structural health monitoring team is working. So this is very early, when some 20 years back, like unification of gauge. Originally this arch bridge, it is in near Salem, Athur region. It is a stone arch bridge, it constructed during 1914 and all. So meter gauge to broad gauge traffic, whether this old structure, whether it is utilized, can be carry the new broad gauge traffic. So for that we have done this load carrying capacity. So we have instrumented with strain displacement transducer at different locations, and this was connected to data logger. Okay, here the data logger is placed, and it was loaded with rail plus some kind of a sandbag. So the design load was applied, and finally we could measure the responses and the ground displacement and the spread displacement. This is within the allowable limit. So later, based on our intervention, the bridge was like meter gauge traffic converted into broad gauge traffic, and now it is still it is running broad gauge traffic near Salem in Tamil Nadu. And this is structural assessment of a railway bridge. Here in this particular railway bridge, at the time of construction itself, here you can see this is a pre-stressed concrete structure. I think normally any pre-stressed concrete structure, once the pre-stressing is done, the initial profile should be, it is a hogging. It is like arch type upward. But here you can see it is a kind of deflected, looking like a deflected profile. But this is because at the time of casting of the pre-stressed concrete, this casting girder should be like a straight line. But same casting girder they have repeatedly using for different spans. So some point of time, the initial profile of the casting girder, that is instead of horizontal, this itself became curved. So the initial profile itself is becoming curved, and even after pre-stressing, it is looking like it is deflected. But it is not so. But the Commissioner of Railway Safety, they are not given clearance, and we have gone to site and like we have measured. One is like already it is pre-stressed. So how to get a stress, already available stress, that we have developed. We have one technique called concrete core trepanning technique. So based on this technique, we can evaluate what is the available stress. Then later for live load, we have done a load testing. So finally we could combine and get the total stresses available, and we have like evaluated whether what is the stress developed due to pre-stress and self-weight, and what is the and total load due to the proposed loading. So that way the structural adequacy of the bridge was assessed, and based on our report, then later it was cleared from the railway safety point of view. So, no, these are all the details. What are the instrumented locations, how the loading was done, and what is the deflected profile. So this is the stress pattern. So here we can see a linear stress pattern is there. So that means it is linear within linear elastic range, and the maximum deflection it is within allowable limit, and the stresses also within allowable limit. So thus the serviceability of the bridge was established. And this is the Pamban Bridge. This is old Pamban Bridge. Old Pamban Bridge also, like it was originally constructed for meter gauge traffic. Later in 2005 or so, they want to convert into meter gauge traffic to broad gauge traffic. At the time, our Abdul Kalam, who was the President of India, this is his native place. During that time only it has been done. And this is a complicated structure. It is a movable bridge. You can see when ship is coming, this will be open up and the ship will move, and other times normally it is open for railway traffic. So this is a like a different configuration. So the analysis we have to do. So for that we have done with the meter gauge traffic, what is the stresses developed, and using that stresses we modeled, finite element modeling was done. After that, with that testing, we perfected the FE model. Later, the broad gauge traffic was applied, and the design was modified based on this numerical analysis and experimental work. So that way we converted into this old Pamban Bridge with meter gauge traffic to broad gauge traffic, and after that it was served the purpose. And since it is located in Rameswaram, that is the world's second largest corrosive environment, because of some reason the corrosion was happened, and now they dismantled it, and new Pamban Bridge has come up. So this is during testing. We have instrumented at different locations. We get the responses, and that response was feed into the finite element modeling. So this was perfected. Then new broad gauge configuration was arrived with this same configuration. Only different the member properties were modified. So accordingly, it was converted into broad gauge loading. And this is one health monitoring of a real-time a bridge. We have done it at Visakhapatnam during 2003 to 2007. 20 years back, we have done it for Visakhapatnam Port Trust. So here also, this is a pre-stressed concrete structure with these are all the how it is pre-stressed and all. So these are all the details of the bridge. So here we instrumented with the vibrating wire strain gauge like this, and during pre-stressing also we measured what is the pre-stressing force applied, and from fiber optic sensor also, and compared with the theoretical calculation. So the variation is very less, and periodically measured for strain and temperature, and finally the loss of pre-stress over 5 years we monitored, and this is as per the design over 5 years it is behaved with what is the design predictions. So that way we have done. So during instrumentation measurement, this is I am doing that time. And deflection also measured at a different point of times using the total station. So this is the comparison between estimate of pre-stress loss from the measurement, and we compared with the American Concrete Institute code. And here this is the deflected profile over 5 years. You can see any pre-stressed concrete, as I said, this should be camber. It should look it should not deflect downwards. So here the deflected profile is only camber only. So that means the pre-stress is effective. So that way we have monitored these structures. And there are so many of the bridges, mostly it is pre-stress concrete, and over the period the pre-stress pre-stressing force is reducing due to so many reasons, corrosion and so many reasons. So in order to bring back the structure to the original design structure, first we have to know what is the pre-stress available, then only we can do a retrofitting using external pre-stressing or some means. So for that, as I said, the concrete coat-repaning technique, we have that technique. Using that technique, we have solved so many bridges, and it was retrofitted and bring back to the original designed condition. Yeah, these are all the different structure we have instrumented and tested for evaluating the health of the structure. And the capacity augmentation of existing bridges in Indian Railway. As I said, the loads are increasing. So originally the Indian Railway with the CC plus CC loading, and later in all iron ore routes, the axial load was increasing to CC plus 8 plus 2. So for that also, we have in iron ore routes, we have these bridges were constructed some 50-60 years back, and even with the higher locomotive and higher loading, whether the same bridge will be safe enough to carry these loads. So for that also we have instrumented and tested, and the longitudinal force developed will be very high because of this latest powered engine and all. So that also evaluated, and since these structures factor of safety was available, so even 3 years continuously, some 4 cycles, different period of time we monitored over 3 years, and almost the same behavior was observed. So that way the old bridges also able to take the higher axle loading. So again, for RDSO, Rail Design and Standard Organization, we have done some 10 bridges instrumented, and how to mitigate the higher longitudinal force. So for that, some STU, shock transmission unit, because if the bridge, on the bridge, if any braking or tractive effort, braking is applied, or the vehicle starts from the bridges, the higher tractive force will be developing. So how to mitigate that? So for that also we have studied for RDSO, and we come up with this STU. So this by placing this STU, we can reduce the longitudinal force. So that way we have contributed, and yeah, these are all during the testing time. Okay, so this is for steel concrete composite. So we are, as I said, we are all over India, we are moving and solving their railway bridge problem. Any bridge issues is there, we are ready to help with our expertise. Yeah, these are all some of the things. Even old arch bridge also, I think during one flood near Vellore in Chennai, near Chennai. So that also one of the bridge was damaged. Then immediately we gone to site, and we have given a solution how to retrofit the structure. So the innovative scheme conceptualized, designed, and implementation on the failed arch within a short span without interrupting the traffic. So that way we contributed. So this is the health monitoring of that new Pamban bridge. So new Pamban bridge also we were involved. So this is almost some 5-kilometer railway line from the India land to Rameswaram Island. So it is connecting this island. So some 100 spans were there. So these are all the normal spans, and this is the same old bridge was there. This is a navigational span where the ship is moving. So out of 100 spans, we selectively done some 4 spans for before commissioning. We tested and assessed the condition of the new bridge, whether it is designed as per the thing. So that way we tested, and for the navigational span also. So these are all some of the measurement and results based on that. So this is now we are doing for this navigational span structural health monitoring. We are now we are on the job. So maybe after 1 year, structural health monitoring scheme will be available. So automatically we can get the health of the structure. So we are on the job. Okay, these are all some instrumentation schemes and all. So how we are going to do? So this is. And even some R&D also we are doing, fiber optics based wayside railway asset monitoring system. So these are all the parameters we can monitor. So normally some manually they are doing this kind of monitoring system. So we can like automate. So that way we are involving in this work also. And even like many like road bridges, every time we have to go to the structure and we have to instrument it. So why we have to like instrument all the structures? Instead, we do instrumentation in a particular vehicle, and if we run the vehicle and get the bridge health, so that way some R&D is going on. So this is also there. Once this is there, this will be very much useful. Yeah, so this is the future direction of SHM. So we need R&D towards low-cost robust sensors and computational efficient physics-based models, and like use of IIoT for monitoring large number of structures and components. Development of guideline methodologies is very important, especially for civil engineering. And that needs interdisciplinary collaboration, like collaboration between engineering disciplines, then material science, nanotechnology, policy regulation, so integration with the computer science and data science. So all those things are very much needed, and now India is very much available this kind of knowledge, and we can come out with interdisciplinary collaboration for mobility infrastructure. Yeah, with that I conclude my presentation. Thank you for providing this opportunity for GSV, and sir, we can also collaborate, like we have excellent expertise facility available in our laboratory for this one. We can collaborate also.
Yeah, thank you. In the interest of lunch, maybe we can discuss
Okay.
during that. Just one thing I want to quickly highlight, that recently Ministry of Railways has set up the Center of Excellence in Bridge Design and Structural Health Monitoring at Gati Shakti Vishwavidyalaya.
Okay.
So all railways, everything, the COE is here. Therefore, we are a natural partner. In next month, we have a Indo-Canada workshop on, I think, 19th and 20th March, related to the same topic. I want to invite you.
Okay.
And we should join hands as an organization for structural health monitoring of our bridges. Thank you so much. We can have more questions during lunch.
Thank you.
Thank you so much, sir, for those valuable insights. We would now like to present each of our esteemed speaker with a token of our appreciation. I now request our esteemed Vice Chancellor, sir, to do the honors. To Dr. S. Parivalal, we present the memento of our gratitude. To Mr. Naveen Chandra, please accept the token of our appreciation. It's now time for the lunch break. We encourage you to use this time to refresh and engage with your fellow attendees. Please ensure your timely return to this hall, as the next session will commence from 3 p.m. sharp. Thank you, and I wish you all a pleasant lunch.
Welcome back, everyone. I hope you all had a refreshing lunch and a chance to network and fully connect with fellow guests. It is my great honor to introduce Professor Amol Anand Gokhale, who earned his BTech from IIT Bombay and MS and PhD in Metallurgical Engineering from the University of Pittsburgh, USA. He retired as Director of DRDO, DMRL, Hyderabad, and is now a professor in Mechanical Engineering at IIT Bombay. His research focuses on lightweight and high temperature aerospace materials, high strength steels, and aluminum foam sandwich materials. He is a fellow of the Indian National Academy of Engineering, former president of the Indian Institute of Metals, and chairman of the Research Council of National Metallurgical Laboratory, with more than 100 publications, 2 patents. He has guided 11 PhDs and 7 MTech theses and was a guest researcher at the National Institute of Material Science, Japan. Today, he will be delivering his talk on materials for aerospace systems. Welcome, sir. It is a privilege to have you with us.
हेलो नेक्स्ट बैक एंड पॉइंटर
ये बैक है
हाँ बैक बैक
और नेक्स्ट का कौन सा
ये नेक्स्ट
हाँ
नेक्स्ट
और
ये
ये
बैक
और ये पॉइंटर
बोलिए
हेलो am I audible? Thank you for the kind introduction. Somebody said refreshing lunch, but it was very sumptuous lunch actually. So I won't blame you if I find some of you sleeping there while listening to me. So before I get into my talk, couple of times my name got mentioned. So let me just tell you about these rare earths. These rare earths are called rare earths not so much because their occurrence is rare, but partly also because it's difficult to extract them from the earth. And India has about 3% of the global resources of rare earth minerals. Only unfortunate part is that the Indian source, the Indian minerals they are occurring in monazite sand. And monazite sand also contains thorium. So the cost of extraction becomes a little bit high because you have to separate thorium securely, which is a nuclear material. While the Chinese are very lucky, theirs comes from the bastnasite ore, and that's not having any radioactive material. But now, luckily now, with various programs in place, now rare earth, oxide to metal, metal to magnets, is now a company has been established, a production line has been established in Vizag with the help of BRC and IREL. And another venture is coming up in Hyderabad under funding from Technology Development Board. That is rare earth oxide to all the way up to motors that Dr. Shankar Venugopal was mentioning in the morning. So that's a little bit about the rare earth part of it. I really enjoyed the talks, all the talks I'm really enjoying, and especially the talk by HAL, because a lot of the things that I have been doing, though I'm in IIT Bombay, but I'm originally from DRDO. I spent 30 years in DRDO, and a lot of my research work had interaction with HAL, GTRE, Mishra Dhatu Nigam, all the organizations that he was talking about. And since he has given a good overview of aerospace materials in general, I decided that only 2 of his slides are going to be expanded here in my talk in the remaining, say, 25 minutes or so. So I'm going to restrict myself to aluminum alloys. When we talk about aluminum, the image that comes to our mind may be of household utensils sometimes, though now practically replaced by more fancy utensil materials. But the other end is the aerospace application. Okay, so I think Mr. Malik in the morning did show this. This is purely the Kaveri engine cross section here.
and it shows the temperature as you go from the intake all the way up to the nozzle, and how the temperature rises slowly stage by stage. This part is the compressor, which is the domain mostly of titanium alloys. They are all indigenized now, right from making titanium sponge as a raw material. Again, the titanium ores come from the same sand of Kerala, which contains the rare earths. So that land is very precious actually. The coastal part is very precious. It contains titanium, zirconium, rare earths, and so on. So extraction to titanium sponge is done at KMML in Kerala, and processing is done up to component level by Mishra Dhatu Nigam. And now there are several other companies which have also come in the recent times. The part in blue, sorry, I think I am using the wrong buttons. Yeah, going back, yeah. The part in blue, that is the domain of nickel-based superalloys. And nickel-based superalloys are made in Mishra Dhatu Nigam again. Of course, nickel is not much mined in India, but nickel-based superalloys are all made in Mishra Dhatu Nigam, and now there are other industries. Some of them were mentioned in one of the morning talks. The only technology which is not fully productionized is the single crystal blade making. The technology has been developed by my previous laboratory, DMRL, and that is actually, but its yield right now is something like 50 to 60%. So if you make about 100 blades, only 50 or 60 will come single crystal, otherwise they will be directionally solidified with multiple grains. But eventually that will be also transferred to Koraput, where the directional solidification technology was transferred earlier. And this part is again a tough part, because in the nozzle we use silicon carbide, ceramic composites. They were also mentioned earlier in the morning, ceramic composites. Silicon carbide fiber, which is called nickel-on commercially, that's a very difficult one. That's one of the laboratories under DRDO in Kanpur, DMSRD, that is the one mandated to develop SiC fibers. But otherwise, the chemical vapor infiltration, chemical vapor deposition, those technologies have already been established at NL under DRDO funding. With that little filler, let me go to my main talk today. So I don't have any other introductory slides, just to save time. And I've taken the example of a passenger aircraft, although my primary job was to deal with earlier fighter aircraft, and even now whatever I'm doing is all towards fighter aircraft. India doesn't have any passenger aircraft industry, nothing big. So what I have shown here is that although in one or two words we can say aluminum alloys, but actually there are 8 families of aluminum alloys from 1000 series all the way up to 8000 series, and only 3 of them are relevant for aircraft applications, and I will deal with only 2 of them, the 2000 series and the 7000 series. But they are meant to fulfill a range of service requirements. Those service requirements vary. For example, the wing, if you take, here also the upper part of the wing, the service requirement requires compressive yield strength, Young's modulus, fatigue, fracture toughness, etc. While the lower wing requires fatigue as the primary domain. If you have seen an airplane in flight, the wing is like this. So Air Commodore will verify some of the sentences that I am saying. And so the tensile loading is mostly on the underside of the wing actually, tensile loading. While the upper part is under compression in flight, so that experiences compressive loading. Accordingly, the requirements are different. Accordingly, the type of aluminum alloys chosen are also different. Then the horizontal stabilizer is an upside down wing, so the requirements are exactly reversed there. And the vertical stabilizer has somewhat similar as the lower part of the horizontal stabilizer is concerned. Then you have the fuselage skin on the upper side, again compressive yield strength, fatigue, and so on. Then this side is under shear type of a loading, because when a turn is initiated, then that part actually experiences a shear force. The role that is in the aerodynamics terminology. And then there are titanium alloys also. Now I'll go to the next slide. Okay, so but what are the factors which translate those service requirements to aluminum alloys? How do we get to aluminum alloys? Because from structural point of view, the weight is proportional to these factors. If the component is designed based on stiffness, that is Young's modulus. If the component is designed based on strength, then these are the ratios on which the weight of the component depends. So density is the primary and the commonly occurring factor here. So lower the density, naturally the weight will be less. And these are the different type of structural members here. And these, so for a beam, it will be rho divided by e to the power half, that is e to the square root of rho by square root of e. Otherwise, it's the one third root, that is the third root of cube root of Young's modulus. So using those formulas, you can find here that among aluminum, titanium, steels, and sorry, that should be carbon fiber epoxy. The last column is carbon fiber epoxy. Given those densities and the elastic modulus, and if you plug them into these formulas, then you will get the relative weights of aluminum if it is 1 as some kind of a normal, and then titanium, iron, and carbon fiber epoxy are in that ratio. So only carbon fiber epoxy weight of the component will be less than that of aluminum, while otherwise using steels and titanium, the weight of the component is more. So that's what is the factor which favors the use of aluminum alloys for all those components. In addition, we have established production lines, and later on I will use the names of some of the industries which already have established production lines for aluminum alloys in general, not necessarily aerospace aluminum alloys. Scraps are recyclable without reducing the quality of the component up to 60% of the scrap, and the remaining 40% can also be recycled, but not for the aerospace. It could be used for other commercial purposes. Then unlike CFRPs, aluminum alloys don't suffer from swelling problems, so there is no problem with moisture. Already strong databases exist, and I will show you towards the end an example how machine learning was used to develop an alloy whose yield strength is almost double that of the common aluminum alloys. And there has been the long experience in the design, production, and inspection maintenance. And somebody was mentioning that certification is a very long and arduous procedure for any aircraft component. So those processes are very well established. So one of the reasons why additively manufactured components are not used as frequently as the bulk produces, because the inspection and the certification become very, very complex when you go for parts which are made one at a time. It becomes very difficult process. So the design criteria, in the morning also, in I think one of the talks it was mentioned, strong and light, that's true. But that was the criterion used during the Second World War. So the 7000 series alloys, the workhorse alloy was 7075. That was chosen based on strength per unit weight only. But then lots of accidents were reported in the 1950s, in which three combat aircraft, they failed, they crashed. And that was the beginning of the understanding of fatigue, which is today an integral part of qualification of any material. Because although the load requirements could be met by that alloy, the fatigue requirement was never factored in. And so they just failed when the load was in the elastic range itself. So no plastic deformation ever occurred, and the aircraft just failed. Later on, of course, more failures were noticed in the 1980s, where corrosion fatigue was understood to be a factor in those aircraft which are operating in marine environment. So later on, the so-called damage tolerance concept was understood, and fracture toughness fatigue strength and fatigue crack growth resistance became important parts in the selection and qualification of materials. So based on that, you can see that, again, the passenger aircraft, a range of alloys is now used, not just aluminum alloys. Wherever higher strength is required in the localized area, you cannot use aluminum. Take the landing gear, for example. Very small part of the landing gear may be in aluminum, because you may say that I'll use a more voluminous landing gear, but then it has to be retracted into the body of the aircraft under the fuselage. So you cannot accommodate that much volume there. So there steel has to be used. But now some of the steel is replaced by titanium alloy, which is shown in the first one, number 1, titanium 10-3. That's a high strength titanium alloy. Similarly, somewhere the temperature requirement may be such that you cannot use an aluminum alloy. And I will show you towards the end some recent development where people have tried to raise the temperature limit of aluminum alloy. So let's look at the trend. 1960s, late 1960s, I think around that time the jumbo jet, Boeing 747 came. That was the time when the aluminum was practically ruling the airframe. You can see that nearly 80% of the airframe weight was done in aluminum, while the composites were, this green triangle, were almost not there. Means the composites were made by that time in the 1960s, but their properties were highly unreliable. There was a huge scatter because the quality of the fiber was not good, so they were not used. Because in aircraft, the performance is more important than the cost. So composites could not be used in the 1960s. But just see what happened over the years. Aluminum just went down, and today we are somewhere here actually, around 20% structural weight is in aluminum, but the composites have just taken off. So these two lines are actually mirror images of each other, which say that the reduction in the aluminum alloy used on the aircraft is a direct result of composites replacing them. But another factor also replaced aluminum alloys, because wherever aluminum alloys were okay to use, but the joint between the aluminum and the composite was not good galvanically. Aluminum was corroding when it was in contact with CFRP. So those components had to be replaced by the heavier titanium alloys, because the titanium alloys were chemically compatible with CFRPs. So that led to a great reduction in aluminum. However, this may not be the last word in the story, because a lot of the things which come by experience are not well understood in CFRPs. There are environmental issues, UV exposure issues, composites swell over a period of time. Then the recyclability is under question. You cannot recycle them again to aerospace quality use, while aluminum alloys are 60% recyclable to the aerospace quality. So there are a lot of issues, and we don't know whether the trend will continue as shown by the dashed lines. So as far as these are all the applications from within India, I have not taken any example from abroad here. So top left is the light combat aircraft Tejas, where about 45 to 50% airframe weight is aluminum. Missiles, one of the stages is in aluminum, that's the Prithvi missile. Here, this is not aerospace, but that's an armament application where the main core is the tungsten, which defeats a main battle tank. But the tail unit, which is here, and the discarding sabot, they are made of aluminum alloys. The sabot gives the aerodynamic stability to the penetrator, which goes and hits a tank and defeats the armor. Helicopters like ALH Dhruv of HAL and light combat helicopter also, they use aluminum alloys. And PSLV uses extensive amount of aluminum alloys. In terms of requirement, I wish HAL could have corroborated this number. But what I obtained from ADA, which is the main designer and developer of the light combat aircraft, the orders today are such that about 1,000 metric tons of aluminum alloys are required for the next decade for the light combat aircraft. But they will look small because compared to the AMCA program, which is now advancing very fast, Advanced Medium Combat Aircraft, because that is at least twice as big as the light combat aircraft. And you may be hearing or reading in the newspapers that they are now in the selection of a partner who will produce the AMCA aircraft. So the requirement is not very high, requirement is rather low. In fact, that's one of the reasons why we don't have a well-established production line for aircraft grade aluminum alloys. Yeah, so that's the Indian Advanced Medium Combat Aircraft, which ADA is spearheading. Some time back, there was a talk of a fifth generation fighter aircraft to be produced by HAL in collaboration with the Russians, but I think that plan has been dropped. But in place, just last week, you would have read that Rafale may be produced in India, co-produced in India under some TOT from France, from Dassault Aircraft and Aviation. So I think in the future, you can expect that the 1,000 metric ton over 1 decade, that will be increasing multifold. And aluminum alloys are required in different product forms such as forgings, extrusions, sheets, and plates. And the starting point all of them is direct chill casting. So you would have heard, I think steel is a more commonly understood material, commonly taught material also. And continuous casting of steel is a very well-known word. But DC casting, direct chill casting is a less known word. But it's another type of continuous casting. But it's semi-continuous casting because steel requirement is very huge. So steel continuous casters rarely stop. They keep running 24/7 and they stop only when there has to be maintenance. But DC casting ingots is not so. So from the top of the building till the bottom, when the casting reaches the bottom, then the process is terminated. Then again the next melt starts. So it's kind of a semi-continuous casting. Then the ingots have to be homogenized. As the name says, the homogenization is done to remove the segregation of the alloying elements, because at the end of casting, the alloying elements are non-uniform in the ingot. So you cannot directly forge it or process it by any other means, but it has to be homogenized. Also, all the aircraft grade aluminum alloys, the recrystallization, if you have had any course in materials, unfortunately I cannot give this talk without using some metallurgical terms, is that the recrystallization has to be controlled or prevented. Because if you don't do it, the grain size becomes very large. And if you know what is the Hall-Page relation, that tells you that very large grain size will reduce the strength of the alloy. And so certain dispersoids have to be precipitated as a part of the homogenization process. And then you have to scalp it, that is clear the surface, and then you have to reheat the ingot, take it to the recrystallization temperature. Now, recrystallization is allowed here because then you are going to refine the grain size during hot rolling, forging, extrusion, etc. Then finally, you do the solution treatment. During this stage, you want to prevent or control the recrystallization. So you want either a very fine grain size for the fuselage applications, or for the wing, upper part of the wing, you want unrecrystallized microstructures. They are typically made up of thick plates. But also towards the end, I will show you the thick plate part is also penetrating into the bulkheads of the fuselage to reduce the inventory and to minimize the usage of the rivets. Now people are preferring to go for thick plates rather than riveting multiple thin plates. So again, the thick plates are coming into the picture, which require unrecrystallized microstructure. There are 4 kinds of strengthening mechanisms in aluminum alloys: the grain boundary strengthening, solid solution strengthening, work hardening, and precipitation hardening or precipitation strengthening. The one in bold, that is precipitation strengthening, is the main strengthening mechanism in aluminum alloy. Although I did mention grain boundary strengthening, that also contributes about 10% of the strength. Solid solution strengthening is the reason for which copper, magnesium, zinc, all these elements are contributing there also. And work hardening is not very important in aluminum alloys because they are all solution treated eventually. That nullifies the effect of work hardening. But work hardening is important in 5000 series alloys, which have a limited use on aircraft. Some of the naval aircraft which are very sensitive to corrosion problem, they use 5000 series alloys. And precipitation hardening is the most important one. Okay, so now this is metallurgy, pure metallurgy. So there are different kinds of aluminum alloys, right? The first column, 6000 series, 2000 series, and 7000 series alloys. And the last column you see is the range of the typical, that is the tensile proof strength or the yield strength. You can see from the top row 275 MPa, down below as you go up to 600 MPa. It is increasing for the different alloys. And why is it so? The solute content is also increasing. Part of the reason is that the second column is the solute content, but also the kind of precipitate, the highest strength aluminum alloys, which are the 7000 series alloys, are here, and they are all strengthened by a precipitate which is a plate, not a rod, not a lath, not a needle, not a sphere, but a plate. Now I'm talking about nanoscale plate. When I say plate, don't think of what a structural engineer would think of a plate. I'm thinking a plate which is only maybe 50 nanometer wide and maybe 10 nanometer thick. So all these strengthening precipitates are at the nanoscale, to observe which you need a transmission electron microscope. A normal optical microscope won't work. Scanning electron microscope won't work. You need a transmission electron microscope to characterize those precipitates. So they are not only because they are plates. So what is the importance of a plate? A precipitation strengthening mechanism works because the precipitate hinders the dislocation slip, which is what causes plastic deformation. So if you resist plastic deformation, you are effectively increasing the yield strength, and the plate occupies more area for a given volume. So the dislocations are effectively retarded, causing plastic deformation. Not only that, more importantly, the precipitates occur on 111 plane. If any of you know what is the significance of 111 crystallographic planes in aluminum, they will know that 111 is the slip plane. So that is a plane on which the plastic deformation takes place. So if you block the plastic deformation on the slip plane by the precipitates, you get the maximum strength. Okay, so that's mainly the reason. But one of the new 2000 series alloys, which is not included here, and I'm currently working on that, 2050 aluminum copper lithium alloy, also forms precipitates on the 111 slip plane. That's a more recent discovery, and so they also are high strength alloys. So yes, so 2000 series by and large are used where damage tolerance is important, while 7000 series alloys are used where high strength is used and where compressive loads are more dominating than the tensile loads. And the 2000 alloys can withstand slightly higher temperature range, 120 to 150 compared to the 7000 alloys. And that's all related to the phase diagram. I'm not going into those details right now, but that's broadly the classification of 2000 and the 7000 series alloys. Now, I don't want you to read the entire table, but just look at the alloys whose last two digits are 24. So they are the same family of alloys. The second digit 0, 1, 2, 3 up to 5, it tells you the purity level of that alloy, and that can be seen here. Iron and silicon are the impurities. As this second digit is changing from 0 up to 5, you can see that the impurities are decreasing here. And so that's how those are the improved versions of that original alloy 2024, though conventionally many people say we use 2024, but now rarely 2024 would be used. Now mostly 2124 onwards alloys are used. And copper, magnesium are the main alloying elements here, which actually result in the formation of the precipitate, which strengthens the alloy. And zirconium and manganese are those elements which form dispersoids, which prevent or control recrystallization. So another complication is that many of these alloys, see, more the alloying element you add, higher the precipitation strengthening you get. But then where do you stop? How do you optimize the alloy content? A time comes when you find that you cannot solution treat the alloy anymore. For example, from strength point of view alone, I would like to add as much copper in aluminum as possible, but as you will see that if I go to the right side of that point here, I cannot solution treat that alloy anymore, and so I will never be able to enter the single phase region during my solution treatment. So my limit practically becomes this point, means in reality somewhere here, because any industrial furnace will have some plus or minus temperature range. So I have to stop short somewhere. Similarly, in a multi-component alloy, this is aluminum 4% copper. If I keep adding magnesium, the range of temperatures over which alpha, single phase alpha exists is reducing. So I cannot really add more than 1 or 1.2% of magnesium, because then the temperature range becomes so narrow that in an industrial solution treatment, I would end up either going into the liquid or unable to dissolve the second phase, the core second phase, which will reduce the fracture toughness. So you have to consider the physical metallurgical aspects as well as the industrial processing aspects in optimizing the alloy composition. And if you have too much impurity content, then you get the crack actually during stressing, and that can reduce the fracture toughness. These are 7000 series alloys. They are more rich in terms of the total alloying additions. And then you can see that again here 7075, 7175, 7475, etc. They become purer and purer. And nowadays they are largely replaced by alloys which are down below in the range. Yes, so they are used again in sheet, plate, extrusion, forging, etc. And here again the composition control to be able to cause all the coarse particles to dissolve is very important. And the second problem that the 7000 series alloys suffer compared to the 2000 series alloys is that they suffer from what is called as a stress corrosion cracking. And I will show you one heat treatment which has led to solving that problem. That is shown here. So one of the problems of 7000 alloys is that this is a strength versus aging time during the artificial aging treatment. We would like maximum strength, so we would like to stop the aging here. But then also that's the same time range over which the stress corrosion cracking resistance is the lowest. So to avoid that, what is done is, so that's a schematic microstructure, that's a real microstructure. This is a transmission electron micrograph here. And within the grain, so these are the grain boundaries, within the grain you have a very fine precipitates, two kinds of precipitates. One are the dispersoids, GP zones, Guinea-Preston zones, which are the clusters of atoms of the size of 5 nanometers or less. And the needle-like things are precipitates called eta prime, which is MgZn2, again of the nanometric scale, which is barely visible here. So extremely fine structure, but then it has, at the grain boundary, it has an unwanted phase called eta, which is the equilibrium version of eta prime. So this microstructure gives you the maximum strength, but lowest stress corrosion cracking resistance. And that was leading to early failures in the early part of the life of 7000 alloys. So nowadays, this patented treatment by Alcoa, RRA, retrogression and reaging treatment has solved that problem, where retrogression is done, where you let the grain boundary precipitates coarsen. So now they are not connected. Here they are all continuously connected. Here they are not connected. So even if a corrosion crack forms here, it does not penetrate at the same rate as in this microstructure. But here within the grain, the fine precipitates have gone here during retrogression at a higher temperature. So the structure has to be re-aged to bring the matrix microstructure somewhat comparable to the original, and the grain boundary structure will be as here. So it's a combination of this and this you get here, and the actual microstructures are shown there. And that has now solved, that's called T77 temper, and that now gives you a good combination of stress corrosion cracking resistance, that RRA treatment. And the strength is also high, and the resistance to stress corrosion cracking in the form of K1 SCC is also high. Okay, I will skip this because I have already, I think, gone into it. But this only shows the extent of corrosion, which was not shown previously. So without the RRA treatment, the corrosion penetrates more. RRA treatment, the corrosion penetration is much less. Less corrosion penetration can also be obtained by simply over-aging, but then the strength is low. So that's why, to get the best combination, we do RRA treatment. Now within India, so this is our ecosystem within which the aluminum, the aerospace aluminum alloy development community is operating. There have been some changes in the recent past because many private entrepreneurs have now entered the picture. But HAL has been traditionally the producer of aircraft in India. ADA has been the designer since 1984 when it was established. And ISRO has been the designer as well as integrator of the space launch vehicle as well as the satellites. And the aluminum producers have been Balco, Bharat Aluminum Company, which was a PSU, now owned by, I think, the Vedanta Group, and HAL, which is Hindalco Industries, joint venture between Hindalco Industries and Almex USA. So they have this plant in Aurangabad, which is the only plant, by the way, which can cast aerospace grade aluminum alloys. All other companies are not casting traditionally aerospace grade alloys. So HAL produces the best quality, that is the DC casting. If you recall my flow chart, DC casting is done here. Then there is Hindalco, which is capable of doing some further processing. There is Nalco. Nalco is virtually absent from any of the strong alloys. They are only there in pure aluminum and some of the low-end aluminum alloys. And there is Ordnance Factory Ambajari. They are the ordnance factory, which is the only ordnance factory which has the highest capacity extrusion plant. So before forging, normally billets have to be extruded and then forged. So the whole country depends on only Ordnance Factory Ambajari at present to make large extrusions. And DRDO and ISRO have been the key establishment involved in the development of aluminum. All the IITs and IIC have been there, but if you find any metallurgy department or materials department, you will find that a lot more people are working on aero engine materials, which are not produced in India right now, except the Russian engines which are produced under license. But hardly anybody is working on aluminum alloys, though aircrafts are produced in India. But hardly there is any research in aluminum alloys in the IITs and IISc. And to make it commercially viable, had the automotives been using or the railways been using aluminum alloys in large numbers, then the companies would invest and produce those alloys in large numbers. But currently the applications in railways as well as automotives of aluminum alloys are very low. And so now commercial viability of aluminum alloys production is very less. In spite of that, ADA has indigenized among this is total import, but the total indigenization is still less, needs to increase because of the thick products which cannot be produced within India. So some of the recent trends, this is a 2050 alloy, which is 5% lighter and 10% higher elastic modulus than the other 2000 and all the 7000 series alloys. It maintains an unrecrystallized grain structure at the surface, at the core, and midway between the surface and the core. Some difference in the grain size, but all of them are unrecrystallized as it is required. This alloy, ADA has picked up to be used to make thick bulkhead frames where the wings are attached and the landing gear is attached. They are strengthened by the precipitate called T1. You can see these thin plates. In all the three micrographs, you can see thin plates. They are not easy to observe under a transmission electron microscope. But recently we have seen these in the transmission electron microscope. And they have properties which are fairly consistent at the surface, at the central plane. And why this is important is because these plates are 165 millimeter thick. So the plate thickness is about 165 millimeter after rolling, and you need at least 10:1 reduction ratio in thickness. So imagine that the initial cast slab had to be 1 meter thick, which is a huge capital investment, and unless you have orders, it cannot be done again and again. So the properties are fairly good. Even the short transverse property, which is low, you get only 5% ductility in the short transverse direction. But that is better than the conventional 7000 alloys which give. They used to give only 2.5% ductility. So compared to that, this alloy is still better. So this is one development. Second development is now the computational materials engineering techniques have been used along with database modeling to come up with multiple options of compositions. And one such paper which has recently appeared in Nature Communications, they have shown that an alloy with yield strength greater than 800 MPa could be produced. The previous slide showed the yield strength of, why did I lose? Yeah. So the yield strength of, here you can see that is about 400 plus. But the yield strength of this computationally designed alloy is now more than 800 MPa. So there is actually hope to improve the strength further, and then it can replace some of the titanium alloys. Yeah, this is a thick bulkhead frame where those 2050 alloys could be used as a single plate rather than riveted multiple plates. And 7085 is another alloy which Alcoa is refusing to supply to India. They are refusing to even sell the patent to India. ADA tried to acquire the patent. They say no. And the patent is still live, so you cannot produce 7085. So for academic people, here is an opportunity to come up with an alloy equivalent to 7085 in terms of performance, but coming out of that patent regime and having your own patented composition. And this alloy is special because its properties do not deteriorate much, this 7085. You can see that the same property holds even up to 200 millimeter thick slab. So that's the advantage of it. And the last thing I'm showing here in this slide is that now people are also developing high temperature stable aluminum alloys. So take the fan, for example, or some of the early part of the compressor of the aero engine. If the aluminum alloys can withstand 300 degrees centigrade, then you can use aluminum to replace titanium. Or some of the backside of the engine coals can be in aluminum also in place of the beta titanium alloys. And some of the recent developments which have also come very, very recently, just 2 years back, they show that there have been alloys containing rare earth elements, not the expensive rare earth elements that were talked about in the morning, that is the neodymium, samarium, not those, but cerium and yttrium. So those are cheaper than Nd and Sm. So they could be used to produce alloys which are stable at 300 or 350 degrees, and then some of the titanium could be replaced. So by doing these developments, if you can increase the total volume requirement of aluminum alloys, then companies like Hindalco and Balco, they are ready to invest. But right now we are actually facing that problem of bridging that gap between the volumes required and what is commercially viable. So we need to set up an infrastructure which specifically caters to the requirements of aerospace and defense. Also, we need high purity aluminum. So Nalco, Balco, Hindalco, they don't routinely produce high purity aluminum because they say there is no requirement. They need to use a very special quality carbon electrode in the smelter, which they don't do because it's too expensive. And the R&D capabilities are very, very low. We need to expand those. And we can dream of supplying to the world. That will increase the commercial viability of production. So in other words, there is a tremendous potential to not only do R&D, I showed you some examples, high temperature aluminum alloys, computationally developed alloys, thick product development at a lab scale at least could be done. And there are companies, so we have the resources. India is one of the largest exporters of bauxite. So rather than selling bauxite, which is like selling mitti only, if you produce value-added aluminum alloys, then you can make a lot of money. And then, so a lot of aluminum resources exist, but how to build the capacity and volumes? Currently, the volumes are very, very low. And often the government sanctions, one day they say that it is being sanctioned, next day they are thinking of importing. So there is a lot of uncertainty. If the government takes some decisions and stick to them, I think then the companies can invest. Otherwise, for companies also, it becomes difficult for us to approach the companies and say that you invest in the money. Otherwise, they say that let the government invest in my plant and then I will produce everything. Even that can be thought of actually. But some consortium is required consortium mode is required, which involves academia and R&D. Somebody else has also spoken about it, and industries as partners. And some guaranteed requirements is what the companies are asking. And I was asking a friend of mine who did PhD with me, who worked with Alcoa for 35 years, that how did, say, Boeing, how did Alcoa develop 7085 alloy 300 millimeter thick product? So they said that it was the Boeing which gave a guarantee that if they develop alloy with those properties, they will buy it. So that's why they are not able to sell it to India, because they have told Boeing that they cannot sell it to anybody else. The whole development was done at the cost of Boeing. So it's a user agency in this case which has to pay for this kind of a niche products. And so that's the answer to my, the last question, who will fund? Either the government funds or the user gives a commitment over the next 10 years or so that I will buy so much of volume, and then the companies will invest one way or the other. But it has not happened yet. So in spite of lot of capability, lot of potential, we are not short of like rare earths or nickel and cobalt, lithium. We are not short of those. We have plenty of bauxite resources. We know how to produce aluminum. We know how to produce the alloys, but we are not producing aerospace quality aluminum alloys as of now. And very limited indigenization has been done so far, and a lot more can be done. Thank you. Thank you very much for giving this opportunity to me and present to you some thoughts on aerospace aluminum alloys. Thank you. Sorry I took more time.
Thank you, sir, for those valuable insights. Now, it is my privilege to introduce our next distinguished speaker, Dr. S. Senthil Kumar, who is a Senior Principal Scientist in the Surface Engineering Division at the National Aerospace Laboratories, CSIR, Bangalore. He also BE in Chemical Engineering from Bharatiya University, MTech in Ceramic Technology from Anna University, and a PhD in Materials Engineering from the Indian Institute of Science, Bangalore. He has worked at NIST Trivandrum, JNAR DDC Nagpur, CGCRI Kolkata, and has been with NAL since 2008. His research focuses on high-temperature electrochemical devices, nanomaterials, ceramic processing, plasma spray coatings, and space electronic packaging. He has transferred 5 technologies to industries, published more than 40 papers, 15 patents, 2 book chapters, 29 ICDD diffraction files, completed more than 15 R&D projects, and received several prestigious awards, including the CSIR-Raman Research Fellowship 2024 and Professor K.C. Patil Young Achievers Award 2023. Today, he will be delivering his talk on advanced electrochemical and thermal protection materials for next generation ground and aerial mobility. Welcome, sir. It is a privilege to have you with us.
Very good afternoon, everyone. Thanks for a nice introduction. So, first of all, I would like to thank the organizers for giving us this opportunity. So today, myself, I am from Surface Engineering Division of CSIR-NAL. So I may not be able to cover the entire NAL's R&D program. Of course, in NAL, there is a gamut of R&D program going on based mainly on the aerospace related, right from the materials, structures, propulsion, and controls, and also a lot of simulations and wind tunnel testings, those kind of programs. So I may not be in position to cover the entire thing. Today I'm going to cover our expertise on the electrochemicals and thermal protection materials for the next generation ground and aerial mobility, which we are developing by our group. That is at the Surface Engineering Division. So I'm going to split my talk into the 3 parts. The first part I'm going to cover on the fuel cells, mainly in the context of aerospace, which we are now, NAL is now initiated this work, and followed by some of our offshoot work, which we work for industries on this oxygen and NOx sensors, mainly for automobile applications, and followed by the high temperature thermal protection coatings for the gas turbine engines, mainly to increase the operational envelope and the efficiency of the engine. So as I told, CSIR-NAL is one of the premier lab for the aerospace R&D programs, And we at NAL mainly is surface engineering divisions, which are focusing on the coating technologies, coating materials, and the energy materials and systems. So fuel cells are nowadays commonly seen in the ground applications, that is in the vehicles, but there are also attempts now to explore for the aerial applications like aircraft and UAVs, so which I may be briefing in my presentation. So you may know this very well. These are the main problems are associated with these three. There is energy, waste management, environment. So whenever we are giving solution for one problem, we should not aggravate the other. So unless otherwise, the solution cannot be a sustainable one. So with this, I am moving forward for our fuel cell session. So nowadays you are commonly seeing the batteries in the road vehicles. Morning also we have seen our excellent talk how we are using these batteries in the cars and buses. But we should not forget the fact that batteries are an energy storage device. It's not an energy generation device. So, so when we are using batteries, there is also the possibility for the indirect emissions from the power source which is being used to charge these batteries. So we need to have an ultimate goal of getting rid of this kind of emission as well. So in that context, so a fuel cell can play a better role. And beyond that, batteries have many other challenges in the context of aerospace applications. Particularly when you are seeing the present batteries power density is far low for aerospace applications. Even morning, Dr. Shankar from Mahindra, he clearly explained that they were using this lithium phosphate based batteries. So wherein the power density there is somewhere around lesser than 150 watt-hour per kg. So that is the but aerospace applications requires very high power density batteries, particularly even for a hybrid aircraft system, that is the conventional and the batteries kind of thing. Even that requires more than 800 watt-hour kg kind of energy density. And if you want to go for all electric aircraft, still it is higher. That is even around 1800 watt-hour per kg. So these are the values which are very high from the present growth trend. So at least these are far exceeding this 15 years projection for the batteries, which stands at somewhere around 600 watt-hour per kg. So though the battery is having material in theoretical having the higher capacity to even 10 order of magnitude, which can store these energies, but when it comes to the system, including all the packages and electrolytes and collectors, drastically these power densities are getting reduced. So in that context, the fuel cell is one of the promising options which we can look. And there are also a lot of demonstrations in aerospace industries also. We are looking as aerospace industries, we are looking the fuel cells mainly for the auxiliary power units, which is will be in the rear end of the aircraft, mainly for the ground support and the cabin power requirements, and the low altitude aircraft propulsive power, high altitude long endurance aircrafts, and the ground support equipments and unmanned aerial vehicles. So these are the applications which we are looking into. So if at all you are going to use a hydrogen as a fuel, then there is no other device which can convert it effectively to harvest the energy. So if you are comparing the power density with the present state-of-art batteries, certainly its fuel cell stands tall. And also there are many other technology which is having very like solid oxide fuel cells in the cogeneration mode can even increase the efficiency up to 70%. But how to utilize these things in a mobility sector, that is the challenge now. So our CSIR also have brought out many initiatives to introduce these kind of fuel cells in the road applications like cars and buses. Our sister laboratory like SICRI and NCL Pune are already have demonstrated a fuel cell based bus and catamaran with the indigenous fuel cell technology developed in CSIR. So we at NL, we are mainly looking at solid oxide fuel cell technology and PEM-based fuel cell technology for the aerospace application, mainly due to the higher efficiency. So there are many examples and already the demonstration happens in this context across the globe. If you are seeing the PEM fuel cell way back in 2000, the power density is far lower, at least 3 times lower than the present scenario. But over the years, due to the improvement in the catalyst developments, these efficiencies are far increasing. That is at the rate of, it is doubling for every 5.4 years. And way back in March 2008 itself, Boeing have demonstrated two-seater aircraft, first manned aircraft with the fully powered by the fuel cell plane. And here the fuel cell engine is the main, and there is also a support battery unit. Mainly you need a higher power density during the takeoff and climb. For just to support at that place, there is an additional battery pack, but otherwise it is main pack is with the fuel cell. So when you are seeing this PEM fuel cell, it is having also a lot of potential for this APU, that is auxiliary power units. There are many labs across the world which are exploring this, like Sandia National Laboratory and Boeing, and even there are a lot of work happening at DLR and Lutford, Germany. So presently, I would say the batteries and fuel cell technologies are already matured to the level of propelling a small aircraft and UAV. So you can already see many UAVs flying with presently with fuel cells. And but for the fully large electric aircraft, suddenly there is a major technology breakthrough has to happen. If we are going by the present projection, at least we need, in the next 15 years, we need to realize more than 2 kWh per kg of fuel cells to go for all electric commercial size aircrafts. Whereas we are now standing at 400 Wh per kg. So now in the present context, UAV may be the better option, and these are all the aeropacks already giving the fully integrated systems, including the fuel cell storage. So this is fuel storage. Like if you are seeing this aeropack, it is also coming with sodium borohydride kind of fuel storage, where it can generate internally the hydrogen required for the flight. So there are many demonstrations already happening with these kind of aeropack. We at NAL also working on drones, we are developing our own fixed wing drones and the octocopter and all. And we are now introducing these kind of fuel cell pack in our systems. The main advantage of this kind of fuel cell pack is that if you are changing the battery pack to the fuel cell, you can see easily the endurance can go from 90 minutes to 180 minutes. So this is the kind of advantage we can get when we are going to the fuel cell based system. And also we have an ambitious plan to electrify our Hansa. That is, we are already, NAL is known for two-seater Hansa NG aircraft. Now we are planning to convert that into the electric aircraft platform. So we are already, first of its kind, we are in India, we are already establishing the ground test rig for this electric aircraft platform. This is of a 100 kilowatt electric engine ground tested facility. So when you are talking about fuel cell, we should also have to address the storage issues. So it is easy to talk that we can introduce hydrogen-based fuel cell, but the hydrogen with a very low volumetric density, power density, it becomes very hard to utilize in the aerospace industries. So we need to find an alternative how to match the energy density of hydrocarbon fuels, at the same time how to avoid the pollution. So in that context, the ammonia can play a very important role, because when it is combusted, it is going to give only the nitrogen and the water as a product. So in that context, the solid oxide fuel cell can play a major role, because this is the fuel cell which is flexible to the any types of fuels, including the ammonia and hydrocarbon fuels as well. And also this can also be used as a regenerative fuels. So in one side, due to the temperature, people are neglecting, but other side, due to the temperature, it is also having many benefits, that it can easily it can work in the reversible mode, that is in the hydrogen generation mode. In that way, it can also act as a regenerative fuel cell, that is just like your regenerative braking system. Whenever there is an opportunity, excess power or a reduction in the speed, you can harvest those in form of hydrogen fuel, and later you can utilize and use it in the fuel cell system. So this is also possible. So if you are seeing the specific power and power density, the SOFC is placed above the most of the fuel cells. And similarly, the specific energy and power density is very much favoring the particularly the mobility sector. Even it is better than the IC engine, provided the technology is yet to mature. That is the only thing we need to look into. So already there are demonstrations using these kind of solid oxide fuel cells in the UAV propulsion, like by Lockheed Martin. So and also this had a very good long endurance, 8+ hours, which is very crucial for the mission. So, but of course there are challenges. The present fuel cell technology is even heavier than the PEM fuel cells. So the technology is in the nascent stage. That is one thing we need to keep in mind. So we at NL, we are also developing our own fuel cell, right from a single cell level to the short stack, and we have demonstrated the performance part with the international standards. And whatever the required components for the fuel cells, like interconnect coatings, and the mesh coatings, everything is in-house developed indigenously. So we have also successfully developed the hydrocarbon compatible solid oxide fuel cells. So these are also can handle the hydrocarbon fuels like methane directly, so without compromising the performance majorly. So we have developed the unique type of catalyst which can handle this hydrocarbon. Otherwise, the normal nickel catalyst will get disintegrated while you are using the hydrocarbon. So, and we have, this is one type of fuel cell called electrolyte supported cell. Here the electrolyte supports is going to give the mechanical support. So we have developed these cells also in our lab, and demonstrated in both in the fuel cell mode and the reverse mode, keeping in the mind for utilizing the regenerative as a regenerative fuel cell. So these are the smart short stack technology which we have developed indigenously at our lab. So we have demonstrated it's in the fuel cell mode and the hydrogen generation mode also. And these are the various types of single cells, that is fuel single cells, which we are developing, that is already developed, that is electrolyte supported, anode supported, metal supported, hydrocarbon compatible fuel cells. All these are all indigenously developed at our lab. And we have also transferred some of our technologies to industries like carborundum universals, VB ceramics consultants, and Highland Power. And we are encouraging the MSMEs to produce these kind of advanced technology locally in India. And my next part of the presentation is the emission control sensors, which is the offshoot of our earlier solid oxide fuel cell technology. So here Presently, in order to combat the air pollution, India already leapfrogged from the Bharat stage 4 to stage 6 emission control norms. As per these norms, every two-wheeler has to come with the oxygen sensor. And the four-wheeler and heavy vehicles has to be installed with nitrogen, even NOx sensors for the onboard diagnostics. So these oxygen sensors can also work independently as well as along with the catalytic converter for efficiently control the emission. So once again, there are the different types of automobile oxygen sensor available in the market, like narrowband, wideband sensor, titanium sensors. So however, these chips, the basic chips are coming from imported. Only in India we are assembling this so far. So first time we have helped the industries to have our own sensor chips. So this is based on our earlier experience in the fabricating the space electronics substrates. So this narrowband sensor works based on the enhanced potential. That is based on the concentration difference, this potential will be developed. So this sensors uses the zirconia material. So we have developed a technology based on high temperature coated ceramic technology, packing technology. So for fabricating these sensors at the industrial scales. These are just like the PCB boards. It's a ceramic PCB boards, I would say. So first we will make tapes of ceramic tape materials, that is active materials like zirconia. Over that we will print the required circuits. So these sensors are integrated with different elements. I will show you here. So you can see it has a thick 830 micron sensing elements. It also have inbuilt this sensing layers, micro channels for taking the samples. Followed by the heater, that is for supporting the sensor operation at 800 degrees centigrade. This is how we are integrating these sensors with multiple layers. And for oxygen sensor, it's 11 layers, and we are producing it at industrial scale, and packaging and all developed for it. And you can see the sensor performance is par with the imported sensors. And we have tested this at ARI Pune, and these are the sensor performance details, and these are the sensor features of NAL sensors. And also next we also similarly we have developed a NOx sensors. Once again, the NOx sensor also used for the heavy vehicles. So here it's a next level of oxygen sensor. Here it has a multiple electrochemical cells. Each cell will have its own work. The first one will remove the freely available oxygen. Next one will strip out even the chemically adhered oxygen from the NOx. With this, we can able to measure how much NOx in the exhaust gas. So this technology also we have developed, and we have transferred to the industries. And now we have also helped them to set up the facilities, and now they have started producing indigenously in India. And the final part of my talk is on the thermal protection coatings. So being in aerospace industries, we are also working on this coatings for high temperature coatings for turbine blades. So the gas turbine blades will undergo many different types of erosion and corrosions. So in order to mitigate these things, it is essential to have the coatings which can confront these issues. So we have our own different types of coating facilities ranging from plasma to HPOF and cold spray technologies. For turbine blades, we are using the atmospheric plasma spray technologies, and we also have the high-speed combustor, which is state of art in it's established in NAL. So for testing these kind of coatings, and also we have our own facility for synthesizing the powder, whatever required for this kind of coatings. So our coating materials involves like doped zirconia and gadolinium doped zirconates, and there are also we are also closely working with our sister labs like SICRI for developing various type of materials. So the typical coating architecture looks like this. So that is over the superalloys there will be a bond coat over that thermally grown layer followed by the top coat for the functionality. So these are the highlights of our in-house developed TBC coating. So this is having a very low thermal conductivity, so that it have a very good insulation property to improve the operational envelope, and it has very good thermal cyclability and very low erosion rates. So these are some of the components which we have coated and demonstrated. So, and these coatings have demonstrated up to 120 degree centigrade the temperature drop. So our propulsion divisions are also working on the high intensity combustors. These high intensity combustors, naturally you will end up heating up the surfaces a lot. So it will have, in a small volume there will be a high heat generation. So that we need to protect these surfaces. So we are also helping them using these coatings so as to improve the combustor efficiency. So these are some of the experimental details where we have tested our coatings in the high-speed combustor, high-intensity combustor test facility. And nowadays the turbine blades also coming in the form of composite, that is SiC composites. We should not forget the fact that the SiCs are prone to the hydrolysis in the presence of high temperature steam. So in order to protect that, we need to come out with different types of coatings for these composite blades, like ytterbium silicates, ytterbium silicate based coatings. So with this, I would like to summarize that the batteries and fuel cells technologies are already mature enough for the UAVs and the small aircraft. So we are also in NAL focusing on integrated material research efforts to develop these kind of devices and realize these in the aircraft platform. And we are also establishing the India's first of its kind electric aircraft ground test facility. And also we are supporting many MSMEs. Of course, we are also happy to welcome academics also. Recent days we are also, our administration also allowing us to recruit more students for project works. And if you have any help regarding the projects, everything, you can always approach. And of course, our ex-scientist, our Omkar Hoble is here, so you can take help of him also. So this I would like to acknowledge our director. Thank you.
Thank you, sir, for your informative words. We would now like to present our esteemed speakers with a token of our appreciation. I request Vice Chancellor, sir, to do the honors. To Professor Amol Ananta Gokhale, please accept our token of our appreciation. To Dr. S. Senthil Kumar, sir, we present the memento of our gratitude. Not aware, sir. To Professor Amol Ananta Gokhale, please accept the token of our appreciation. Now, it is my honor to introduce our next distinguished speaker, Professor P.S. Robi, who had completed his BTech in Mechanical Engineering from Kerala University
MTech from NIFFT Ranchi, and PhD in Metallurgical Engineering and Material Science from IIT Bombay. He joined IIT Guwahati in 1997, where he served as professor, head of mechanical engineering, dean R&D, and deputy director with 38 years of research and 32 years of teaching experience. His research spans materials and manufacturing, including high temperature materials, high entropy alloys, laser processing, metal forming, fracture mechanics, hydrogen fuel production, and underwater technologies, completing more than 15 major sponsored projects, supervising 48 MTech and 16 PhD theses, and publishing more than 165 papers with 1 patent. He has been a member of boards of governors of IIT Guwahati and NIT Nagaland, faculty selection committees, DST PAC, and ANRF TPC MME Government of India. Today, he will be delivering his talk on recent trends and future of advanced materials for transportation. Welcome, sir. We are truly honored to have you with us today.
Next, back pointer. This is pointer. This is back. Good afternoon. Thank you for the nice introduction. I am from academics, so I thought I will just talk about rather than what I have done, but what we should be focusing for the next few years. What I had to, I plan to speak, Professor Gokhale has already talked about some of the aircraft materials, and in the morning also something has been talked, so there is not much for me to speak also. But I thought I will just give a brief idea about in what direction we should move for the next few years in the area of materials for transportation. It includes materials, and sometimes I may talk about the importance of manufacturing, because when it comes to manufacturing and materials are interlinked. So we cannot isolate this from the other, one from the other. So initially few slides I will talk about what is the existing materials in brief, and then I will talk about this one. I will try to finish it in maximum 30 minutes. Okay. So the current transportation materials represents a transitional engineering phase where conventional materials coexist with emerging advanced materials driven by safety, electrification, sustainability, and performance demands. And we know that transportation system includes automobiles, aircraft, rail vehicles, marine vehicles, new mobility platforms like maybe drones. Okay? So these are, and the requirements are different for many of the cases. Many materials are common also. So the materials engineering therefore has become the focus of attention in achieving efficiency, reliability, environmental compliance, and maintaining economic feasibility for large-scale production. When I was in IIT Bombay as a research scholar, I saw that in front of the workshop there was a very huge NC machine. Now that much space if you have, we can have a lab. So it was such a big, which came maybe somewhere in 1960s from Russia. Now the same performance can be done on a tabletop CNC machine, all because of the material development. Okay. So that is the thing. So, and efficiency increases, the reliability increases with the new materials, and the environmental compliance, because now that has become a very important thing. See, because by 2030, we have to reduce our emission, this one by 50%, and by 2060, India has committed that near zero emission we should achieve. So, of course, the solar is coming into picture, but that alone will not serve the purpose. We have to design new materials, manufacture new materials, for that new technologies has to be evolved. And the impetus for development of advanced materials for transportation is basically from the demand for fuel efficiency and the electric vehicle ranges, which is going to come up. So what I am going to talk is not about the past, not about the present, but the future, what is the aim of that, it will be there. The stringent emission and safety regulations is putting pressure. The need for lightweighting without loss of strength. So you have to have high strength, light material, high stiffness, and lightweight materials. So improved durability, comfort and intelligence, and finally the sustainability and recyclability requirements are the most important motivations. If you look at, as I said, a few cases I will talk about. The steel it dominates the transportation sector for maybe 7 to 8 decades, or maybe more. Basically because, and now also, it is the single most widely used material in automobiles and railways. It is the cheapest material, high strength, high stiffness, ease of fabrication, and well-established manufacturing infrastructure. That is the main reason for the steel. And today morning, you heard about the stainless steel, or the achievements which have been achieved in our country. But now, that conventional steel has been replaced by stainless steels or maybe newer materials like dual-phase steels. The trip and twist steels, that is a transformation-induced plasticity, and twin-induced plasticity steels. The retained austenite transformed to martensite during deformation, and whenever that happens, giving high strain hardening and excellent energy absorption. Then you have the high-strength low-alloy steels by microalloying with elements like niobium, vanadium, and titanium. You get a higher strength, good weldability, good toughness, and they are used mainly in frames and cross members and chassis applications. Then the newer class, the third generation high-strength steel, it is the quenching and partitioning steels and medium manganese steels. These are coming as a next generation electric vehicle body. So these are the developments in steel. So I am not going into too much details about this. And parallelly with the steel, you will see that aluminum alloys. The biggest advantage, which already the former speakers have already talked, lightweight, corrosion resistance, formability, and recyclability. And metallurgy is such a beautiful area that you can tailor the properties to get whatever you want. Okay, so that is one thing. And these aluminum alloys can be used in electrical vehicles, basically for the lightweight applications. In automobiles, in high-speed trains it is being used nowadays. Earlier in trains it was not used, but nowadays it started using, as well as extensively in aircraft structures. These are some of the alloys which Professor Gokhale has already discussed. The aluminum, copper, lithium alloy, that is 2195. 3000 aluminum series, which is used for marine applications, even 5000 also used for marine applications. 2000 series and 6000 and 7000 are precipitation hardenable, high strength materials. Any alloy which has a yield strength more than 90 KSI is considered as a high strength material. So these 2000, 6000, 7000 series are considered as high strength aluminum alloys. So the metallurgy part has already been discussed. Now this magnesium, its density is nearly 1/4 of that of steel and 2/3 that of aluminum alloys, is a very important material for high strength, high specific strength and stiffness materials, used in weight reduction, vibration damping, and good castability. But the major challenge is poor corrosion and creep resistance and high manufacturing cost. And to my knowledge, only very few sectors are working on magnesium alloys in India. Not too much of industries are working on magnesium alloys. That is another thing. And I am not sure, other than maybe HAL is working or not, I don't know, but ISRO there is some work on magnesium alloys. Others, whether they are working on that, I am not sure about it. The corrosion property, poor corrosion resistance is the major impediment in the application of magnesium alloys. But recently some materials on ZK series, that is zinc zirconium magnesium alloys, magnesium zinc zirconium alloys. When it is microalloyed with the calcium, it has shown very good corrosion resistance, very, very high corrosion resistance. But mechanical properties has not been reported, and some work is going on in India also. Okay, so that hopefully, if that is a success for, without compromising on the mechanical properties, when you are microalloying, that means less than 1% of calcium is the microalloying element, and if it is giving so much excellent corrosion resistance properties, naturally it is going to supersede all other materials. That is what I hope. Okay, so these are some of the series of magnesium alloys: aluminum, magnesium aluminum zinc alloys used for automotive transmission housings, steering wheels, instrument panel support, and so and so. Aluminum, magnesium aluminum manganese alloys, superior energy absorption and impact resistance for vibration damping. This is being used. Steering wheels, seat structures, and instrument panel beams and crashworthiness. ZK series, high strength and good fatigue resistance used in aerospace and high performance transportation applications. And AE series, that is a rare earth, magnesium aluminum rare earth alloys, improved creep resistance, and used in powertrain components like transmission cases and engine related housings. So then you have the fiber reinforced composite materials. Extensive work on this has been carried out in ISRO, NAL, and you will find that the high specific strength, stiffness, corrosion resistance, fatigue durability, and significant weight reductions are possible with these materials. You have the GRPF, CRPF, then armored fiber composites for the radomes and ballistic protection panels, where impact resistance and toughness are very important for this. You use this armored fiber composites. And ceramic matrix composites are increasingly used in aircraft engines and thermal protection systems. So in automotive applications, the trend is the rapid growth of thermoplastic composite, and the composites are expanding from the role of high performance to a broader market. Nowadays it is expanding, so thermoplastic, because it can be recycled. That is the major advantage of that. Then you have the advanced polymer materials. These are also being used, not for structural purpose, but for corrosion resistance and many other applications. See, which includes the polyamides, PEEK, then PPS system, PP, and ABS plastics. Then you have the elastometers, where EPDM and TPU are being used extensively in both aircraft applications, even in railways, even in automobiles. These are being used. And ceramic-based materials. So oxide ceramics are there, non-oxide ceramics are there, CMCs for aerospace turbine components, and function and electronic ceramics. This is one major area which is now coming up, and in future we have to go for that. With the PZT, the ferrites and dielectric ceramics and solid electrolytes, these functional electronic ceramic materials are there. Now, these are what are already existing. Let us come to that. What are the requirements for new materials? Now, when you are going in future, the materials which should cater to the need for EVs, that is the most important thing. And what is important for that is the lightweight, because the battery itself is very costly. So if you are adding a battery, because recently, I was just looking at it, we were trying to buy one battery for our underwater vehicle, and that battery is costing something around 40 kg or 50 kg. So if one battery is costing like that, you can imagine for an EV how much it will be taking. So you have to reduce the weight. Then another is multi-material design, and better thermal management and electrical insulation is very important for EVs, because a lot of heat is being generated. You have to dissipate that heat. And you have the sustainable and circular materials are the future materials which are going to be there. because energy norms and other things are of much importance. New manufacturing technologies has to be evolved, and introduction of functional and smart materials will come, so that at the end, maybe from 15 to 20 years from here, the material, the vehicle itself will act in different purposes. So let us see that. The electrification-driven materials, the emerging material needs are high energy density battery materials. This is the most important, where lot of efforts is there and scientists are concentrating their effort on that. Thermal management materials are required. Whatever heat is generated, it has to be dissipated. Even if it is for a small semiconductor device or maybe computer panels also, this is very important. So battery also is a very important thing. And electrical insulation and safety materials are required. The challenges are fire safety protection, fast charging, heat dissipation, battery enclosure and crash resistance. And the important developments which are there are solid-state battery cathode materials under industrial development, reduced cobalt rare earth dependence, advanced copper, nickel and lithium chemistries. So basically, if you look at for battery materials, the cathodes which are there to be developed are nickel manganese cobalt oxides and lithium iron phosphate materials, which you have to work too much on that. The anodes are graphite and silicon based, which are already existing, and new electrolytes like liquid and solid state electrolytes are to be developed. In the motor, the power electronics, you want the permanent magnets. Of course, it is not in our control because neodymium, we don't have the source of neodymium. Though rare earth is there, but I don't think we have neodymium in India. We have to either depend upon China or on Brazil. Electrical steel, see, after so many decades, we are using extensively electrical machines, transformer, armatures and other things. But for each and everything, the electrical grade steel we have to import. In India, it is not manufactured. The grain-oriented electrical grade steel, silicon steel, is not manufactured in India. And I think it is high time we have to develop that technology and concentrate on that. Otherwise, no, always depending upon other countries will be a problem, because you know that today what is the relationship with other country, and tomorrow what will happen, we don't know. So this electrical grade steel is very much important, and these battery materials, motor and power electronics, you will see that it gives higher efficiency and driving ranges. Next is the sustainable and circular materials. So sustainable and circular materials is the result of, say, maybe the climatic change, concerns related to climatic change, the resource depletion, the environmental regulations. As I mentioned, we are committed to zero NOx conditions and life cycle cost optimization. These are the things. So you have to have either sustainable materials or circular materials. The difference is not much. So between these two, sustainable materials are those that minimize environmental impact throughout their life cycle, whereas the circular materials remain in continuous use through reuse, repair, manufacturing, and recycling. So that is the thing. So these two things are very important. So we have to design the materials which are sustainable, and at the same time either it is sustainable or circular materials. So example includes fully recyclable thermoplastic composites. We can use it. May not be for the same purpose, but for other purpose we can use it. The modular components, prepare the modular components. And then, so that entire thing you don't have to replace, only that particular module remove. And the materials specifically engineered for repeated recycling cycles you develop. The main goal is elimination of waste and closed material loops. So the major directions in sustainable and circular materials are recycled aluminum and polymers. See, even low quality waste aluminum can be used for hydrogen generation. One of my students has done it. He designed a small reactor and made a in situ hydrogen generation as per our need, we can have it. And then he used for firing a sintering furnace. So those type things can be developed. Maybe you can use it for automobile application also for firing a hydrogen engine, where too much of storage of hydrogen is not required. Only as per your demand only you prepare it. So that is the advantage of that. So by using low quality waste aluminum, aluminum waste, you don't have to go for high. But people may ask a question for aluminum, production of aluminum itself is a energy intensive process. But waste aluminum is not energy intensive, that is what we will say. But you can satisfy the NOx terms actually. So that is another thing. Development of bio-based plastics so that environmental degradation is minimum. Closed loop material cycles, battery recycling and recovery. See, if you look at the automakers increasingly integrate recycled materials into interiors or structures and battery casings. And battery recycling systems can cover nearly 95 to 98% of valuable metals, so enabling the circular supply chains. The high temperature and extreme environment materials, titanium and nickel-based superalloys. Nickel-based superalloys has almost reached a saturation. Now new techniques are developing. The air cooling blades, thermal barrier coating. See, thermal barrier coating, there is another problem. You have two interface coming. One is the metal substrate and the bond to coat interface, then bond to coat and the ceramic coat, basically because the substrate and the ceramic materials compatibility is not there, especially when you are heating it from room temperature to the high temperature, the expansion is different. So it develops cracks at the interface. But now the recent metal-based, say, high entropy alloys, and high entropy alloys, if you look, it is very costly, but you can use it as a thermal barrier coating. In one of the high entropy alloys which showed excellent, very high properties, the 90% of the strength was retained, room temperature strength was retained even at 1200 degrees centigrade at Guwahati itself. And when you try to study further, what happened, the compression platen itself broke. So the strength was so high. So that, since it is metallic, the compatibility, the differential thermal expansion, that difference will get reduced. So you can avoid these multiple interfaces. You can allow the metal to diffuse into that, so that a diffused interface will be there, by which you can have a very good compatibility. So that is one thing for the ceramic barrier, thermal barrier coating. Then lightning resistant hybrid composites are there, which can come. So the wear resistant thermal barrier, okay, this is what I have already mentioned. Now the most important thing is the smart and functional materials, self-sensing composites, the piezoelectric materials which are used for, now we can develop it for energy harvesting. It can be used in most of the transportation system. So whether it be marine environment, if you have that patch of piezoelectric patch on the ship body itself, when it moves, so energy harvesting can be done with that because of the pressure which is exerted on the body, you can have it, and so those type things can be there. Even on aircraft wings also you can have this patch, or I don't know, in automobiles also one has to look at it. So that is what shape memory alloys, piezoelectric materials and MR fluids finds a lot of applications. Self-sensing composite, the embedded sensors and structure is one hot topic which one can concentrate, and smart fabrics and adaptive surfaces. These are, you will find the application adaptive suspension system, sensors and actuators, vibration and noise control. So these, some of the advantages will be there. And of course, nanomaterials and nano-engineered structures, where morning you have given a very good topic about that, a talk about it. Enhanced mechanical and thermal and barrier properties are there. Multifunctionality, machine learning designed nanostructures are achieving extremely high strength to weight ratios now. The manufacturing and digital materials engineering, see, when you talk about the materials, if you look at the history, you will say that materials revolutionized the industrial sector. The nickel-based superalloy history, if you look at it, first materials were developed, then to improve the properties, processes were developed. And then once certain processes were developed, again the new materials came into picture. So initially, the wrought nickel-based superalloys, nickel-chromium alloys were there. Then you came out with investment casting. Then you got the castable, in that the cast alloys, nickel-based alloys were developed. To improve the properties further, what happened? The directional solidified castings, that technique was developed. And then to improve further, you developed the material single crystal casting, and the single crystal casting technology was also developed. So this material development and manufacturing always will go hand in hand. So that is why I said initially, you cannot isolate one from the other. So with the new materials developing, new techniques also will evolve. So that is one thing. The thin strip casting technology is one method. 20 years back I worked on it, but we were not having very high this one. We worked on aluminum alloys, where we could get around 1 millimeter thick strips, a continuous melting. Maybe now Jindal should look into that, okay, for making stainless steel, or maybe even you can make nickel-based superalloy sheets. 718 alloys you can make out of that by thin strip casting. Why? The reason is that you have a molten material, maybe steel, suppose let us say molten steel, to convert that into, say, to a thin sheet of say 1 mm or 2 mm or maybe 1.5 mm thick or 0.5 mm thick. It involves almost around 32 different processes. Professor has shown for aluminum alloys how it was done. But if you look at the steel for obtaining thin sheets, and this, for example, the first thing is that you pour it into an ingot and cool it, a lot of energy is lost. Take it out, clean the surface, top discard, bottom discard in the ingot, that is the thing. And then do the cogging operation, which is also energy intensive process. Material also is lost when you have the top discard and bottom discard. Grinding of the surface. Then you do the cogging, hot forging is done. And then after a few operations, you have to again reheat it, otherwise it will become hardened. And when you reheat it again, you have to do the cleaning process, all those things. So like that, finally the rolling operation comes, hot rolling and finally cold rolling, and almost 32 different operations are there, continuous operations. Somewhere in the line, it gets stuck, the whole process is stopped. And all these processes are energy intensive, labor intensive. So, but if you can convert that molten metal from that molten metal stage to thin strip, thin sheet, so all these things can be, so much of energy can be saved, so much of labor charges can be saved. So that is one advantage with the thin strip casting technology. And lot of computational work has been done, even in my department, even my students are also doing that to get the thin strip casting. But if you do for special materials, that will be a big advantage. So the industries have to come forward it. What happened? Then topology optimized structures, 3D printed metal components. These are the future areas in manufacturing where you have to concentrate. Digital twins for materials design, simulation-driven alloy development and manufacturing. This is a very important thing. If you look at 20 years back in India, a metallurgist, he will not do any computational work. Okay, computational work is done by mechanical engineering. He will not knowing about the microstructure. This was one major problem, but now things have changed. Now in mechanical engineering, the faculties and students are forced to learn microstructure, the structural property correlation, and the effect of the processing technique on the structure and property. So that is a very good thing. So this simulation and driven alloy development and simulation driven manufacturing technique, so where one can concentrate, and in India we have enough candidates to do that. Both MTech and PhD level, even BTech level also, people are capable of doing it. The benefits are saving in materials, energy and labor, and complex geometries can be saved, and faster development cycles. By this, you can avoid all the experimental trials by optimizing this processing manufacturing techniques, parameters. Okay, that is one advantage of this. Then multi-material design philosophy. The philosophy is linked to electrification and energy efficiency. Lighter vehicles require less energy for propulsion and produce lower emissions. Support sustainability by recyclable metals to coexist with the durable composites and functional materials designed for longer life. Modern joining technologies such as adhesive bonding, friction stir welding. You can join two dissimilar materials by this friction stir welding, and hybrid fastening methods. And by this method, you can have a component with the steel, aluminum, composites, and polymer into a single component. And the right material in the right place is the strategy in this. So the material roadmap, in my opinion, for transportation is the driving forces are basically net zero carbon mobility. So that is one important thing where transport contributes a major share of global CO2 emission. When in use itself, the material can harvest the energy. That is another advantage. Then electrification, hydrogen propulsion, and sustainable fuels demand new materials. Lightweighting remains the most universal strategy for energy reduction, because lighter the material, the lower the fuel consumption. And lower the fuel consumption, the lower the pollution. Okay? Then EVs by 2050, it increases the demand for battery materials such as lithium, nickel, and manganese. The recycled metals and polymers become mandatory design criteria, and battery recycling is expected to become a primary raw material source. The electric vertical takeoff vehicles, it requires around 40 to 50% weight reduction compared to conventional systems. And the digital and AI-driven materials design, machine learning reduces the material development by 50 to 60%. Now this AI technique is known to almost every educational institute also. That is what I feel. So the technology roadmap is the third generation ultra high strength steel with a yield strength of more than 1400 MPa, maybe in another 10 to 15 years. As mentioned earlier by Professor Gokhale, the large structural aluminum casting manufacturing is one where we have to concentrate our attention. And now the composite manufacturing is limited to small scale manufacturing only. So high volume composite manufacturing by automation is something which one has to concentrate it. Then development of hybrid metal polymer vehicle structures. Then multi-material architectures become standard vehicle platform. So impact will be 25 to 35% of vehicle mass reduction will be there, and improved EV range and payload efficiency, because before long this EV is going to replace all other types of vehicles. So that you have to keep it in mind and concentrate on that. Okay, this already I have been mentioned. Now, hydrogen mobility introduces new metallurgical challenges. See, if you keep this hydrogen in a hydrogen cylinder for 2 months and then look at it, after that you will find there is no hydrogen in it because it diffuses through the cylinder material, steel itself. The hydrogen atomic diameter is very less and it can come through the interstitial site and come out of that. And maybe instead of inside the cylinder, if it is kept in a closed godown, you will find a lot of hydrogen is in the godown. So that is one risky factor. Then cryogenic composites has to be developed. Ceramic matrix composite for high thermal applications has to be developed. Hydrogen compatible polymers, if you can develop so that it can reduce lot of reduce the weight. And this hydrogen causes embrittlement in steel itself. Hydrogen flaking, it will come. It will form a flake and then finally, so even in steel also, if you don't remove the molten metal, the steel, hydrogen from the molten metal, after some time it will start diffusing and form, concentrating on some area and then flakes will form and then it will develop cracks. So applications are hydrogen aircraft, automobile also we can concentrate, fuel cell trucks and ships, long range aviation. Hydrogen aviation material markets are projected to grow rapidly due to cryogenic storage needs. So vehicles should be designed for complete recyclability, material traceability, closed-loop manufacturing, recycled aluminum, polymers and battery metal dominate supply chains. So in hydrogen, the major thing is hydrogen embrittlement resistance material has to be developed. That is one major challenge. Though people were working on it for the last 30, 40 years, it has not been a success. And fast, low energy recycling technologies should be developed. Affordable mass production of, I think this I have mentioned. So transportation materials evolved from structure plus protection to structure plus energy plus intelligence plus sustainability. And future transportation materials, that materials become an energy storage device, it becomes a sensor, thermal system and recyclable resources all into one. So maybe another 20 years or 25 years that is going to happen. So the summary is the future roadmap for material in transportation in another 2 decades reflects a convergence of lightweight structural engineering, advanced energy materials, hydrogen compatibility, intelligent functionality and sustainability. The materials engineer of the future will work at the intersection of metallurgy, electrochemistry, polymer science, data science and manufacturing technology, a multidisciplinary area. Okay? And the ultimate vision should be a transportation system composed of lightweight, energy efficient, self-monitoring and fully recyclable material system that enables safe, sustainable and intelligent mobility for carbon neutral world. Hearing it may be good, but we have to make it practicable. Thank you very much. Any questions? Yeah. That can you sit it on? Or I will come here.
Yeah, so very thorough description of what materials exist, what could be future for this. And as I earlier said, I believe fully in, nanostructure materials and nanotechnology playing an important role in design of materials or interfacing, as you said, also metal, plastic, and others. And I talked about self-healing materials. Another direction which we are taking, which is a stimuli-responsive, transformable materials that can change the shape or change the surface characteristic, and applying this, and I think that that could also play a very important role in advancing materials for transportation or aviation.
Okay. Transforming materials, yeah.
So one example could be very easily changing the surface.
Okay.
Addition properties that can play very important dynamically, reversibly.
Yeah. Thank you.
Thank you.
Thank you, sir, for sharing your valuable insights and experiences with us today. Now, it is my honor to introduce our next distinguished speaker, Professor P. Chakraborty, who is a former professor of electronic engineering, IIT BHU, and former director of MNNIT Allahabad 2011 to 2016 and IIEST Shibpur 2018 to 2024. He made significant contributions to microelectronics and photonics, founding and coordinating research centers including CRME, MEMS, CIR, and CMDR, and supervising 23 PhD students, including international scholars. He has published 350 plus papers, authored 4 textbooks, edited 6 books, and holds 4 patents, and has delivered numerous keynotes and invited talks internationally while serving on editorial board and as a reviewer of leading journals. He is a fellow of International Institute of Engineers, senior member of IEEE, and recipient of INSA, SERC, DST Fellowships, MIT Academic Excellence Award 2015, and MRSI Distinguished Lectureship 2019-20. Today, he will be delivering his talk on organic semiconductors for smart transportation systems. Welcome, sir. We eagerly look forward for your insights.
Hello. Yeah.
Next, back, pointer.
This is? Next.
Back.
Back.
Pointer.
Point. Good afternoon. And at the very onset, I'd like to thank Gati Shakti Vishwavidyalaya, particularly Honorable Vice Chancellor and Dr. Jyoti Sharma, who actually contacted me in the beginning to deliver a lecture here. So I was thinking that let me talk on something where this semiconductors play a role in the future generation, because from morning you're listening to a series of lectures from people from industry as well as from academia, and speaking mostly on materials. But let me admit in the beginning that I am not a material scientist. I am a hardcore electronics engineer. So I have been using materials, different kinds of materials for developing electronic devices, right, which are used for variety of purposes. So initially I thought that the talk will be of 1 hour duration or so. So while organizing these slides for the presentation, I just sent you a message asking that what is the time slot given. She said 20 minutes. Then I said, oh, I have a huge number of slides, so which I'll have to cut short so that I can fit into 20-minute slot. That's very difficult, you know. But anyway, so I had to remove many of the slides. So during the presentation, you may find some charts suddenly because I had to cut and remove some slides so that I can conclude within this time frame. So I'll not talk deep into the research because the audience is from different areas. So technologically, I'll not dive deep into this, but I'll like to share that my experiences as a researcher in this area, and I have seen the changes because all of you are seeing the changes. Many of you are born and you have seen a lot of technologies coming which we have never seen. So the computer which I used first had a hard disk of 40 MB capacity and the size was this much big. So now you can imagine that a pen drive you are carrying, so you have gigabytes of your storage there. So this kind of technological changes, but we have seen that change occurring. So we are fortunate in one way to see the technological changes which has happened over the years. So I have shared my experiences as a researcher, and we are talking from morning, and for last 3 or 4 decades we are listening that we are saying that there is a gap between the industry and the university, and those who work in the universities, we know our problems and our limitations, right? And industry also, and in recent years, India has actually entered into the manufacturing sector in a big way. It was not happening earlier, right? And most of the time the technology used to be transferred. So that way, we blamed each other in one way, the university blaming the industry is not coming forward, or they are blaming that academics, they are doing research within the lab only, nothing is coming out. So that gap continues still, but gap is reducing, I believe. And now let me share my experiences. So this will be my outline of my talk. So a small introduction, then advanced materials for smart transportation system. So which are the materials which are going to be used in the coming smart transportation system. Then I'll talk of organic semiconductors. Today I've chosen that topic, that flexible materials, which is called also plastic devices or plastic electronics. I'll be talking about this, why we are interested in these plastic materials for electronics application. And then I'll talk about these few organic devices which we have developed in the lab. My switching over to organic devices was because of some compulsions, I'll say, because the kind of facilities you require to work in conventional electronic circuits like silicon or your 3-5 materials, you require an extensive investment in terms of laboratory, creating the laboratory facilities, which are not always available everywhere. So it was one of my compulsions coming into organic semiconductor. But when I started doing work in this area, I found that enormous potential is there in these organic materials. So then what are the future scope and the challenges? I'll see, and some concluding remarks. So what is this smart transportation system? Let us see that what we are heading for is something not what we see today, but something which is coming that says, for example, smart delivery system. So which will be a pilotless, driverless delivery system, right? We'll be having this driverless car, as you see, smart signaling system. Then we'll have this high-speed trains, these infrastructures, roadways, etc. Then the hyperloop trains, the vacuum train which is going to come. Then driverless or pilotless aircrafts. Today you imagine that you board the flight and then your pilot welcomes you on board and says that today I'm working from home. So you sit and relax, what will be your condition, right? So that situation is going to come very soon, that where there will be no pilot, right? Aircrafts will be pilotless. And there will be a system where the content distribution will be there in real time, which will talk about the road conditions, your weather condition, everything, all information you'll get for your booking, reservation, in all of this that can be done. So prospective materials for this, you have from the morning you have heard about lot of materials which are being discussed and they are being used. And my focus in this talk particularly will be on electronic materials, right? Materials which will be used for making electronic devices, which will be mostly used for different kinds of sensors, display devices, and others. So advanced composite material, we are talking of lightweight materials, so that is one part. Carbon reinforced fiber, polymers are there, advanced composite materials are there. Then you have smart and adaptive materials, self-healing materials, smart glass with switchable glazing, that you are already being used in aircrafts now, that you press the button and your transparency, that changes of the glass by applying a voltage there. So these are already in applications. Then intelligent and functional materials such as smart concrete or bricks, which will be, there will be embedded fibers inside this and various kinds of sensor that will monitor the health of these road conditions or bridge conditions, all these things will be monitored. And semiconducting materials for electrification, sensor design, conducting polymers and battery materials. Now, organic semiconductors, key advantages. Before coming to this, let us see that what is the situation, why we are coming to organic materials, and what is this semiconductor. Primarily the materials, as you know, that initially the materials were germanium and silicon. That these are two primary materials which were used. Imagine that when the first transistor was invented in 1947, right? Shockley, Bardeen and Bratton, they made this first transistor. And that time the device was made on using germanium. Then there are a lot of issues with germanium, and finally people switched over to silicon. And the advantage of silicon is that silicon is very low cost material and abundantly available in nature, right? And right from sand, it enters into your CPU or your mobile chip, right? That comes directly from sand by purification, and multiple steps are there. So silicon has been widely used in making your electronic devices and systems. And today also, silicon rules the entire semiconductor industry, even today. And there was a time we had limitations, particularly in making electronic devices. The limitation was that limited materials, number of materials were available with us, right? And then given that material, you'll have to make a device. But over a period of time, we found that we can design the material, we can tailor the property of the materials. So this gives enormous flexibility in terms of design of new electronic devices. Because if you can tailor the property of the material, you can have lot of other devices. Because when you use, say, silicon, for example, its band gap is 1.1 electron volt, fixed. You cannot change it, right? So whatever you want to make out of this, you'll have to make. Or for example, that silicon is an indirect band gap material, cannot emit light, so silicon cannot be used for making a laser source or for a light emitting diode. This kind of devices you cannot make out of silicon, right? Then other materials came into picture, that 3,5 materials, 2,6 materials, 4,4 materials, and people started working with these materials and started making new devices. So this is one part. These are all inorganic semiconductors, and all electronic circuits were based on these inorganic semiconductors in the beginning, right? Then, but the technology of this semiconductor making these devices is very expensive. So you need a very, very sophisticated lab with clean room facility to develop these semiconductor devices, right? But reliability, if you come in terms of reliability, the reliability of silicon cannot be compared. Silicon devices or even 3-5 semiconductor devices cannot be compared with any other kind of oxide semiconductors or even these organic semiconductors at all. So the purpose is totally different. That thing we should understand, that these new generation materials, particularly these organic semiconductors, most of the cases it will complement this what is provided by silicon, but it is not going to replace silicon. That is one thing must be clearly understood. Why we go for organic semiconductors is the flexibility and conformability onto curved surfaces, right? So, like your vehicle dashboard you can use, windshield you can use. It is lightweight, and for large area application, particularly for display purposes, and like sensor array and solar panels also, these materials can be used. They are low cost, and the temperature, low temperature processing is possible. As I told you that both 3-5 materials as well as silicon needs your very good infrastructure, facility, lab facility for developing this. But these devices using these organic semiconductors can be made at a very low cost, and at low temperature processing can be done, and scaling up can be done also very easily. And low power consumption and energy harvesting also, these organic semiconductors are used. So some of the specific applications of these organic semiconductors, and many of these devices we have also fabricated in the lab and tested. And problems with these devices also I'll tell you. So flexible display and OLED, these days you have seen that many of you are using your mobile phones and your televisions without knowing that these are really organic LEDs, OLEDs are used. So most of the TV, your LG, Samsung, everybody is now started using these organic LED displays rather than conventional LEDs. So for vehicle, this is very, because you can bend it also. So now the situation has come where you can just roll this television screen like a drawing sheet, right? And your mobile will be something which you can fold like a piece of paper and put it into pocket. And so that stretchability of this is a unique feature, right? That makes them very attractive for application, particularly in vehicles. Then organic photodetectors for wireless optical communication, vehicle to vehicle or vehicle to everything. We can communicate because it is the age of Internet of Things or Internet of Everything, right? So vehicle to anything, these organic photodetectors can be used. Organic photovoltaic cells can be used for energy harvesting, particularly I said large area applications, say the rooftop of your car, vehicle or train, everywhere you can mount this photovoltaic arrays, the solar cell arrays there at the top. So they can produce, they can do this energy harvesting. And organic thin film transistors, OTFT, we have designed a couple of OTFT, organic thin film transistors, and we have used this organic thin film transistors for driving OLED circuits, OLED drivers. We have made conventional electronic circuits like electronic oscillators using this OTFT or OFT, organic field effect transistor or organic thin film transistor, same thing, but they have different structures. So we have fabricated this device, used it for making an oscillator, and we have used this device for sensing ammonia gas also and hydrogen also. And we have made some organic, inorganic hybrid devices also, because I said that silicon cannot be replaced. You can add these organic materials to silicon to increase the functionality, enhance the functionality of the silicon. So these are some of these practical OTs and these flexible devices. These are the application areas where you can use this for personalized security system. Then printable organic circuits, organic solar cell, organic wearables, then organic laser sources, organic memories. These are the areas where these organic semiconductors are being used. And all of these will be important for your transportation systems. So let us see that the history of these semiconductors, organic semiconductors, because semiconductor used to mean inorganic by default earlier. So in 60s, the first studies of dark photoconductivity of anthracene crystal was reported. That was in 60s. In 70s, the synthesis and controlled doping of semiconducting polymer was demonstrated by Shirakawa et al. In Tokyo Institute of Technology. And that's the starting of your, in organized manner, people started working on this organic polymers for electronic applications. So in 80s onwards, organic semiconductor polymers like polyaniline, polythiophene, PPB, PFO, so different types of organic polymers are used for making electronic devices. So two major classes are there. One is the low molecular weight material, and where we mostly use the film deposited by sublimation or deposition by evaporation. These are the two methods. And in conjugated polymers, we deposit the film by sol gel method, the chemical route, or we can use that electrochemical workstation for doing that also. And these are the chemical structure. I told you I'm not a material scientist or a chemistry guy, so these are some of these structures of these organic or molecular structures of these semiconducting materials. So nature of bonding, if you, those who have studied inorganic semiconductors know that silicon forms covalent bond, and there you can change the conductivity by adding some extraneous element, group 5 or group 3, to control the conductivity of this silicon. And sp2 orbital hybridization is there, and in the case of organic semiconductors, you have a sigma bond and an orthogonal pi bonding, and your conductivity is because of this p orbital pi bonding here, which is orthogonal to the plane of this. This actually gives the backbone, this covalent bonds, take them together, and this is responsible for the electrical conductivity in organic semiconductors. So this is an example of a simple bonding in ethane, where you have two kinds of bonding and anti-bonding which are creating, and you have between the pi and pi conjugate, this you have optical excitation. One of the biggest advantage of using these organic materials, particularly for OLED application, is that you can get colors out of this material which are more close to the natural colors, which you cannot get with inorganic semiconductors. That's why OLEDs are so popular as display devices. So this is what I said, that this kind of conduction mechanism in organic semiconductor is quite different from which happens in inorganic semiconductors. So this I'll not get into this, that mechanism of operation of this. So in normally your inorganic semiconductors, we have a concept of valence band and conduction band. We measure the energy gap, the band gap Eg. In case of organic semiconductor, the edge of the valence band is called the highest occupied molecular orbital HOMO, and the edge of the conduction band is called the lowest unoccupied molecular orbital LUMO. Right? This is the difference between HOMO and LUMO, is the band gap energy. So existence of well-defined spin states in organic semiconductor in the form of singlet or triplet, like isolated molecules, leads to interesting optical properties of these organic semiconductors. Another difference with inorganic semiconductors that here it is free charge carriers are not created, here excitons are created, where you require some amount of energy to break this and convert them into free charge carriers. So band transport, there are two major mechanisms of charge transport. One is band transport, which is observed in highly pure molecular crystal and is dominant at low temperature, but relatively higher mobility is found in band transport, whereas in hopping transport between this in the molecular chain, you'll find that mostly in amorphous organic solids, the mobility is usually very, very low and the transport process is very slow. So organic semiconductor for a smarter tomorrow, that organic materials have the potential to build devices with flexibility and stretchability, right? That's why it is sometimes called soft electronics or plastic electronics also. And OLED-based display system will have a major share of this global display market. And organic electronic gadgets can often be folded like map assembly, already told you. And devices made with organic electronics are compatible with biological systems. So it will have a lot of applications in human health care. And it is sustainable also. Organic electronic devices do things that silicon-based electronics cannot do. One, I told you that large area, when it comes to large area. And organic electronics are more energy efficient and eco-friendly. But don't think that all these organic materials can be disposed easily or they are all biodegradable. It is not like that. And organic electronic devices can be manufactured using more resource friendly. This is the most important part, that you don't require a very sophisticated lab for making these devices, right? And not that high temperature processing also is needed, or a very high clean room also is not needed. So in normal LEDs, you need a backlight for this normal display devices, but OLED generates their own backlight. This is one advantage, and the thin film transistor which you use can be made also by organic. So the driver circuit for these OLEDs can be made using your organic materials. So that's the advantage. And OLEDs are already commercialized, I have already mentioned that. And organic thin film transistor, you know that what you use in normally your CPU chips is based on MOS circuits, right, which is based on silicon. So that MOS technology is used, and the advantage is that your packing density is very high, right? So you, in a stamp size IC, you can have trillions of transistors there. So that kind of thing you cannot expect in your organic devices. So if it comes to making discrete devices, or sensors, or sometimes sensor array, this can be used. So, but if you think of making a CPU chip using organic semiconductor, will not be possible, right? But for this kind of applications, you can have organic LEDs, mostly photovoltaics, organic LEDs, and different kinds of sensor arrays. You can use organic semiconductor. So all of these points I was just reading that I have not covered anything. So room temperature processing is there, and biological system also it is compatible, but the main issue is that reliability issue in the organic semiconductors. That's a big issue. Stability is another issue. But not with all this, because some of this, what happened? It's working the other way. Some recent advances in organic semiconductors. So current flexible electronic prototypes commonly built on polymer thin films. Their cost is very high. So to address the issue, scientists have now started on biodegradable materials with a fraction of this cost of polymer thin films, right? So this is a conductive paper. So where you can use the paper and coat it with conducting gel, organic gel, right? And then you sandwich a layer and you can apply a voltage across this and it will start glowing. That one organic conducting organic paper, the glowing is shown here. And the production could be roll-to-roll process. The production can be at a rate of 30 meters per minute and cost will be $1.3 per square meter of this. So if you compare with the cost of any silicon based thing on this or any 3.5 semiconductor based display, it will be much more. And the flexibility will also not be there. So another thing is that in conventional semiconductor device making, electronic circuit making, you will have to go through several process steps like your oxidation, then metal deposition, then doping. All these steps you'll have to go through. But in organic semiconductors now, it is possible to get it in the form of a sticker. So to make a device, you can have multiple stickers and you can put one after the other to make a device. So that flexibility is enormous. So if you want to make a field effect transistor, so you can have the source contract as a level, drain is a level, gate is a level. So you put together, just like on a drawing sheet you do it, right? So similarly, the stickers you can put and you can make an entire device, right? So this kind of flexibility is there. So this is another recent advances in this. And now it will be like human skin. So this is a circuit, organic circuit. It can do lot of your functionalities it can. So these devices, it's looking like a cloth, right? It is so flexible and there are mechanisms by which it can correct if there is any fault in the circuit that can be corrected also, right? So this kind of technology has come. So now I'll talk about some of our contributions that we have done some research in this area and made some device prototypes. And I work primarily in these 4 labs. One is the Central Facility, Research Facility at IIT BHU, and the Center for Research in Microelectronics, CRME, and CIR at MNIT Allahabad. We have a interdisciplinary research lab there, and there's a Center for Excellence in Green Energy and Smart Sensor System at IIT Shibpur. It's a very good lab which is making commercial solar cell based on single crystal silicon, right? So there we also worked, and we had a major project from DRDO, design and development of low-cost plastic devices for electronic and photonic applications. So we make a few devices which I'll just briefly outline this. So one thing we have done that in organic semiconductor, this is, we have reported first that how we can modulate the conductivity of the organic semiconductors by adding some foreign materials to it. And so we have studied polycarbazole, and these are the ACM images. And then pure polycarbazole, then we have mixed your RGO, then we have nanoclay we have had, and your carbon nanotube we have used, and we have seen that, you will see that under SEM this changes, all these images, and it results in a change in the conductivity. And the band gap of the material, we have measured the band gap of the, calculated the band gap of the material, and you see that the conductivity for carbon nanotube and nanoclay and pure PCZ, the conductivity for pure PCZ is 757 siemens per centimeter, and which is ultimately rising to 1000, 1300 and 1538 by putting some other materials into this. Then we have developed an organic Schottky diode, where we have used a ITO coated glass substrate, and on ITO coated glass substrate we have a polycarbazole and amorphous silicon contact we have made, and we have made diodes which are similar to your PN junction diodes you find. So this is a kind of diode which is made of your organic semiconductor. So these are the characterization. I will not get into these details. So these are some of the images, AFM and SEM images. Then we have done this IV measurements of this polycarbazole, and you see that these IV characteristics are very good kind of characteristics if you compare it with silicon. Ideality factor is little high as compared to silicon, but this rectification property is very good in this. Then we have made a hybrid heterojunction. Sometimes we say that inorganic semiconductors are good in some way. Organic semiconductors have their own advantages. So if we can make a combination, make best use of both their advantages, then we can make hybrid kind of devices, right? So this is an example where on an N-type silicon we have grown a polycarbazole layer, and then we have the metallic contact, and using this we have made a diode kind of a structure, and the IV characteristics, we get quite good IV characteristics. Then polycarbazole and crystalline silicon based organic inorganic hybrid point contact solar cell we have made. One solar cell we have developed, and this is giving, as compared to organic solar cells where the efficiency is very, very low, it gives almost 11% efficiency, where we have a hybrid device which polycarbazole as organic semiconductor and crystalline silicon tip as your inorganic. And we have later on applied it. Recently we have, in 2021, we have published one paper in IEEE photovoltaics, where we have used this organic inorganic kind of a structure. One additional layer we have put organic materials, transport layer, and we have enhanced the efficiency of the conventional solar cell. So similarly, another diode we have made by using polyendol. And one organic light sensor we have made for smart traffic signaling. The green light sensor we have made using these organic semiconductors. So this is the configuration of typical OTFT, and we have developed this OTFT, used this OTFT, developed and used this OTFT for ammonia detection. We have 3/4 structures we have proposed, and we have seen that selectivity is a major issue. We have a combination of number of gases, but we have optimized this structure to detect specifically ammonia. So this is the fabrication steps. Some snapshots are given here. So these are the characteristics we have obtained, and this looks very similar to your inorganic semiconductor IDVD characteristics, current versus voltage characteristics. And this gives a very good sensitivity to this ammonia detection. And so finally we come to this concluding remarks. That organic electronic devices will be very promising, especially due to cheap manufacturing cost, flexibility, and easy integration with other systems. Automotive sector is one of the fastest growing segment for organic electronics. OLEDs already adapted in premier vehicles. Organic semiconductors are playing major role in sensor and energy harvesting in transportation system. We are talking of piezoelectric materials and energy harvesting from there. And flexible and sustainable organic semiconductor components in great demand for electric vehicles and autonomous vehicles also. Challenges remain around the long-term stability, which I have already mentioned, and the performance compared to inorganic counterpart. There is no denial of the fact that inorganic semiconductors are far, far away from in terms of performance, in terms of their reliability. You can see that my first laptop is still working. So your software is old, but still it is working. Even the calculator which I purchased while studying BTech is still working. So this kind of reliability you don't get from these materials. So the bottom line is that the organic electronics complement silicon in hybrid system, not intended to replace silicon. We are not going to replace silicon. We can't replace silicon. As I see for next 10 years also silicon is going to stay in your microelectronics applications. So it will add important features like smarter, lighter, and adaptive design of transport infrastructure. That's all I wanted to share with you. Thank you. Any question, any queries? Yeah, please.
Semiconductor world, how do you cater to the obsolescence management?
That's a big issue. That's a big issue. That particularly disposal of this, right? So the obsolete things and the things are changing so fast now. Today's mobile, you see that you don't go for replacement of the battery. You change the mobile because companies know that no one will be going to use it for a long. Now, often I also think that when we talk of green energy, say for example, right? Green energy or sustainable. How green is green energy actually, if I put a counter question to you? How green is this green energy?
For us, right now, we are still at the very nascent stage. We are building up the staircase step by step with the anticipation that in the coming 5 years, we'll try to capture our target because we are not going to go to 100% never ever.
No, but my point is a little different, right? Now you say that the emission will be near zero in electric vehicles, right? But what we'll do with the batteries after this? Urbanization, it will have an adverse effect on the environment. We cannot deny it. The way you put in facts and figures that this is this thing, we are going to reduce this cannot go together. There's a trade-off. So I think that way, this is a big challenge, electronic, this disposal of this. So when it becomes obsolete, what you will do with that? So I was just looking that over a period of time, I had 10 laptops. So what to do? None of them are now, because the software is now changed and your hardware is also changed now, they cannot perform the way we did it today. So what will do with this? I don't know. I have no answer for this really.
In the transportation industry, we are facing this thing as a big issue.
Yeah.
Because I'm making my equipment run for 35 years.
Yeah.
But down the line after 5 years, these products are not available in the market. They go into the generation 5, 10, 20 and we go for the availability of parts.
That's true. That's true. That's why one way this is advantageous is that there is a time when people used to repair an instrument or a gadget, or now we do not do it. We just throw it and buy a new one because it is affordable now. So repairing the instrument will be costlier than buying a new one. And as you are rightly saying that the things are changing, the technology is changing, the manufacturer is not producing it anymore. So it's a big issue. So our mindset has to change that. Use and throw kind of culture has to come. Yeah, but where to throw? Again, it will go into environment and it will pollute the environment. So it's a cycle that you cannot have both the things satisfied today. Technology will develop at the same time. It will have no adverse effect in the environment. It's not possible. Not possible to them.
Thank you, sir, for your insightful thoughts. Your expertise and global experience has given us so much to reflect on. Now, it is my honor to introduce our next distinguished speaker, Mr. Bishwaroop Bose, who is Domain Leader and Transfer Disciplines, Alstom. He has completed BE in Mechanical Engineering with honors, MS in Mechanical and Aerospace Engineering from Villanova University, and a PG degree in AI, ML, and Digital Manufacturing Applications from IISc, Bangalore. Mr. Bose has 10 years of experience in railways, 12 plus experience in aerostructures and aero engine calculation, and more than 5 years in material handling and storage, specialization in aerospace and railway mechanics structural engineering. He currently leads a team of 45 plus engineers in tender evaluation, design, simulation, safety, and transfer discipline. Earlier, he led 45 plus engineers and 25 subcontractors in calculation, optimization, and areas like vibroacoustic, thermal, aerodynamic, fire, and environment. He also served as discipline lead engineer, handling FEA and engineering calculations across industries. Today, he will be delivering his talk on materials for modern railway mobility transportation. Welcome, sir. We are truly honored to have you with us today.
Hello, good afternoon. Good afternoon, everyone. Note of thanks to VC, Honorable VC, and all the faculty members. And my special note of thanks to Dr. Jyoti Sharma and Dr. Kuldeep for arranging my visit. I'm really thankful and grateful to all of you to giving me an opportunity to present for such an esteemed organization. I have conducted one WC expert presentation for design and calculation 2 years back, but that was online. I could not visit. So I wanted to recap that one, but just due to shortage of time, I'm covering in a very nutshell about the various design calculations, disciplines in a nutshell. It will be a bit interesting because the speakers who presented before me, they are the stalwarts of the field. So they have gone such a deep in the aluminum and structural alloys. There is nothing much for me to cover. But basically, I'm also not a material expert, but I work a lot with the material applications. I'm basically a structural calculation and design expert. So we work a lot with our design is dependent on the selection of the material. So selection of the material is very critical for us. So I'll quickly go over to the structural disciplines, each of the disciplines which I head, and each team size consists of 20 plus. If we go to the first structural simulation for any aircraft structure or any railway structure, first we have to see the directional stiffness, which is bending, axial, and torsional. Then we also have to see the shock and vibration of the various electrical equipments attached with the railway under frame. Then the various interior structure, which Naveen sir has told, that we extensively do the calculation of seat, ceilings, the side walls, the end walls, all the static and the fatigue calculations. And also we do the calculation for railway signaling and the railway car body. If time permits, I will show you some of the calculation notes which I presented to RDSO and for Mumbai Line 3 and Mumbai Line 4 customer for their calculations. We also do the testing of the car body, and we do a very robust correlation between the testing as well as the simulation as per the structural validation requirement. So this is in brief the calculation. It's a huge domain. You can see this 75 people works in various projects which covers all over globally, which is APAC region, North America region. Just to tell you that in India we have the facilities in Sri City and in Sauli, where the train car bodies are manufactured and they're delivered in Canada, in Montreal, and the complete region of Australia. We manufacture in Sri City the car bodies of Sydney, Perth, and Melbourne, which is currently in progress. And I had a list of all the metro and the ILOCO projects, which I'm working in Alstom for last 10 years. So starting from Chennai to Kochi Metro and ILOCO, almost all the metros and regional trains and ILOCO have worked as a design engineer and a calculation engineer. So our next team is CFD and thermal team. It is, as you can see, it is mostly deals with the Navier-Stokes equation for some of you who are doing the thermal and the CFD calculations. It is a very coveted field and a very demanding field. If you, in future, if you build your career, it will be highly demanding if you work on thermal and the CFD calculations. So various electrical equipments have very high temperature. So we have to simulate and see exactly how much is the temperature in the surrounding. Based on that, the electrical equipments and the structural items will be positioned. And then we will do the structural simulation. So this is a very important field. There are various standards to comply for the various electrical equipments like transformer, CVS units, and the HVAC unit. The next team is vibroacoustics. It itself is a very important field. We have various both simulation as well as the testing tools, and there are external and internal noises which we should comply against various railway standards. And it is typically the internal noise should not go beyond 70 dB, and also the external noise, which is called squeak and rattle, they should be within a certain limit. So we have a dedicated team who does a very detailed simulation as well as the testing, and the testings are done for a period of 7 to 10 days, where they have to work till the midnight to get the readiness of the track. When the track will be empty, in the depot the train will run, and they will do the physical testing. So this is also a very specialized and very demanding field. The next one is fire safety. The name itself tells that how much important it is. A train has to be fire safety compliant under various standards. In the Indian scenario or in the APAC region, we should comply to EN 45545, and for the North American region, it is NFPA 130. There are various clauses where each and every material should comply with the means of proof from the supplier, and for the fire safety inventory list should be complied, and there will be a running capability test. We have a software called PyroSim where we run between the two nearest sessions, and in a particular fire outbreak condition, whether all the materials will be safety compliant or not, we do a software simulation, and also a typical fire test is done for a fire floor barrier and the driver partition wall. So next team is ergonomics and human factors. I will very quickly go through this. This is also a very demanding field, where the various structure of mannequin is built of a man and a woman driver, and the various ergonomic aspects are tested in the driver cab region, in the saloon region, and there are various standards to meet. Okay, it's also a very vast field, and around 10 people are working in this field. Then we have the comfort discipline for the passenger flow and lighting. It is also, we use two softwares. One is ANSYS SPOS and a Legion software, where the dwelling and the passenger evacuation is evaluated. There can be side evacuation and front evacuation in case of emergency. So all these things can be simulated. And also an external lighting, what you see now, this can be simulated in a software where we see the luminance and illuminance inside and outside the train. There are various comfort standards which we should comply in a railway. these are all very specialized field. And the next one is environmental, climatic condition and corrosion. I think we discussed enough, but it's a very, very crucial field that all of our things should be properly painted. You can see the passivation, how it is passivation clean, the electropolishing, all these. There are various standards and very, very detailed engineering standards are there, follow for our manufacturing sites as well as our suppliers. Then we have eco-design, which is a very important field. We do the life cycle analysis, recyclability, the end of life manual, all these things are done in details. So this is all for now. There are, if there is time, I can go through some calculation notes which is presented to the RDSO. If we have time, we can. Okay. So I'm going very fast because each of these fields are, by itself, it's a career for people. So now I'll go to certain, I will give one example. This is a calculation I did in the year 2019 for Smart Coradia, where, there is a weight reduction target was given. If you can see, this complete structure is like a steel structure. So we simulated with software simulations of HyperWorks, where we made a sandwich panel of balsa wood and a combination of that cross section is given here. This is the aluminum sheet balsa frame. It is like a honeycomb panel. If you see a honeycomb, it will have a shear resistance, and the top and bottom surface will have bending, tension and compression, and the middle core will be shear resistance. So this, we had a very huge weight savings, and this was basically, it was applied in SNCF. SNCF is OEM in France, which is equivalent to our BEML in India. So they have, there is a specific design practice is authored with this. And also, very quickly I can go through, there is a Kochi front mask. There is some huge weight savings we have done through the composite FRP things. And here we have a layered structure where we do a special simulation of Psi-U and Psi-Hill. Okay, so this is all. There are many materials due to shortage of time, I could not cover. So if you have any question, I am available tomorrow. So please contact me. I have many materials which I could not cover. So any questions, please ask.
Thank you, sir, for those valuable insights. We would now like to present each of our esteemed speakers with a token of our appreciation. I now request our esteemed Vice Chancellor, sir, to the honors. To Professor P.S. Roby, please accept the token of our appreciation. To Professor P. Chakravarti, please accept the memento of our gratitude. To Mr. Biswaroop Bose, please accept the token of our appreciation. As we bring this workshop to a close, I would like to invite Dr. Jyoti Sharma, Assistant Professor at Gati Shakti Vishwavidyalaya, to propose the vote of thanks on behalf of Gati Shakti Vishwavidyalaya.
Distinguished speakers, Honorable Vice Chancellor Sir, respected colleagues, and my dear students. As we conclude our national workshop on material for transportation, I like to extend my heartfelt gratitude to all the eminent speakers, senior professors from IITs, scientists from CSIR lab, and industry leaders who share their invaluable experiences with all of us today. It has been our honor to organize this workshop with such an extraordinary assembly of academia, industry, and institutional leaders. The depth of the discussion today, from electric mobility and aerospace material to smart system, sustainability and indigenous innovation has truly been inspiring. The ideas shared here will not remain confined to this hall. It will shape our academic direction in the year to come. Before I speak about the future plans of our university, please allow me to briefly share my own academic journey, which deeply shaped my commitment to this field. I completed my bachelor and master degree in physics from Randa House University of Delhi. I earned my PhD from Department of Physics and Astrophysics in the area of preparation and characterization of magnesium ion conducting polymer electrolytes for solid state batteries. Following this, I undertook my postdoctorate from University of Texas in the lithium battery technology. My academic and research journey, particularly in advanced energy material, has strongly reinforced my belief that material science is the central to the future of transportation, energy, and sustainability. By the guidance of our Honorable Vice Chancellor, Sir, our university will soon be launching bachelor and master program in the field of materials science engineering. However, our approach will not be conventional. It is industry-driven, application-oriented, research-integrated, and future-ready. The insight and the experience shared by our eminent speakers today will directly influence the design and the structure of our curriculum. We are not designing a course in isolation. We are building it in partnership with academia, industry, and research institutions. We also intend to pursue strong institutional collaboration with the premium academic institutions, industry, and the national laboratory so that our students will benefit from the internship pipeline, joint research initiatives, co-development laboratories, and the industry mentor projects. The goal is simple yet ambitious: to create a material science program that does not merely award degree, but produce innovators, problem solvers, and the technology leaders. Let this workshop mark the beginning of the long-term partnership between academia, research institute, and the industry. An event of this magnitude requires significant support. I would like to extend a special note of thanks to Jindal Stainless Limited for sponsoring this workshop. This workshop has played a vital role in making this initiative successful. I would also like to extend my senior appreciation to our distinguished speaker, Professor Prasad, our guest of honor, for his visionary global perspective on advanced material. Dr. P.S. Robbie, Professor from IIT Guwahati, for his valuable academic insights. Dr. S. Parivalal, Chief Scientist at CSIR-CERC, for bridging research with real-life engineering. Professor P. Chakravarti, former professor of IIT BHU, for adding academic depth to our talk. Dr. Shankar Venugopal, Vice President at Mahindra Research Valley, for his forward-looking industry insights. Dr. Naveen Chandra and Dr. Biswarup Bose from Alstom for sharing practical perspective for the rail sectors. Professor Amol Anand Gokhale, Professor at IIT Bombay, for his research-driven academic contribution. Mr. Arup Kumar Malik, Executive Director of HAL Academy, for sharing his leadership insights in aerospace manufacturing. Dr. Senthil Kumar, Senior Principal Scientist at CSIR-NAL Laboratory, for his expert inputs on aerospace materials. Mr. Ranit Rana and Mr. Pankaj Agarwal from Jindal Stainless Steel for sharing valuable industry perspective on stainless steel applications in transportation. Your guidance, expertise, and encouragement means a great deal to all of us. I acknowledge the faculty's organizing committee, staff, and students for their help and support. Thank you once again for being a part of this important journey. We look forward to your continued collaboration and mentorship as we build together the future of material science and engineering. Thank you so much.
Thank you, ma'am. Now I would like to kindly request everyone for the group photograph.